Hello, we're back. That was easy, right? All right, I am about to hand off my hosting responsibilities to the inimitable, the one, the only Andrew Dessler. Another, by the way, second generation scientist, right, Andrew?
Yeah, I would say second generation.
All right, good. From New York to Texas, I pass the baton.
Thank you, Rob. It's good to see you. It's been a while.
It has. All right, good luck, Andy.
Thanks, Rob. Well, welcome aboard, everybody, to the beginning of live stream number 4. I hope everybody is doing well. And so let's go ahead, and we're a few minutes behind schedules. Let's go ahead and bring in our next speaker. The next speaker is Becky Alexander. Professor Alexander is in the Department of Atmospheric and Climate Sciences at the University of Washington and a co-PI of the UW ISO Lab. She has a Ph.D. in chemistry from UCSD, University of California, San Diego, and her research group studies how aerosol formation and the oxidative capacity of the atmosphere respond to climate change, human activities, utilizing global chemistry, climate modeling, and isotopic analysis. So Becky, welcome, and take it away.
Great, thanks, Andy. So I'll be talking about some of my group's work on investigating chemical side effects of a geoengineering strategy called marine cloud brightening. So marine cloud brightening proposes, this is not happening, it's just a proposal that would use sea salt aerosol to brighten low clouds over the ocean and thus cool the climate to counteract the warming effects of greenhouse gases. So the general idea here is shown on the left, where if you add additional aerosol particles to the atmosphere, especially smaller aerosol particles, you will increase the number of cloud droplets in a cloud because you'll have more nucleating particles on which water vapor can condense. And if you have more smaller drops as opposed to fewer larger drops, that increases the brightness or reflectivity of the cloud. Another word for that is albedo. And if you reflect more sunlight back to space by brightening clouds, then that has a cooling impact on climate. And the idea, which does not yet exist, is to have sort of autonomous ships that drive around the ocean and spray a kind of sea salt mist in the lower atmosphere in order to brighten clouds. And this is particularly effective over the oceans, we think, because the oceans, as you can see in the image, are dark. And so if you can put something that's reflective above the oceans, that will have a cooling effect on the climate. And we know that this works from observations of ship tracks, which is shown here. So this is a satellite image. You can see clouds, but in addition to clouds, you can see lines, these ship tracks. And this is from ships that are emitting aerosol particles. In this case, it's not sea salt aerosol, it's sulfate aerosol, but it has a similar effect where you increase the number of aerosol particles, and that will tend to brighten clouds, especially in regions where clouds are already forming. You can then take those clouds and just make them brighter. And so a question that I've had in my group is, what does this do to the chemistry of the atmosphere? And are there any chemical side effects that might in turn influence the efficacy of this climate intervention strategy? And what kind of prompted my interest in this is the fact that sea salt aerosols are the largest source of reactive halogens in the troposphere, in the lower atmosphere. So these are reactive halogens, chlorine and bromine. And so sea salt aerosols are emitted from the ocean surface, just wind-driven emissions naturally. Also blowing snow on first-year sea ice especially, which tends to be relatively saline, emits these sea salt particles into the atmosphere, and sea salt contains chloride and bromide. And once it's in the atmosphere, species that are in the gas phase, chemicals in the gas phase, can react on the surface of the particles, and certain reactions will release the bromine into the gas phase where it's very reactive, and it reacts with species like oxidants like ozone and NO2, which affects the chemical composition of the atmosphere. So most of us are familiar with reactive halogen chemistry and its impacts on ozone in the stratosphere. So this is an image of the Antarctic ozone hole from NASA. The image in 2008 and in 1979 before the ozone hole became significant. And the Antarctic ozone hole occurs in austral spring, September, October, every year. And the ozone depletion is driven by a combination of reactive halogens, where in the stratosphere, their main source is chlorofluorocarbons, not sea salt aerosol. And these reactive halogens also require, for this strong effect on ozone to occur, they require a surface on which they can react, and that is supplied by ice particles in polar stratospheric clouds. So in some ways, these ice particles can be analogous to the sea salt aerosol in the troposphere. And although the ozone depletion is maybe not quite as dramatic as it is over Antarctica in the springtime, it can be pretty significant and even dramatic in the lower atmosphere as well. So in the 1980s, we learned from observations that in the springtime in the Arctic, ozone concentrations at the surface would go from their typical background concentrations of around 40 parts per billion, or ppb, and within a couple days could really plummet down to near zero concentrations before recovering, and this would occur episodically throughout the springtime. And these plot on the left also shows that these ozone depletion events are accompanied by increases in reactive bromine. And so we now know the two are linked, that the reactive bromine is causing these ozone depletion events. And we can measure one species of reactive bromine, BRO, from satellite, which you can see here on the right. And we've learned from these satellite observations that BRO can get quite high in the springtime in both polar regions, particularly over first-year sea ice, where the saline blowing snow is an important source of sea salt aerosol. Now, at first, we thought that this effect in the troposphere was really unique to polar springtime. But now we know it's ubiquitous throughout the atmosphere. And these are just some examples of observations of a couple of different reactive halogens, BRO and IO, at the surface. And this is showing on the left some measurements in the tropics, on the right some measurements in the mid-latitudes. And what we've learned from these measurements is that reactive halogen concentrations are pretty low, on the order of 1 part per trillion. However, similar to the stratosphere, because the reactions are nonlinear, they recycle multiple times and are catalytic, that they can disproportionately to their concentrations destroy significant amounts of ozone in the troposphere, similar to what is happening in the stratosphere. And so now we know that halogens, through this mechanism, can have an indirect impact on climate. So I've just mentioned that halogens will reduce ozone. And so this is just a model simulation, which is estimating the radiative or the climate effects of the decrease in ozone driven by reactive halogens in the pre-industrial and the present day. So ozone is a greenhouse gas, so it has a radiative effect. And so the decrease in ozone results in a cooling on the order of about 0.2 watts per meter squared, as estimated by this one model shown here. Now, because ozone is an important source of OH, the hydroxyl radical, OH is important because it's called often the atmospheric detergent of the atmosphere because it reacts with most trace gases in the atmosphere, determining their atmospheric lifetime. And one of the most important gases that it determines the lifetime of is methane. So methane, 90% of it is destroyed in the atmosphere by reactions with OH. So OH is really important for the lifetime and the concentration of methane in the atmosphere. So if you lower ozone, you also lower OH, and that results in an increase in the methane lifetime. And this model is calculating that halogens then will lead to an increase in the methane lifetime, the methane relative forcing or warming impact of methane on the order of 0.1 watts per meter squared. And halogens, although they're not the main loss process for ozone, they're significant. Models estimate that they lead to 20 to 30% of ozone loss, and these are corroborated by some field campaigns that show that halogens are important for the ozone budget. And iodine represents, which is shown here in this brown color in the troposphere, represents about 2/3 of the total halogen-mediated ozone loss, with bromine representing the other third. Chlorine is a pretty small effect on ozone. And so ozone, again, is important because it can photolyze to form O-singlet-D, an excited atomic oxygen that can react with water vapor to form OH, which is the main loss process for methane. So our driving science question was, how does marine cloud brightening, through its impact on halogens and ozone and OH, impact the lifetime of the greenhouse gas methane? So we explored this using a global chemical transport model, GSChem. This isn't a climate or weather model because it uses observed meteorology from satellite observations to drive the model. So it uses observed wind speeds, temperatures, etc. It has very extensive coupled gas and multi-phase tropospheric chemistry that includes the relevant halogen chemistry. And it includes things like natural sea salt emissions that are dependent on temperature and wind speed, emitted in the small size range, the accumulation mode. This is the radius, dry radius shown here, as well as the larger size, the coarse mode. And so what we did was we implemented in the model 2 marine cloud brightening or MCB strategies, MCB low and MCB high. And the total amount of sea salt aerosol that we emit into the model are based on previous climate models as part of the a geoengineering model intercomparison project, or GeoMIP. So we kind of took what they had done and put that into our chemistry model, GSChem. And we emit all of the MCB aerosol in the smaller size bin, which is what the mechanism proposes doing. And that's the smaller sizes that are most effective at brightening clouds. And so I'll show you a few slides that look like this. This is showing the sea salt aerosol concentrations at the surface in the model and just the standard model. So only the natural sources of sea salt aerosol. And so you can see the highest sea salt aerosol over the Southern Ocean, where there's lots of ocean and it's windy. So that makes sense. And then below is showing the change, the additional amount of the MCB sea salt in the MCB low on the left and MCB high on the right. So you can see that we're emitting the MCB sea salt aerosol in the tropics. And that's because that is what was done in the GeoMIP climate model simulations. So these are, I'll note, these are substantial increases in sea salt aerosol locally up, to a factor of 40 increase. So this is the impact that MCB aerosol has on reactive bromine and chlorine. So this is the natural, or just the standard, in the standard model, the reactive bromine and chlorine on the left, and on the right shows the change after adding the MCB emissions in the low and the high. And so you can see that we are increasing the reactive bromine and chlorine in the tropics in the same place we're emitting the aerosol as expected. And that increase is on the order of 20 to 40%. So pretty significant increase. Here is showing the impact on iodine. And the iodine has the reverse sign. So iodine decreases. And the reason for that is because the source of iodine isn't from the aerosol itself, it's from the sea surface. Iodine, reactive iodine, is emitted into the atmosphere following deposition of ozone to the surface of the ocean, where it reacts with iodide in the ocean and emits gas phase reactive iodine. And so we're getting decreases on the order of 5 to 15% in the model. So you can see that those decreases in iodine are driven by the decreases in ozone. So we do get a decrease in ozone as we expected. And then that leads to decreases in iodine. And the decreases in ozone also lead, as expected, to decreases in OH, the hydroxyl radical, which is what controls the lifetime of methane. So we look at how this influences the methane lifetime. So this is showing the methane lifetime in years in the standard model, total, and then the lifetime that's determined by reaction with OH and reaction with the chlorine radical. So you can see if the chlorine radical was the only oxidant, methane would have a lifetime of almost 300 years. Really, the lifetime of methane is controlled mostly by reaction with the hydroxyl radical OH. And when we add our MCB aerosol, because we lower ozone, we increase the lifetime of methane due to the reduction in OH. Because we're emitting a lot of chlorine in the form of sea salt aerosols, we do increase the chlorine radical as a sink for methane. But it's still such a minor sink that has a pretty negligible effect on the lifetime of methane. And so in our model simulation, our MCB scenarios result in a net 3 to 6% increase in the methane lifetime globally across these two scenarios, the MCB low and the MCB high. So there are a lot of uncertainties in reactive halogen chemistry, and it's an active area of research in the atmospheric chemistry community. And we followed this up with a more recent study, something that's still in progress. What if reactive iodine does not decrease? So the figure on the left shows the iodine budget in the model results that I just showed you. So we emit iodine from the surface of the ocean following ozone deposition to produce reactive iodine. And that can either be deposited to the surface of the earth, or it can undergo uptake onto aerosol and then be deposited to the surface. So there's no recycling of iodine in the aerosol in the model. There are reasons for that because there are a lot of uncertainties, but we do know actually that it does happen. And so we've been working on implementing an updated iodine chemistry in the model. And so now, instead of it being a one-way transfer of iodine from the gas to the aerosol phase, it can be recycled and go back from the aerosol phase into the gas phase. And this happens in the model on the order of 8 times on average. And this significantly enhances the iodine concentration as well as the iodine lifetime in the model. So we've reinvestigated our MCB scenarios to see what impact this has on the methane lifetime. And this is just a reminder that it's actually iodine is 2/3 of the total effect of halogens on ozone. And so this is quite important to determine. And so these are our preliminary results. So here what I'm showing is just the base model concentrations of reactive bromine, chlorine, and iodine. And on the right shows the change after implementing. Here we just looked at our MCB low scenario. And you can see, just like before, we have increases in the tropics for bromine and chlorine. However, now we're getting the opposite effect from iodine. We're getting also increases in iodine. Interestingly, the MCB results, these results here, result in a net decrease, not an increase this time in the methane lifetime. And this is as a result of some additional heterogeneous chemistry that has been implemented in the model since our previous paper. And that's mainly influenced by emissions or recycling of NOx on sea salt aerosol. So if you put all of this together, we have concluded in our modeling studies that marine cloud brightening would have a substantial impact on the abundance of tropospheric reactive halogens. That is a pretty certain finding. The impact on the methane lifetime is uncertain, but in our variety of modeling studies where we really try to hit it hard, so we're not trying to be conservative, we're trying to see what the maximum impact could be, we're getting impacts on the methane lifetime plus or minus on the order of a few percent. Although this is a significant change, its impacts on climate via radiative forcing is relatively small compared to the cooling impacts of sea salt aerosol itself on brightening clouds. And so halogen chemistry is highly uncertain. More studies are needed, especially laboratory studies, because some rate constants are still unknown. But it's, I think, important to study, as this might have an impact on not just things like methane, but also air pollutants in certain areas. So I'm happy to take any questions. If there's time. I think I went over. Sorry about that.
I think we have time for one quick question, which I'm going to use host privilege here. I'd be curious to know what's your view on just geoengineering in general. Is this something that you think we're likely to do, we should be doing, or just we should be researching? There's a lot of debate, a lot of extremely strong feelings. So I'd be curious to know what you think about that.
So I'm generally feeling like most of the time, I'm very cautious about it. Generally, my first reaction is that it's a bad idea. I also know that people are really interested in doing it, and there are private companies, startups that are promoting various ideas. MCB is only one of them. And so I think it's really important for scientists to examine the efficacy and potential side effects of these strategies, because in case there is a really bad side effect, it would be good to know about that before people or governments, for example, begin to implement these strategies. And Australia is implementing this strategy over the Great Barrier Reef. They are injecting sea salt aerosol over the lower atmosphere over the Great Barrier Reef, attempting to influence the coral bleaching event, so cooling off the surface of the ocean. So I think it's just really, I'm not promoting it. Generally, I think it's not a good idea, but I do think it's important scientists know why specifically it's not a good idea.
Yeah, no, I agree with that. We should be researching it because, you don't know what's going to happen in the future, and you don't want to get to a situation where something really bad happens and people say, well, we should geoengineer, and we say, we don't know what's going to happen if we do that. So I think it's important. All right, I think we have to move on, but thank you very much.
Thank you.
Becky. That was really, really a great talk. We kind of rushed into this. Introduce myself. My name is Andy Dessler. I'm at Texas A&M, and thank you for joining us for our 27 of the live stream. 23 of the live stream, 27 hours to go. So we've seen a lot of great talks so far, and our next speaker is no exception. But let me just say quickly why we're here. Weather and climate forecasts are crucially important for society. I think people don't appreciate the extent to which we rely on the weather for our survival. You think you go to Kroger, that's where bread comes from. Bread does not come from Kroger. Bread comes from farmers, and then it shows up eventually at the store. And just there's so many ways that we rely on the weather, for food, for example, and for power, and for all sorts of things. And so we really need to understand this. And there's some really bad budget cuts, which would really hamper the U.S. climate and weather effort going on. And so please call your representative. And let me just tell you one thing I tell all the people, which is that, a lot of people are hesitant to call because they don't want to be, combative, and they're afraid the congressional reps, the person who answers the phone is going to yell at them. Let me tell you, these people are paid to politely listen to you. So don't have any fear about calling them. They're not going to get mad if you criticize the rep. They're not going to get mad if you say something that they don't like. They're going to be super polite because that's literally their job. So please call or write your representative. Go to the link below. All right. Having said that, let's move on to our next speaker I'm very excited about. Bronwen Konecky is an associate professor in the Department of Earth and Planetary Sciences at Washington University in St. Louis. She has a Ph.D. from Brown, and her research focuses on paleoclimatology and the past and present effects of climate change in the tropics. Outside of academia, she is a singer-songwriter. There's some question as to how active she is. So I will just leave it at that. But let me turn it over to you, Bronwen. Thank you.
Thanks so much. Well, it's a pleasure to be here and speak with you. I will not be singing to anybody today. And to share the research that our group has been doing on extreme rainfall here in Missouri and elsewhere in the central US. So like Andrew said, I'm a paleoclimatologist. Paleo means past. And the goal of paleoclimatology is to use the study of ancient climates and that means climates prior to the emergence of modern instrumental data, to really understand how the Earth system works. Paleoclimatology helps us to understand how the climate system works in general, but also gives us really good long-term context for some of the changes that we're seeing today. So my group at WashU integrates several different approaches to studying changes in past and present climate, from reconstructing it to observing it in modern weather data, using climate models. And we integrate these things all together. But I want to tell you a story today about something that happened in 2022. So the person on the screen here is Dr. Alex Thompson. At the time, Alex was a postdoc in my group here at WashU, and we were working on some projects that were blending climate models with data from lake sediments and other paleoproxy archives, projects that were completely unrelated to what I'm going to tell you about today. In the summer of 2022, we experienced a massive rainstorm that hit St. Louis. And what you'll see in the upper left is this was a band of precipitation that really stretched across the central and eastern US. And if you look at the radar map at the bottom left, you see the arrow pointed to St. Louis. And what you'll see when it starts repeating is these bright orange and red, basically like train cars pummeling one after the other, the metropolitan area of St. Louis. This happened overnight. In the middle of the night. And by morning, we had really extreme and excessive flooding all across the region. This storm system then continued to move across the central US. So it hit us on July 26th. And by July 28th, it also hit eastern Kentucky and caused additional flooding, catastrophic loss of life. So this was a really, really severe event that occurred. Anybody who lived in St. Louis at this time can tell you exactly where they were and how they remembered it. We broke the record for the highest 24-hour rainfall ever recorded. We received in just 6 hours the amount of rainfall that we would normally receive in a typical July and a typical August combined. So this was an extreme amount of precipitation that fell in a very short amount of time. All over the news, and there were other events happening that year as well that were extreme, and we saw a lot of talk about how this was a really rare event. It was a 1 in 1,000 year event. And being paleoclimatologists, Alex and I thought, that's curious. How do we know that, since we don't have 1,000 years of data? And we just got really interested in looking at this further. And so this really spun off into a whole new side project where we started looking at how these estimates are generated of the return intervals or return periods of storms of any given magnitude. So what you're seeing here is a product using station data from the St. Louis Lambert International Airport, which is one of the longest running, highest quality data sets from weather stations that we have in this region. This is a product coming from NOAA Atlas 14, although they are in the process of updating this, and it's going to have even better estimates of precipitation. What you're seeing in this dashed line is the magnitude of that July 26, 2022 storm. And where it intersects with the black line is the median, basically, of this return interval. And what you can see there is that according to that where it intersects the black line, it was more of a 200-year event. But if you look at that full confidence interval, it actually could have been a 1,000-year event, and it also could have been a 100-year event. So that's not maybe as useful as it could be. And also, if we look at the magnitude of events that really truly are 1,000-year events, according to this station, it actually spans a range of something that could be a little bit less than 8 inches to almost 15 inches. So again, when we think about sort of the city or local scale planning and how we sort of deal with these types of disasters as they happen, that's a really big range to have to deal with. It's very difficult to for managers to adjust to something like that. So we said, why don't we try extending our observations back in time? This is what we do as paleoclimatologists. Many approaches we could have used. We decided to blend weather station data with climate model experiments. And we did that for a couple of reasons. One is that we really needed long-term statistics on rain events that were the size of this rainstorm that occurred in July 2022. That said, climate models are not weather models. Within a climate model experiment, the timing and magnitude of any individual storm is going to be really subject to internal variability within the climate system. So just one climate model experiment was not enough for our purposes. We needed multiple climate model experiments, but run by the same model over and over and over again to give us an ensemble of 1,000-year plus long simulations that we could use to investigate this type of internal variability. So we turned to the Last Millennium Ensemble, which is a suite of experiments performed by NCAR in collaboration with university partners and performed with the Community Earth System model. There is no suite of simulations like this anywhere else in the world, even now. The Last Millennium Ensemble is a single model ensemble, meaning that the same model, same experiment was run over and over and over again. Any differences that arise are not because of forcing, but rather due to internal variability. This ensemble was run because of longstanding community demand for assessments of internal variability versus forced changes that occurred during the last millennium and during the industrial period. So thank you, NCAR, for running these simulations. They're all publicly available online for people like me and Alex to then go click and download and then use for various purposes. So we picked the 4 full forcing ensemble members that were run starting at the year 850 and all the way out actually to 2100. So during the period of time that has occurred already, those simulations used all the known climate forcings that were important. And then going to 2100, the simulations used one of the RCP scenarios, RCP 8.5. And that really gives us a high greenhouse forcing scenario to work with. So Alex developed this whole new approach to blending climate model simulation data with weather station data. And in doing so, we quickly discovered that a lot of the choices that you make along the way can be really influential on your ultimate finding. And we didn't really want that. We wanted to be able to really allow for robust findings that were not dependent on a particular choice that we made along the way. So what we did is we developed a workflow that went through blending these climate model data with weather observations and then repeated it thousands of times, making different choices each time. And that really allowed us to quantify the uncertainty that arises from any of those different choices. And so what we get at the end is a blended data set, an ensemble of blended data of the maximum rainfall occurring over a 24-hour period in any given year. And so that's what you are seeing here. So all of the symbols that you see are that maximum daily rainfall for that year. The black symbols are the observational data, and the colored symbols are the different ensemble members from the Last Millennium Ensemble. What you're seeing at the bottom is a bunch of bars. The horizontal black bar represents the 1,000-year time period prior to the year 2022. And the blue bar represents the whole pre-industrial period, so all the way to the year 1850. The yellow bar represents the historical period, the period of time when we have some greenhouse forcing and we have weather station data. And then the red bar is the future scenario with our CPA 0.5. So what this allows us to do is then compare the storm of the magnitude of the July 2022 storm with these different reference time periods. So what you're seeing here is our updated perspective on the July 2022 rain event. And so that event is shown here as that vertical dashed line with the gray shading on either side. And you can see that from this distribution of these maximum daily rainfall data that you see here, regardless of which reference time period we use, this was an extreme event. It really fell in the tail of the distribution, regardless of which one of these you pick. We knew that already. What we were then able to do is develop some better constrained estimates for the return period of an event of this magnitude. And we found that in St. Louis, this was not a 1,000-year event. This was more like a 534-year event, with some error bars giving us sort of a range of the recurrence period for an event of that size. And in Eastern Kentucky, this was a 282-year event, which is really significant considering that Eastern Kentucky especially had catastrophic loss of life during this storm. We also found that an event of this magnitude occurs even more frequently in a high greenhouse future. So relative to the pre-industrial period, which is the blue box that you're seeing here, these two blue boxes, the top is for St. Louis, the bottom is for Eastern Kentucky. Relative to that period of time, an event of this magnitude is almost twice as likely in a high greenhouse future in St. Louis, and almost 4 times as likely in Eastern Kentucky. So, rainstorms like the July 2022 catastrophic event are more frequent than we actually had appreciated already, and they're going to be more frequent moving forward. So the question is, how do we leverage climate research to improve the resilience to natural hazards that we have in our communities here in the Midwest, where we already have really wild weather, and the weather is going to become even more wild in the future? The good news is, because we already have a very variable climate here, just improving our resilience to the variability that we already experience now in the 2020s actually also builds our resilience to future extremes. And so that's really, really useful information. But we have to know what kind of a future to prepare for, whether events like these are going to be twice as likely, 4 times as likely, et cetera, et cetera. So this is where this type of research really becomes crucial. We have to really understand better these fundamental relationships between climate variables that we study and the actual consequences that matter the most to our communities, like flooding or public health consequences, for example. This is where climate modeling centers and community-driven experimental design are absolutely mission critical. These publicly available data sets are what made our Midwest-specific research affordable and therefore possible in the first place. And I'm really grateful to NCAR and to the CESM community for making it possible to do the science that we need to do in order to address these weather-related hazards here in my home in Missouri and in our nearby communities. So I'm happy to take some questions. Thanks.
Thank you. That's a super interesting talk. Are you guys going to highlight questions from the chat? I have not actually been looking, or I could ask. I'll start off asking a question. Oh wait, here's one. We have a lot of students watching the stream. What science classes from high school and undergrad levels are most connected with your research?
Woof. Congratulations. I've never gotten that question before. So I think that there's a number of different courses at the high school level that I think are really useful for setting somebody up for understanding climate change or for weather. If your high school teaches climate science, great. Probably it doesn't. But climate science is really an integration of physics and earth science and several other fields like that. And so I personally in high school, I took AP environmental science, which is what set me up for this career in the first place. But even just getting some really basic training in physics and chemistry and biology, these are all setting us up for understanding the type of work that we do.
So what should cities be doing now to adjust for sort of an uncertain future, because it's really kind of a tough situation they're in. A lot of the infrastructure was built in the 80s for a climate that really doesn't exist anymore, or very shortly won't exist. So what would be your advice to city planners?
Yeah, it's a really great question. And I would say actually in St. Louis, the infrastructure was built in the 1880s, right? So we're really talking about very ancient infrastructure when it comes to our storm drains and things like that. So this is really critical. And in St. Louis, many of you probably heard that last year on May 16th, we had a horrible tornado that devastated communities in my neighborhood and neighborhoods just north of me, right in the city. And this event, as well as the event like this storm in 2022, really opened my eyes to what we need to do in order to prepare for climate-related disasters in the future. And obviously, funding is important, right? But what I've seen even more, maybe even more than money, is integration and communication at the city level among all the different agencies that are involved in disaster preparedness, as well as disaster response. So this means emergency management services. It also means working with community organizations to be able to get the word out really quickly. We had sort of a well-known failure of our tornado sirens last year during that event. That was really a problem. And we've also really struggled as a city and during, I would say for years, and especially recently, at coordinating the responses of the city level government to the state level government and with FEMA. And that communication is really not straightforward. And this is not just sort of a one-off thing that we can say, well, a big rainstorm comes along and then we kind of adapt to it as it happens. And then, moving on, we just sort of forget about those lessons moving forward. These types of events are going to become more frequent. This actually becomes the fundamental crux of city management, is being able to do that level of communication and preparedness. So really communication, preparedness, integration, and working directly with community organizations in addition to funding.
Well, thank you, Bronwen, for your really great talk, and let's move along. So thank you for joining us. Hour 23 of the Weather and Climate live streams. We have 27 hours to go. My name is Andy Dessler. I am at Texas A&M. And before we move on to our next speaker, let me remind you why we're here. The U.S. has, I'm still going to use present tense, the greatest scientific system in the world. Everybody in the world wants a US PhD. That's why, everybody's from all over the world's applying to US grad schools. The smartest people in the world we accept, they come over here, and of those, the smartest of those, we keep them. This is this enormous benefit to the US. And if you look at, if you walk down the hall of a building at NASA, I worked at NASA for 10 years, it's like the UN. It's people from all over the world are here helping the US and helping science. And so the US's science infrastructure is this enormous, amazing public institution that is really getting ravaged by the present administration. At least that's what they want to do if you look at the budget. And so everybody should be calling their representatives at that link and telling them to fully fund NASA, NOAA, don't break up NCAR, and push back on OMB regulations, which I think is what we're about to hear next from Andrew Williams. Is Andrew available? He is here. Let me introduce Andrew. Or have you already been introduced, or should I introduce you again?
You can introduce me again, so I can fix the last little bit of my slides.
Sure. So Andrew Williams. So it says here you are a postdoctoral researcher at Scripps. Are you still at Scripps, or have you moved to Columbia?
I am still at Scripps, but I'm starting a faculty position at Columbia in July 2027. Right.
So you'll be an incoming assistant professor at Department of Earth and Environmental Sciences. You have a PhD in physics from University of Oxford. You also are one of the organizers of the last year's 100-hour live stream, this year's 50-hour live stream. And it says, outside, I Googled this. Outside of academia, you're an avid cyclist who enjoys embarking on long-distance cycle tours. But the question is, you like embarking on them. Does that mean you don't like finishing them? You don't like you just like the starting part of it?
The journey's part of the joy. We got to fill a slot here, but if I Yeah, I can show some pictures from Mallorca, where I went recently if we have time. but I can talk about what I actually came on for if you want as well.
Sure. Yeah. No. What do you want to talk about?
Could someone put my slides up briefly? I think. Can you see them? Oh, your slides.
I cannot see them.
Oh dear. Oh wait, I got it. All right. Here we go. All right. So we had a little bit of a gap in the schedule. And so, you've heard us talk on the live stream already about these like OMB rulings. And I thought it would just be worthwhile spending, 10 minutes or so just going through like what these actually are. And why, personally, from my perspective, I'm talking as a citizen now, why I'm worried about this. So one of the things that you're probably sensing from the live stream is we're all scientists, we're all nerds, we're not politicians. And so the first thing I had when I was hearing about this is just like, what is OMB? And I'm pretty sure many of you in the chat have also wondered this at various points. So if you look into the details of it, the OMB stands for the Office of Management and Budget. And as I, a non-politician, understand it, it's basically like the plumbing between the president and the executive branch of the US government and all of these federal agencies like NSF, NOAA, NIH on the health side of things, NASA. And it is basically there to translate presidential priorities into the operational reality of what it is to run a federal agency. So like the monetary side of things and the administrative side of things. And this has always been the case. So OMB has always been like the kind of rule setter for federal agencies on these things. And that's not a problem. You need someone to do it, right? So someone needs to go in and ensure that the finances are all up to the scratch. And, you would pass an audit and you can set performance standards and make sure that no one's doing fraud and things like this. This is important. It's boring plumbing, but someone has to do it. What OMB has traditionally not done is actually set the rules for what the agencies do, what their priorities are. And that's what makes these proposed rules, these are still just proposed and Congress can push back on them, as can we. What makes this so extreme is that it's using this kind of plumbing apparatus between the president and the agencies to take control of what the agencies are actually able to do. And so I'm going to try and just summarize this, what's actually happening here in a couple of key points. And it really builds off this really accessible Substack article by Elizabeth Konecky, who I've probably pronounced her name wrong down here. Sorry, but this is the article that I found really helpful for trying to understand this stuff. And I think what she draws out, she's a really as I understand it, a really well-established person in the NIH space. She draws out this idea that really the rulings touch on every different stage of the life cycle of funding as a scientist. So it touches on the program design. So, agencies like NSF may decide there's some gap in the science that they want filled, and they're going to put out a call and say, we want scientists to try and do that. This affects that aspect of it as well. That's point one. This ruling also affects how grant applications are reviewed and how they're awarded. It affects what you can do with the grants once you actually get them. It places conditions on the grants as well. That's kind of points 3 and 4. It affects and limits the science you can do once the results are ready. So once you've got the grant and you've done the science, it affects what you can do then. And it also gives political appointees like fairly extreme termination power, arbitrary termination power of grants. So I'm going to try and summarize these quickly with a TLDR on each one. Yes, so I put some quotes in here. This is a little bit too long. I put this together like very, very rapidly, but basically, as I was saying, the first thing that happens is maybe NSF decides that there's like a gap in the science, they want to fill it. Normally, they would just do that and then put out a program or a grant opportunity. But now, before they do that, they need to make sure that every program must align with the president's political priorities, not necessarily just the scientific need of the community. And this requirement, as it says, this quote here, is embedded directly in the regulatory text, meaning that science agencies must structure their grant solicitations, so their calls for scientists to submit grants, around the current administration's political agenda rather than around scientific need. So that's not good. It basically means that even if NSF feels like there's a gap that needs to be filled in the science, they need to worry about whether that's going to, bode well with the president. And that's a bad thing, no matter who the president is or who is in the executive branch. These rulings also, actually, I should say as well. So these things I've got in brackets here, these little squiggly S's, these are like my receipts. So we're always meant to show references as scientists, real references. So if you go to the OMB ruling, you can find where the TLDR is kind of coming from by going to like section 200.202. So these rulings also affect how applications are reviewed and they're awarded. And how they're awarded. So typically the way it works is in the US, it's the best idea wins, and whether it's the best idea or not is decided by a group of your peers. So, for example, when I start at Columbia next year, I'll start writing grants to, for example, the NSF, and I'll pitch my idea about like thunderstorms or something in the climate. And people around the US or whatever will read that and decide if it's worth funding. If I make a good case, if they think that it's a viable route forward for the science or not, and that's called peer review. Andy has talked about this in his talk yesterday. And this ruling basically says that rather than peer review being the primary thing that decides whether a grant is awarded or not, it's now political appointees. And so in my mind, this is basically like a doctor having their performance review done by an accountant. Like, it's just completely nonsensical. And I think this is it should be clear to most people that that's just like, if you're really good at your job, your performance review can basically only be done by people who are also good at your job. That's the analogy here. There are also conditions placed on active awards. So there are pretty sweeping restrictions on who you can collaborate with. So lots of people, I've spoken to folks already who have had limits placed on, for example, I spoke to someone on my way down to DC, where I am now today, who works in the health space, but this is also affected by these things preemptively, I guess, basically saying that they were going to have someone from India on their grant as a named collaborator, and now they're being encouraged very strongly not to do that. And so, this just really limits the type of international collaboration that we can pursue as scientists. And this collaboration is really, the lifeblood of science. There's also mandatory bans on grants which explicitly talk about DEIA practices. DEIA, diversity, equality, inclusion, and accessibility. These are really important aspects of our field. The weather and climate space in particular we've been really pushing over the past decade or so to try and make sure that everyone's included in our work, everyone's able to actively participate and not be sidelined or marginalized. And so this is really important to me and really important to many in the field. And now we're really being encouraged not to talk about that in our grants. So that makes me worried. What can you actually do during the grant? So, often one of the big things that you do during the grant is you're doing your science, you're trying to find things out, you're tackling problems, and you go to conferences and you talk to people and you say, like, well, you share preliminary results. So maybe you're halfway to the answer, and then you go to a conference, you tell someone, and they help you find the rest of the answer. That is no longer something that you can easily do anymore under these proposed rulings. So, for example, conference attendance now needs to be basically ticked off by a political appointee. So you can't automatically just go to a conference. Professional memberships. So, for example, being a member of AGU or AMS, people that, if we had the AMS presidents on right at the beginning of the stream, that would also be limited. And also just getting subscriptions to journals. So journals are where we publish all of our scientific work. And this would limit the amount, the scientists' access to everyone else's work. So, you're kind of like flying blind in a sense and not being able to see what other people are doing. So that also worries me. What happens when your results are ready? So I just told you that, when you finish doing your science, you have to tell people about it. Science is not worthwhile unless other people know what you've done. And so the way that we do that is by writing papers and putting them up in journals. And the journals are a business. They have to pay to host a website, to print the thing, to edit it, and so on. and that has some costs associated with it. Normally, those costs are covered by a grant. So you'd write in certain publication costs. Now, and this is an actual quote from the OMB proposed rulings itself, publication costs are unallowable under federal grants. That's the presumptive ruling. There's also limits on how you can publicly communicate your findings. There's some very vague language about politically sensitive topics, and it's implied very strongly that climate change is one of those politically sensitive topics. And finally, a very worrying one is just this kind of extreme termination power that's given to political appointees. So the too long didn't read of this is basically any active grant. So if you get a grant, or if you already have a grant, this grant can now be terminated under this ruling, proposed ruling, at any time with no finding of misconduct. So at any moment, even if you have a grant that's meant to go for like 5 years and you're like 2 years into it, if a political appointee decides it no longer aligns with the agency's priorities, this can now be cut. So I think it's pretty clear that this is a worrying development. And this is why we're so strongly pushing for you to call your representatives, to go to wclivestream.com/act, to write to your representatives, to call them, and to tell them that this is not how science should be. Science is meant to be, in the US, ever since World War II, the contract between the government and the scientists has been, all right, best idea wins. You guys are going to compete for funds. You're going to try and make sure the cream rises to the top. And when you win that money, you can go around and you can actually do your science with it. We're not going to put limits on the science that you do. We're not going to try and guide the results that you get or tell you what you can communicate to the public afterwards. And this just totally rearranges that landscape. So that's all I've got. Andy, I don't know if you wanted to jump in on any of that quickly, but
no, I think you're exactly right. I mean, as I said before you came on, we have this great scientific system. It's the envy of the world.
Mm-hmm.
It's the best ideas prosper, and it's you ask the question, why is the U.S. the leader in AI? Why is the U.S. the leader in drug development, mRNA technology? It's because of our research universities and our research funding infrastructure, and they're just going to take a sledgehammer to it. So I think this is deeply problematic for people that are interested in the U.S. maintaining scientific leadership. I mean, we're going to be a country without scientists, if you sort of take this down the road. So I think it's extremely worrying also. And I feel very sorry for you. I mean, I can retire. I've been at A&M so long, I can literally retire. But people like you that are starting out, it's going to be a tough road. And I see why people like you are leaving science, which is a real tragedy. I mean, we've trained these people up to be experts and then they just leave.
Yeah. One of the things I would say, just if I can, is that, so you mentioned I was lucky enough to do my PhD at Oxford. It's was sometimes called one of the best universities in the world. I finished my PhD, and the first thing people told me is that if you want to make the most of your career in science, you go to the US. That was the line, and I think it was correct, and that's why I came over for my postdoc. Did my postdoc at GFDL, Suki Minabe's lab, working with great people. While I was there, people, one of my best friend across the hall got fired, and suddenly things are like falling down around you. Robert Pincus was talking earlier about how a very, very promising scientist who I know did excellent work during their PhD and couldn't get the postdoc that they deserved, basically, and now are in France. And so that's certainly not the country I chose, and I think that it's not the country we have to have. It's not this certainly not what has to. This is not the way it has to be. And so, not to be a broken record, but go to the link and phone people.
I think there's a real echo here of 1930s Germany. So, in the early 20th century, Germany had the premier university system full of, the giants of physics. And when the Nazis took over in the 30s, they basically went in there and interfered with their research system in not exactly the same way, but in similar ways to kind of this OMB directives, and people left, and the U.S. was the recipient of that. And I think we're dismantling our higher education system in a way that's very similar to that. And I think the U.S. is going to suffer at the end of the 21st century. If people look back and say, how did China overtake the U.S. in sort of global leadership and all these things? You could look at, if we continue down this path, that's going to be one of the prime drivers, I think.
Yeah. Well,
so call your reps.
Call your reps. I'm gonna as soon as I'm off your screen, I'm going straight on the phone. I'm gonna phone them. If I can make that presentation in 20 minutes, you can phone your representatives.
Right. Definitely do it. And I think we need to move on. We're a bit behind schedule. So thank you, Andrew. That was really great. So I would like to welcome our next speaker, someone I've known for years, another University of Washington person who's talking about marine cloud brightening, because we just had Becky Alexander probably about 45 minutes ago. So Robert Wood is a professor of atmospheric and climate science at the University of Washington. He earned his bachelor's and Ph.D. from Cambridge in atmospheric physics. His research focuses on processes of controlling clouds and their roles in climate variability. And he serves as lead scientist for the Marine Cloud Brightening Project, investigating the potential of seeding marine clouds to cool the Earth. So good to see you again, Rob. It's been a while, and I will turn it over to you. You're muted. Good.
Okay, thanks, Andrew. Yeah, thanks for the introduction. That's very kind. I'd like to speak a little bit about a project that I've been involved with for quite a number of years, focusing on the idea of maybe providing additional cooling which could be used in case the global warming from greenhouse gases gets way out of control. It's an idea we're really not advocating for using it, but understanding whether it's even possible is really where I'm coming from here, and really from a physics scientific perspective. You can see the Earth there in the blue marble. That's a classic picture taken with taxpayer-funded money to bring us pictures of the Earth. Now we use those for weather and climate research routinely. So you can see there's a lot of clouds there. The Earth's covered by about 2/3 of the globe is covered with clouds. Many of them are low down in the atmosphere and can be affected by atmospheric aerosols, and I'll talk more about that as we move forward. So this idea of solar climate intervention, sometimes called geoengineering, has been around for a while. There are probably two main methods that are being mostly focused upon, which is increasing the aerosols in the stratosphere, rather like a volcano does, and that has been shown to cool Earth. The other one, which is being actively researched, is the idea of adding salt particles from the ocean, so natural salt particles, making them very small and injecting them into low clouds over the oceans to try and make those brighter. And that's what I'll be talking about today. So here the idea is not that we would use sunlight reflection, as we sometimes refer to it there, as the only means of tackling climate change, not at all. In fact, this really would have to work in conjunction with efforts to reduce emissions, not only reduce them significantly, but also potentially remove carbon dioxide from the atmosphere as well. Because if we just stop emitting at this point, so that orange curve in the middle, if we've got very extremely aggressive greenhouse gas emission reductions, which we don't yet have, but we may be moving towards that. Even with those, we're going to, if you stop emitting completely, the temperature won't go down again for a long time. It will stay high. So if that high temperature is causing a lot of problems and a lot of economic and ecosystem disasters, then we may want to look at means to cool it further. And that's the idea of adding particles to clouds to make them more reflective. This image here is an image of ship tracks off the west coast of the US. That's all low clouds. You can see up here the state of Washington, Oregon, and California, so a pretty big area. Each one of these tracks in these marine clouds, which is noticeably brighter, it's reflecting more sunlight back to space, is caused by a single container ship, which is pretty remarkable when you think about how long that is. It's hundreds of miles long, reflecting a lot of additional radiation back to space. That sort of gave people the idea. These have been known since we started looking at the Earth from space in 1960 or so. These gave people the idea that, well, what about if we did that deliberately? Could we make those clouds a bit brighter, reflect more sunlight, and therefore cool the planet? So the idea would be not to do that with sulfur from container ships, which have significant health impacts, but to do that with salt from the ocean, so a benign aerosol. The idea there is it's fairly simple. It's not to make new clouds, although that can actually occur, but it's mainly to change the ones that are there already. So on the left, the number of droplets in that cloud is relatively low. That's typical of the marine areas where there's not a lot of aerosol particles going into clouds. If you can increase the number of those drops, even if you have exactly the same cloud, the same surface condensate amount, same liquid in the cloud, you would make more particles, and each one of those would be smaller, and the overall surface area of those particles would be increased. And that itself is all you would need to make that cloud reflect a little bit more sunlight back to space. So that's the nugget, the idea, but the idea would be to introduce these salt particles into clouds. Now, how we know we've been doing this already, not with salt, but with actual anthropogenic pollutants, primarily sulfur dioxide gas. And this chart shows basically modeling efforts that to have certain climate forcing agents. So greenhouse gases is the red one. That's the primary warming agent. This is a simulation with the red curve simulation that with just greenhouse gases. Now you can see that the total warming, which is the black dots, hasn't kept up with that. And that's because we think there's been a significant additional forcing agent in the other direction from aerosol particles, which brighten the clouds, reduce sunlight coming into the climate system by reflecting more back to space. And so through the course of industrialization, and particularly in the late 20th century, aerosols have also increased a lot. And they've stopped the warming being as strong as it is. So there's a significant aerosol cloud radiative forcing from these aerosols already. And these are from anthropogenic aerosols. So nobody's doing this deliberately, but it's a side product of burning fossil fuels, which contains significant amounts of sulfur. So the idea with marine cloud brightening, as I mentioned, it would be to put a lot of ships over the ocean. Essentially, you would create a whole fleet of, if this were to be done on the large scale, thousands of ships, each one spraying a huge number of particles per second. Still, the amount of salt that would need to be added is actually not as much as is already in the atmosphere, because this would make the salt particles smaller. So we'd have to have a special spray system to create small, very small particles. Most sea salt in the atmosphere is actually rather larger particles. And so by making them a lot smaller, you can actually brighten the clouds without adding a lot of extra salt mass. The low clouds over the oceans occur pretty much everywhere, but they're concentrated in certain areas. This is showing the concentration, the frequency of occurrence, if you like, the coverage of the particular stratiform cloud that's very amenable to this brightening, where we see most of the ship tracks is in these stratocumulus clouds. So they can cover regions up to over 50% of the mid-latitudes, for example, even higher in some other areas in the eastern tropical oceans. So there's a lot of them, about 20% coverage of the globe. And so the idea would be, if you can brighten each one of those a little bit, you could actually get significant cooling. We can use climate models to get at this. This is 3 climate models. The top panel here is showing the temperature change from the present day to the later part of the middle part of the 21st century. So the temperature change from 2025 to 2075. So this is what happens if we just let things go with a really fairly modest or mid-range greenhouse gas scenario. So not excessively high greenhouse gases, but not low greenhouse gases, perhaps business as usual, as we might want to call it. You can see that these 3 climate models are warming the planet considerably over that period, right? Especially over land, especially in the Northern Hemisphere, especially in the Arctic and Antarctic. The warmings are different in the different models, but when we add marine cloud brightening here, what we're doing is injecting salt into the regions with the red boxes. So these are all in the mid-latitudes. And this is showing what the pattern would be like if we inject a significant amount of sea salt to offset the warming from greenhouse gases over that period. And you can see that in each of these models, there's significantly reduced warming. Now, it's not uniform. It's not the same everywhere, but neither is the warming either. So, we're not to the point where we can, make the warming pattern completely go away from greenhouse gas, but there is a sense that you can offset by choosing the locations wisely. Now, if climate models were enough, we would be, maybe we'd be already kind of thinking about this as feasible, but we don't really know that the climate model clouds are all that accurate. It's been a problem over a long time. They have improved a lot, and so I would, with a lot of funding from taxpayers and a lot of work that's gone into improving these models so that they're much better than they used to be, there's still a significant problem with clouds, and it can be sort of illustrated by this image here. This is an image from a very high resolution numerical model called a large eddy simulation. This is a cloud deck, and you can see precipitation as the blue falling from this cloud, and you can see cooling at the surface here from the precipitation evaporating. But the point here I want to make is that this all fits in one climate model grid box. So when we model the climate, the boxes we use are quite large, but they have to be in order to run for 50, 100 years. So what we find by doing high resolution numerical modeling is actually that not all clouds brighten in the way that they might do, what you might think they would. And in particular, this is because in addition to this just changing the cloud droplet size, that's not the only thing that happens. When you reduce the droplet size, you also reduce the chance of it making rain. And so you can actually, by suppressing the precipitation, by adding the aerosols, you can then change the cloud dynamics and the cloud macro structure in a way that could increase further the brightening that you get, but it can actually offset a significant amount of brightening. And we're doing a lot of work with numerical models, these high resolution models, and trying to reconcile those with our climate models to understand, will the overall effect of adding particles to the atmosphere result in brightening, or will it actually result in relatively weak brightening, or will it actually end up with no brightening? We don't really fundamentally know that question, in the same way that we don't fully understand the aerosol forcing of climate now from anthropogenic aerosols. And so there's a lot of work to be done in this area. We're going to be able to show any more of that today, but I just wanted to say that, to improve these models, we also need observations. Observations from satellites are very important, and we've done a lot of work with that. But when you get down to these small scale effects of clouds, changing the amount of mixing that a cloud has with its environment, when you add particles in to suppress precipitation, we need to know that on a rather small scale. And so the idea of doing field experiments with a spray system that can deliver some of these particles to the atmosphere really provides a new way of looking at looking at cloud physics. Essentially, it's a sort of more of a control experiment than we're used to doing. What we normally do is fly around, find some pollution, and try to contrast it with a non-polluted environment. But there's a lot of challenge with that, because pollution is quite a large scale, and it's hard to get good controls. So the idea here is that we could turn on and off a brightening system, a spray system, and then go and monitor it with aircraft and try to prove whether our small scale, our high resolution models are doing the right thing. So there's a lot of work to be done there. And we would like to start off by just seeing if we can actually create a spray of particles that is able to, that is of sufficient number, concentration, and size to be able to brighten the clouds. And so I'd just like to end then with just a summary. Basically, marine cloud brightening is a potential emerging tool for managing present and future climate. It's certainly a long way from being ready for being deployed. It's not being deployed at the moment. There's none of this is actually happening yet. But there's some good evidence, and there's evidence I didn't show, but that aerosols are affecting clouds, and ship tracks are brightening the planet. And we may have already done an experiment where we reduced the sulfur in shipping fuel, and it's making the Earth a little bit darker already in 2020. But there's a lot more we need to know scientifically, technologically, and also governance. There's a lot of governance is needed in this area, and we hope the federal government here would be able to play a role in providing adequate guidelines and governance for doing science in this area and going forward, so we can evaluate fully whether this could be used as a potential means for cooling the climate, or whether it's really off the table. So I'd like to thank everyone for their attention, and I'm happy to take any questions. Thanks.
Thanks, Rob. That was really interesting. I'll just ask the producers, if you see any good questions in the chat, put them up. But until then, I've got a lot of questions. Yeah. So, one of the big issues with stratospheric aerosol injection is that you have all of these sort of knock-on issues about it changes the ratio of direct and diffuse radiation. It changes the color of the sky. It can change precipitation patterns globally. I'm guessing that you'll have some of the same issues, like you'll be changing the precipitation patterns. Have you looked at the impact on things other than temperature?
Yeah, in fact, the image I showed where we introduce some particles into a climate model in the mid latitudes and get relatively uniform cooling, that's a relatively new development. Previously, people were talking about trying to do marine cloud brightening in the tropics, in the subtropical regions where there are a lot of low clouds. But if you do that, it turns out that you have a big effect on the ENSO, on El Nino,
right,
in ways that could be negative. And so there's been already a move away from, and that's not just temperature that's affected; it's the precipitation that comes along with El Nino. So yeah, there are definitely a lot of potential for side effects that would need to be explored, and that includes everything from changing the brightness, changing fisheries. Are there effects on fisheries? Are there effects on ecosystems? Yeah, there's a long way to go there, and it may well be that those things completely render these kind of climate interventions to be not usable.
I mean, my reaction would be, this is why we need to do the research.
Yeah, I think that's,
if you don't do the research, then you don't know what the trade-offs are. And
one of the problems is that these effects probably do cool. Certainly, the stratospheric aerosol could be made to cool. But unless in some future date, if it becomes an emergency, we haven't done the research, then we won't know what these side effects will be. So we need to do that. Yeah.
So I have one more question for you, then we'll have to move on. But I really want your opinion about kind of the public reaction to this. I don't do geoengineering, but I'm in atmospheric science. So I get emails and letters from crazy people who say 5G towers are affecting the climate, and they're spraying stuff out of airliners. I mean, what's kind of your reaction to sort of the public's reaction to this?
I do think that over history there's been a long history of either people sort of selling the idea of changing the climate, changing the weather, bringing on rain making, and people are misled by it because there have been people that do misleading, they deliberately obfuscate the issues. But I think that I think it's important to stress that none of this is actually happening now. So all those ship trucks over the ocean are caused by inadvertent ships.
You say it's not happening now, but you're part of it. That's exactly what someone who's doing it now would say.
Well, okay. Well, therefore, I would say that we need to monitor it better. Then, if there are people going about doing that, then it's improve satellite measurements. These are the same things we need to understand our clouds and aerosols in general. But yeah, I think we need more of that, and that requires federal funding. Yeah.
Yeah, no, that's right. Well, that's a great segue. So thank you, Rob. That was a fantastic talk. I really appreciate you coming. And let me just tell you why we're here before I introduce the next speaker. We're here because science is one of the crown jewels of the U.S. public institutions. And the cuts to science that have been proposed would decimate it and really turn the U.S. into a country that doesn't lead in science. In fact, sort of a science-free country. That would be bad. Science is good. Science is one of the reasons why the U.S. economy is what it is. It's one of the reasons why the world is what it's like. And, we really need to fund science. It's really this force for good in the world. And so call your representative. It takes a few minutes. They're not going to get mad at you. They're paid to be polite. They will politely listen to you saying we should fully fund NASA, NOAA, don't break up NCAR, reject the OMB rules that would hamstring science. So just do it now. I'm old, but the young people watching this, you've got a lot of skin in the game, and you're going to have to live with the decisions that are made. And if they really destroy science, it's going to be decades before they can rebuild it. So this really will affect your life. You, again, not to repeat this too many times, but you have skin in the game. So take action, call, go to that link. All right. Let me introduce our next speaker. Lucas Vargas Zeppetello is an assistant professor in Department of Environmental Science, Policy and Management at UC Berkeley. where he leads the Plant, Land, Atmosphere Climate Exchange Lab. He completed his graduate studies at University of Washington, another Washington person, and later served as a postdoctoral fellow at Harvard. His research explores relationships between water, energy, and carbon at the Earth's surface. And he recently won the American Geophysical Union's Holton Award. I hope all of that's right, Lucas. I think it is.
Yep.
But I didn't check with you in advance. But anyway, I know Lucas. I worked with him on our response to DOA report. It's a real pleasure, and I'm really looking forward to hearing what you have to say.
Awesome. Thanks, Andy. Yeah, that was all right. I don't put stuff on my website to throw people off the scent. Before I get started, I'm going to talk about ecosystems and temperature. It was good to see folks from the UW all morning. Really like seeing this community come together. And just again, speaking for myself, the federal funding has been so important in my journey through science. I could not have done the things I was able to do without support from the federal government. And I am now in a different role and am trying to shepherd students through Ph.D. programs. And that has even more deepened my appreciation for what funding and public investment in science is really able to do. So I would just further encourage people to call, to do whatever you can to get your friends on board, because this is a really vital enterprise. And I don't know what happens if we lose our commitment to that, but I think it's important to demonstrate that there's a lot of people who are very committed to this, and there's really good reasons why we should continue this pursuit. Shifting gears to climate stuff, I'm going to talk about ecosystems and temperature here. And I think it was nice to hear Rob talk about some possible unintended consequences of marine cloud brightening on marine ecosystems. My focus is a little bit more on the land surface, but I think it's really important to understand these interactions between climate and ecosystems. And so I'm going to try to get through today some emergent properties of ecosystems and how they depend on temperature, humidity, and water stress. And there's a couple that I'll try to get to. One is this relationship between surface conductance and vapor pressure deficit, which is basically a way of understanding how efficiently ecosystems transmit water from the land surface to the atmosphere. The second is trying to understand how crop yields depend on temperature. So this is a very famous sort of relationship between only American and only major crop yields and temperature, but basically saying that once crops are exposed to temperatures about roughly 30 degrees Celsius, there's some really consequential impacts, and in particular, you have major yield losses if you increase the temperature, which is obviously a problem for climate change. And then the last thing is sort of extending some of that work into natural ecosystems and trying to understand why ecosystems have these observed optimum temperatures, where if you go out in the field and you measure the amount of carbon drawn down by a particular ecosystem, it displays this sort of optimum behavior where there's a peak value somewhere around 20 degrees Celsius, above which ecosystems stop pulling down atmospheric CO2. So why do I care about this? I am an atmospheric scientist. I'm a climate person. I'm not an ecosystem scientist, although I've really enjoyed my interactions over the last couple of years with folks from all around the country. But I think it's really important to understand that there's a really considerable spread in the anthropogenic CO2 emissions, and not the emissions, in the atmospheric concentrations if you force contemporary climate models with historical emissions. And this spread, which you can see here, goes from about 425 to all the way down to 325 in 2010 if you force the models with historical emissions. Most of that is due to uncertainty in the land surface carbon sink. So understanding why ecosystems have different amounts of carbon drawdown and how that depends and interacts with the climate system is really important if we're going to try to simulate the future, particularly if we include these carbon cycle feedbacks. And this is just some extra information. This is roughly the same as the aerosol climate interactions if you write it down in terms of a radiative forcing. So I think aerosol cloud interactions may have a new competitor for the most important important sort of radiative feedback uncertainty associated with the land surface carbon sink. And so this is my argument that understanding ecosystem responses to climate change are vital for predicting the future. The other thing about land surface climate modeling is that there are these embedded temperature parameterizations that are all over the place. So this is one example from a motivating feature behind sort of the dominant way of understanding the land surface carbon sink, which is the Farquhar model for photosynthesis. You can see this very strong nonlinear dependency on temperature. This is also embedded in the way that we understand plant stomata, which is an entirely different process, but you can see here again, there's this strong nonlinearity that controls the rate at which water and carbon are exchanged across the leaf atmosphere interface. And again, these are parameterized into virtually every climate model that is used today. And I think these things were sort of lifted from the botany literature and put into these models before we really understood how the appropriate scaling between what's happening at the cellular or the molecular level and all the way out to an ecosystem property. So the other important thing about that is that these parameterizations have consequences, and particularly in the context of a lot of uncertainty around not so much temperature. The temperature projections are pretty solid, which I'm showing here in the panel on the left, but really in terms of the precipitation projections. So we really have a much better clue as to what's happening with sort of the spatial pattern of global warming than we do with precipitation patterns. And what I'm showing here is I just picked the local trend at each place in space that's the biggest in all the CMIP-SIPS models over the next century, and then I picked the smallest one in the bottom panel. And what this is basically showing is that for most, let's say, crop-producing regions, you have a pretty substantial spread in the precip trends over the next 100 years, ranging from negative 40% over 100 years to plus 40%, which is, you can imagine how consequential that would be for ecosystems. So just a quick primer on ecosystem scale surface conductance. This is a parameter in models that controls the efficacy with which carbon and CO2 are exchanged across ecosystems. There's a lot that could control this, but one of the ways that people have gone about this in the past is they take observations from eddy covariance towers, they solve for the surface conductance, and then they can say that they use flux tower measurements to calculate surface conductance, which is shown right here. So basically the argument here is that plants respond to very dry air by proactively closing up their stomata to save water, essentially. And that has downstream consequences on their ability to pull CO2 down from the atmosphere. So what I did with Kagan McCall, and this was some work I did during my postdoc, was look at non-vegetated salt flats to basically say, okay, here's an environment where there's not a stomata in sight. Let's see what the eddy covariance data looked at and look for this signature of stomatal conductance. And indeed, we were able to recover this relationship in a non-vegetated environment, which suggests that instead of stomata being responsible for this nonlinear relationship between surface conductance and vapor pressure deficit, instead, this is a feature of land atmosphere coupling. Basically, when the soil is dry, it tends to mirror the dry air, and which is ultimately responsible for this observed variation. So I think that was a really interesting sort of point of entry into understanding these emergent variations between environmental variations. I'm going to skip over this for now. And then I got really interested in trying to use this same approach to understand the relationship between agricultural yields and temperature. And this was work that I did with Peter Hybers and John Proctor. John especially was instrumental in this stuff because he got in my ear very quickly when I was a postdoc. And again, this is just an example of how funding really frees you up to pursue the things you want to pursue. So I would not have been able to do this were it not for some pretty unrestricted funding of the kind that I think should be offered to people pursuing graduate degrees. So that's just another little plug here. But what we were able to do here is use a model that I had developed to try to understand soil moisture trends, which are pictured over here on the left from satellite data and in situ observations. And then we used the same model, which importantly had no limitation of evapotranspiration at high temperatures. So there was nothing in this model saying that when you have a high temperature, you have to shut down your, basically plant development. And we were able to reproduce not only the soil moisture trends, but also historical variations in yield. I did not expect this to work. I was really encouraged by this result because the model basically only takes time series of precipitation and solar radiation as inputs. And so the fact that you were able to do this was very exciting to me. And we were able to use this to try to understand some of these relationships between temperature and yield anomalies, both in rain-fed observations, which I'm showing on the left, which have no irrigation, and then fields that are equipped for irrigation, which I'm showing on the right. And the important thing here is that for both maize and soy, when you look at the yield anomalies in places that have no irrigation, you see this really steep fallout at high temperatures. In irrigated fields, it doesn't really exist. The response is a lot more muted. There's not as much there when you think about these sort of extremely consequential temperature events. And we were able to reproduce this in the model. So I'm skipping through a bunch of stuff. But the point here is that a model that knows absolutely nothing about how temperatures impact crops. There's no phenology. There's no submodel conductance dependence on temperature. There's no kinematics. There's no molecular stuff here. We were able to reproduce this just by considering the fundamental coupling between dry soils and high temperatures, both in irrigated and when we did some irrigation experiments with the model, which I thought was really nice. And just to wrap up here, we tried to build this out even further to understand not just agricultural yields, but for ecosystem productivity in general. And this is some new stuff that I've been really, again, privileged to have the funding to work on with some new collaborators, Todd Dawson, who's here at Berkeley, with Missy Holbrook and Abby Swan, who have just been fantastic collaborators. But trying to move from managed ecosystems in agriculture out to understanding natural ecosystems. And again, we see this really clear sort of separation in terms of these relationships between temperature is on the left and vapor pressure deficit is on the right. It all depends on how much water you have available to your ecosystem. So I'm basically showing everything here stratified by the background evaporative fraction, which is a metric for water availability at an ecosystem scale. But you can see something that really surprised me, frankly, was that when plants are exposed to very high temperature, if they've got water, they just keep going. They're able to pull down more carbon. It's usually sunny when these days are happening. If they have water, they're perfectly happy to keep pulling down CO2 if they have access to the liquid water. It's only when you start to restrict their access to liquid water that we see these sort of consequential impacts that drive the overall behavior and the overall declines at very high temperatures. And the same is true when you look at it from a VPD perspective. I'm not going to go all the way through this, but there's a model that I developed that has a coupled land and atmosphere, which is important to understand this emergent behavior. But the thing that I added here that I think is really important is that there's all these parameterizations for photosynthesis that are sort of based on the sort of granddaddy Farquhar model, which was a fantastic model to understand photosynthesis. But in the original model, like I said before, there's these nonlinear temperature parameterizations that are all over the place in the sort of fundamental equations for carbon drawdown that are now being applied at the ecosystem scale. So there's this behavior that's sort of baked into the model, but it's not clear to what extent these relationships scale all the way up to an ecosystem scale. So what I did was basically built the same model, but took all the temperature parameterizations out, which is a really fun exercise. And I recommend anyone who's remotely interested in this stuff to go read this 1980 paper, because it's just a fantastic example of a very clear model that really boils down something as complex as photosynthesis to just a couple equations. But I took out all these temperature parameterizations, and when you do that, you can still get this observed behavior where you see this sort of separation based on evaporative fraction that ultimately determines the nonlinear relationship, both between vapor pressure deficit and temperature and the ecosystem scale productivity. So we were able to reproduce some of the salient features of the observations, even without these highly nonlinear temperature parameterizations that are baked into the equations for photosynthesis in contemporary climate models. So I'll end just by saying that a lot of these emergent parameterizations are, I would argue, based really on the soil water state of the land surface. And that's really important because, as I said before, we don't have as good of an idea about rainfall and soil moisture forecasts and climate models as we do about temperature. So it sort of changes the texture of the story from this is going to be really consequential to we actually have very little predictive power. And I would say similar to what Rob said at the end of his talk, this is an example of why we're not done with this problem. We actually need more science to be able to develop these water forecasts, because otherwise I would argue that our capacity to understand our agricultural system, our managed landscapes, and our natural ecosystems are a little bit out to lunch if we don't have better water-based forecasting. So again, just an example of how much science remains to be done on this. We've seen this clear connection at a global scale between the atmospheric CO2 growth rate and water stored at the land surface. And I think this is just an important problem that's going to keep going. So I'll end it here, and I'm happy to take questions if I didn't blow through my time.
Thanks a lot, Lucas. That was really interesting. I guess the question I have for you is, what's the implication of this for ecosystems? Like, does this mean that if we just irrigate enough, then plants won't have a problem?
So I don't know. The main thing that I would be worried about answering yes is that the extreme events are still complicated. And you can push plants to a point, even if they have enough water, where they will die, right? If you put an irrigated plant in an oven, it doesn't really matter what you do as terms of the water stress. So I think there's a lot left to learn there. What I would say is that, and we've started to look at this in the observations, it is very difficult to get leaf temperatures high enough to experience tissue damage or xylem cavitation under the contemporary climate. Whether that will change in the future is an open question, but it's hard to overstate how important having water is for these plants. And that was something I was really, really surprised by. That having liquid water is just a complete sea change. You can see it so clearly in the satellite observations. The irrigated lands just sing out as completely different from their non-irrigated neighbors.
Yeah, what I didn't understand. I won't keep talking. I'll ask the question that's on the bottom screen. Is it easier for plants to cope with, adjust to excess precipitation than excess heat?
That's a great question. Excess precipitation is actually a big problem for a lot of rain-fed agriculture. It makes a big problem for microbial infections that plants can get. So there's all kinds of issues with excess precipitation as well, which is why, especially in tropical countries that have really, really large extreme precip events, this is not just add water and everything is going to be fine. Excess heat, I would say, can be mitigated by irrigation, similar to what Andy said, but excess precipitation, it's harder to figure out an intervention strategy because I don't know how well we're able to mitigate that.
All right, Lucas. Well, thank you very much. I think we're going to move on now. That was a great talk, and we appreciate you contributing.
Yeah, thanks everybody for organizing. I really appreciate it.
All right, so thanks for joining us in hour 24. So they've been on 24 hours. We're halfway or 2/3 of the way through, or no, halfway, whatever it is, almost halfway, and we have 26 hours to go. And we've the great talks keep coming, so stay tuned. But before we introduce the next speaker, let me just talk about why we're here. Science is this tremendous public institution. It betters all of our lives. It's responsible for, lots of the great things we have in life, as well as some of the not so great things. But let's focus on the great things. And we really rely on the weather. We rely on the weather, the climate, and weather and climate science to keep us alive. And so the current administration's efforts to slash the budget is going to really hurt the U.S. We're not going to be a leader scientifically, and we're certainly not going to be a leader in many of the fields that, again, we rely on for our economy and our public health and all these other things. And other countries are going to take up the mantle, and we're going to end up being a diminished country at the end of this century if we go down this road. So we want to not go down the road. So call your representative at the link below and tell them to fund science. All right, let's move on to our next speaker. Tyler Fenske is an early career scientist based in Houston, where he leverages his background in atmospheric science to contribute to fire weather forecasting and air pollution exposure. He holds a BS in meteorology from Texas A&M. Great to see one of our graduates here, and an MS in atmospheric science from Miami. where his graduate research focused on low-frequency internal climate variability. Beyond his professional work, he enjoys applying statistical programming skills to evaluate ice hockey player performance. So that sounds good, and loves to traveling to seek out the world's best roller coasters. So welcome, Tyler.
Yeah, thank you, Dr. Dessler, for the great intro. And I'm Tyler, and I'm excited to be here today to talk to you about extreme heat and smoke exposures in California prisons. So this is we're not really doing anything too terribly inventive with some of the climate analysis and modeling work we're doing here. But it's applying it to a field that is really quite understudied. That's one of our main motivations here, is that environmental exposures and their associated health risks for people living and working in prisons are extremely understudied. There was a literature review paper published earlier this year that focused on this, and there are, I believe, only 6 quantitative papers that link prisons, people in prisons, and climate risks. So, there's a lot of work to do here still. These populations are often at higher risk for extreme and prolonged exposure to heat and smoke. There's a fantastic Reuters article called Scorching Cells. I've got the link here, but if you just look up Reuters Scorching Cells, it'll show up. And it covers a lot of the heat-related issues that incarcerated people face. One of the big ones is that, as it makes sense, most prisons are basically just concrete boxes. The prisons and the cells themselves are just concrete boxes. And so you get these mini, it's the same thing as the urban heat island effect. You get a miniature version of that within the cell that causes these heat issues to be even more exacerbated in what's supposed to be the safest place for them to be. So a lot of this work is really aiming to bring attention to these populations regarding climate change research and how we can plan and mitigate any of the health risks that arise from this. So just as some background, we're focusing specifically on California prisons. You might see them referred to here as carceral facilities, but prisons is a bit of a simpler term for that. But these are all sorts of correctional institutions that range from city level, state level, county level, federal level, any kind of carceral facility. And so we've got 410 of these locations in California that we're looking at. There are about 200,000 people who live and or work in these prisons. And this doesn't just include incarcerated people as well. It includes employees of the prisons. Those are also a factor here. And so, 200,000 is a fairly substantial amount of people, especially when you're looking at climate risks like this. So it's while we're studying, we need to make sure that they're treated humanely and are in an environment where they can be safe and not have to deal with unnecessary health risks. So we approached this with a whole bunch of data with 6 different sources. There's a lot of info on this that is not super important to this talk. If you're more into the technical aspect, then this is a good slide for you to pay attention to. But what we're really focused on is pulling temperature from ERA 5 land reanalysis. And then we also have access to, well, it's publicly available, but there's a CMIP6 LOCA2 climate modeling data set available through the CalAdapt analytics engine, which has a subset of CMIP6 that has been downscaled to 3 kilometers in spatial resolution over California. And so we're using that to really get a very high resolution and specific location data for the prisons we're looking at. Everything you're going to see is daily maximum temperature. Sometimes it's aggregated to monthly or yearly data, but we're looking at these maximum temperatures. So this is the hottest temperature for each day for the most part. We're also looking at some smoke data, mostly through PM 2.5. We have different modeling output that looks into that. And then some other various sources of data that we're using, but I'll skip over this for now. So we'll dive into some historical results. So this map on the right is just looking basically at over the last 25 or so years, what the daily average maximum temperature linear trend is at each of these prisons. So what you'll notice is the scale starts at 0 and the entire map is red, which means every single prison in California over the last 25 years has gotten hotter. And in some locations, there is some geographic variability here. Along the coast, you'd expect it to be a smaller increase, which it is for the most part. You're looking at maybe 1 degree Celsius, 1.5 degrees Celsius. But when you get further into the valley and inland and in some of the more desert areas of California, you're looking at anywhere from 2 to even 3 degrees Celsius of warming over the last 25 years, which is very significant. And then it's not super easy to see because we're not zoomed in on the 2 urban areas, but you do see a little bit of an urban heat island effect in the 2 main urban centers in the Bay Area and the LA area especially. So, these are historical results with reanalysis. So we're already seeing this change happening. We can look at this also with the average days with heat exposure, where basically this is the number of days where the daily maximum temperature is over 82 degrees Fahrenheit. So again, you see quite a bit of geographic variability where some points along the coast have very little. Very few days that meet this threshold. And then as you get further inland, and especially in the southern regions of California, you get upwards of 200 days where this threshold's met. We chose this threshold as this is based on the Cal-OSHA standards, which is just California's version of OSHA. Anytime a facility that people are working at meets this threshold, then they're required to provide some ways for employees to cool down, basically like a cooling room or provide extra cool water or something like that. But carceral facilities, the prisons are exempt from this rule, so this doesn't apply to them. We've also tried this with this is just temperature. We've tried this with other metrics that include moisture, because humidity is a big part in how the temperature feels. Living in Houston, 90 degrees here feels a lot different than it does in some of the drier parts of the country, like Denver or Phoenix. 90 degrees can be very different depending on how humid it is and what part of the country you're in. So we tried to account for that with some other metrics like what bulk globe temperature and things that are accounting for this, and you get pretty qualitatively similar results. The numbers are obviously going to be different, but the conclusions you're going to draw are going to be pretty similar. So we did account for that. And then when you're looking at smoke for historical results, we have a couple data sets that we're trying to isolate this to. One of these is a modeling data set, and the other is just general smoke exposure. And both show, they basically show over these 2 periods, which are different, that for the most part, your smoke exposure is going to be a lot higher in Northern California than it is in Southern California. The time periods obviously are important here. As in the last few years, we've seen a lot more of these fires in the LA and Southern California region pop up. And that'll get reflected in some of our projected data that we'll show in a bit. But for the most part, we're mostly seeing a lot of the smoke exposure historically be in the northern region, which tracks with what we would expect with where most of the forests and wildfires occur in the state. So we're moving on to the projected results. There's a lot to unpack here, but I'll try to summarize it as best as I can and as quickly as I can. We're looking at 3 different scenarios. I know there's been a lot of debate about these scenarios with the way CMIP7 has changed the scenarios, but we're effectively from left to right looking at a best case to worst case scenario in terms of how we're mitigating warming. And then the top is a slightly different version. These are taking the means of all these 60, 70 different climate models, simulations that we've got. The top is one that kind of weights those simulations based on how well they perform compared to observations, and the bottom is just a simple average. So the top is actually you're going to have a little bit smaller values than you will with the bottom. But again, the qualitative conclusions you draw from this are going to be pretty much the same. So you can see in this worst case scenario, all across the state, you're looking at 5+ degrees of warming Celsius at every location, and upwards of 7 to 8 degrees of warming. And even in your best case, you're still getting 2 to 3 more degrees of warming on top of what we were seeing before from at every location. So this is very significant. This is going to push some of those thresholds that we talked about earlier, the 82 degrees upwards, to where it's happening almost every day of the year at some locations. And so this is very much, it's already a concern, and it's just going to continue to get worse in these facilities. For the projected results on smoke exposure, these need to be taken with a big grain of salt. A lot of the models have some serious issues with how they're used in wildfire modeling that are being worked on, but data we've got is going to reflect these issues. And then there's just a lot of assumptions built into the methods we used here. So this is still a good first idea, first stab at trying to get projected smoke results. But there's a lot more to do here. One of the things that really jumped out here with looking at these climate projections for potential smoke exposure is the jump in the Southern California and LA regions that you see. So this looks a lot more like if we had included in that historical slide, if we had included the last couple of years, if we had that data for this, I think you would have seen more of this reflected as well. So that's something that's interesting. It's maybe a quick way to kind of confirm that the models are seeing something that we're actually seeing in the real world too. But again, generally you're seeing pretty much all red here, some white where there's no growth. And so again, all over the state for the most part, you're seeing more likelihood of smoke exposure in California facilities. Moving forward. All of this data was also run through another teams that helped on this project. They had a health risk model that basically took these results, the smoke exposure and the heat exposure, and ran it through a health model that told us basically how much more likely it was that people would experience heat stress illness, and then also lung cancer, heart disease, a lot of these common things. And so this risk ratio is basically how much more likely you are, any given person is, to experience heat stress illness. So you're seeing all over the state, around two times more likely. In some of these areas where, especially in Southern California and the LA area, you're seeing upwards of 6 times more likely for heat stress illness. So this is very significant. It's something that definitely needs to be accounted for in regulation and policy, which it really is not right now. So on to the conclusions. Like I said, there's been very little scientific focus on prisons and their population's climate risks, and we're aiming to kind of fill a bit of that void with this work. A lot of our results are showing pretty geographically consistent increases in exposure to both extreme heat and smoke. We're seeing that already happening in the last 25 years or so. And that's expected to continue as we look into the projected data at these carceral study locations. And then when we run all of this exposure data through the health risk model, we're seeing very heightened risks for heat stress illness, cardiovascular disease, and lung cancer as a result of these exposures. So understanding these exposures is crucial for both facility planning and mitigation in order to reduce health burdens as well. And I think that I'll end it there. So thank you.
Oh, there I am. Thank you, Tyler. That was really interesting. I've been following the plight of prisoners for a long time, because in Texas, 70% of Texas prisoners don't have air conditioning. And I mean, it's really, it's like torture. And, instead of fixing the problem, which costs money, what I see people do is they normalize suffering. They essentially blame the prisoners for suffering. Like, well, what do you think? You commit a crime and it's going to be the Hilton? No, you did the crime. Now you do the time. And I mean, I think it's a real Rorschach test of what kind of society we are, how we treat prisoners, because they're the most vulnerable. They can't go somewhere else. They can't install air conditioning themselves.
Yeah, exactly. The Reuters article that I referenced talks about, it follows the story of one prisoner, and he has a vent in his cell, but he said it barely ever works, and he had to earn $25 to buy a little fan, and that's the only thing he has for cooling, and they make on average about 25 cents an hour.
Right.
It took him over a month to save up just for this one little fan that doesn't actually cool him, it just circulates the air.
Yeah. So Kelsey Ward 4083 asks, what led you to study this?
Yeah, that's a great question. We've partnered with the principal investigator. Actually has a few different roles, and she's been very interested in kind of getting more regulations passed for both prisoners and workers in general. So we also did all of this analysis for warehouses across California, where it's just employees who are working in outdoor or unventilated facilities. And so we're kind of tying both of them together. And a lot of this is really to try and get better regulations passed to ensure that, workers and incarcerated people are better protected from heat, from smoke, and from these health risks that are accompanying these exposures.
So Samantha J. Kramer asked, can you speak to some mitigation options? So I think clearly air conditioning is for heat, but what can you do for smoke?
Yeah, for smoke, there's a lot of stuff you can do, but like you kind of said, a lot of it costs money too. One of the simple ones is PPE. You can provide masks for people when smoke is there. A lot of smoke is typically specific events. It'll be, one wildfire that's nearby. Those projected results we looked at was specifically looking at that. It was basically how many wildfires are nearby, and assuming that corresponds to smoke exposure. So you can plan for specific events and make sure that those they're not outdoors. They're minimizing their exposures, and those are just a couple of things. There's a lot more in there, but yeah, we'll stop there.
Right. So do you worry about there's a real push to get rid of like DEI funding, it's like that. Do you worry that studying incarcerated, here's a question from, I guess, Live Life 9680. Will this count as DEI, and therefore, the research is going to be basically suppressed?
That's a good question. I don't know, honestly. And I think that's part of why the warehouse and employee angle is more of the focus, because it's that's a much more, I think, digestible study for people to understand why it's being done. And it's the same kind of thing where, if you're going to push for all of these extra protections for people working in prisons, then why not just go ahead and push it onto everybody in the prison as well?
Right.
But yeah, I don't know exactly how it relates to DEI. That's an interesting question.
Yeah. Well, anyway, Tyler, thanks, and Gig'em. And I think we're going to have to move on from here. And I'm going to hand it over to Margaret Duffy, who will take over as host. So I hand it over to you.
All right. Thanks, Andy. Yeah, great to be here. So let's all remind ourselves why we're here. We are weather and climate scientists. Here to share with you what we do. That's our primary goal. But we are also at kind of a difficult time for weather and climate research, especially when it comes to federal funding. And so we're here to share with you all, the public, what it is that we do, why it's valuable, hopefully convince you that it's valuable, and encourage you to please contact your representatives and let them know that this matters to you and should matter to everybody, in my opinion. And so the next speaker will be Helen Fricker from the Scripps Institution of Oceanography. Helen is a glaciologist, and we're going to have an exciting talk about the Earth Dynamics Geodetic Explorer mission. So go ahead and take it away, Helen.
Great. Thank you. Do you see them now? Am I sharing?
There you go. That looks good.
You see my slides and you can hear me?
I can.
Yes, perfect. All right, so I'll go. I just can't see you, so I don't have any indication of how things are going.
Looks good to me. I know it's a little like disorienting.
Yeah, no worries. Okay, well, I'm going to get going. Thank you, Margaret. Thanks for the introduction. I'm really delighted to be here. And also, I believe we've been going for 24 hours right now. Like it started at this time yesterday. So this is pretty amazing. There's been a consistent level of traffic at this whole event whenever I've tuned in. So it's really cool to see. So I'm here to talk to you about a new mission that was recently selected by NASA in the Earth System Explorers competition. It's been in the works for nearly 5 years. And it's a little bit different because we're talking about measurements across the full Earth system, but I wanted to sort of bring it into the picture of how it's going to allow us to navigate this time that we're in with a rapidly changing climate and all of the ensuing changes that we're undergoing on Earth. So it's called EDGE, Earth Dynamics Geodetic Explorer. We're talking about it as a community LiDAR. It's a laser altimeter or a LiDAR, and it's going to be mapping the entire globe from 82 degrees north and south. It's basically going to be like a giant laser pointer in space, taking measurements of the height of the Earth, which tells us a lot about many different things on Earth that we care about, such as terrestrial ecosystems, ice elevation, which is land ice and sea ice. So that's glaciers, ice sheets, and sea ice as well. So this is a PI-led mission. I'm at Scripps Institute of Oceanography, UC San Diego. My deputy PI is at University of Maryland, and we're working with NASA Goddard Space Flight Center. And so on here, you see Brian Blair, the instrument deputy PI, and also Scott Lethke, who's a project scientist. So as we know, and as we've heard during this amazing 24 hours of live stream that we've had so far, Earth system is warming rapidly. We also know that it's interconnected, right? And so many of the different parts of the Earth system are actually sort of teleconnected to other parts. So, for example, the Amazon rainforest, the West Antarctic ice sheet, it's all part of the same system with the carbon cycle, the energy cycle, the water cycle, all interconnected. We know that every year the global average temperature is increasing. We also know that as we go above the sort of 1.5 degrees Celsius above pre-industrial average temperatures, we are going to be in an era of very fast change, and whereby many of these things that we see on the right-hand side, which we call climate tipping elements, many of these are going to reach thresholds beyond which they will be breached. So changes in them will become irreversible, and at which point things start to really change. So many of these are in the ecosystem. So we see the boreal permafrost, the Amazon rainforest, and we also see on here the ice sheets, the glaciers, and also the sea ice and permafrost as well. All of these things are very important for tracking and understanding where we're at in this sort of unprecedented situation that we're in with Earth. And we need to be able to navigate where we are. We need basically vital signs tracked, so we know how the Earth is doing in terms of its health. Just like a patient, we track temperature, we track blood pressure. Same with the Earth, we track vital signs. How are the forests? How are the ice sheets? How's the sea ice? We can do that with laser altimetry, and we can do it systematically. And we've been doing it for a long time, actually. And what EDGE does is it brings it all together in two different things at once, ecosystems and ice, mapping them all at the same time. So this talk sort of split up. I'm telling you, first of all, about the history and evolution of altimetry, and then we'll talk about the other elements of EDGE as well. So EDGE is actually not, it's not a brand new concept in that it's a laser altimeter. We started out with satellite laser altimetry in 2003. This is actually the mission that brought me to the United States in the late 90s to work on for NASA. My postdoc supervisor was on the science team then, and I've been working on these missions ever since. So this has been a super exciting development, a sort of technology curve that's increased. We've gone from a single laser pointer on the ground. So ISAT was basically one laser pointer in the infrared, very, very sparse ground tracks, but, you know, it's still very much unprecedented information. I think of this technology arc a little bit like the iPhone or the phone revolution. Like in the 90s at this point, we still had those flip-top phones. In fact, I think flip-top phones were a big thing at that point. So ISAT was really, really very cool and revolutionary, but we look back now and we think, oh, how could we have dealt with that? Now we're in an era where we have two missions flying. One is called JEDI on the International Space Station, and the other one is called ISAT-2, which grew from ISAT, but it's multi-beam. So we have 6 beams instead of 1. And so basically we get much more coverage every time the satellite comes around, which increases our spatial sampling and gets other information that we need that way as well, like slopes and things. But both of these missions are also constrained, JEDI by its orbit on the International Space Station, ISAT-2 by its sampling. The little circles on the bottom show you the sampling of the same spot on Earth in ecosystems and ice for all of the missions. And I'll show you the EDGE ones in a more compelling way in a minute. EDGE basically is going to continue on this sort of path of delivering geodetic surface elevation, very precise elevation, very fundamental parameter of Earth, but it establishes a new era because it's actually what we call imaging. It's an imaging LiDAR. It's each of its ground tracks actually puts down a mini swath because there's 5 lasers. Each of those lasers is split into 8 beams, and the beams are all close together. So our mini swaths are 120 meters wide, which just gives the most incredible coverage. And every time we go around, we track the Earth. So you go from laying down like cotton around the Earth to laying down ribbon, but 5 of them at once around Earth. So if you imagine wrapping a ball, the coverage is incredible. And so, yeah, so I'm just going to tell you a little bit more about how it works. Basically, laser altimeter sends a laser pulse from the satellite to the ground and back. If there's vegetation there, you will get a return from the top of the canopy, from within the canopy, and then from the ground. That gives you information about the biomass, the amount of biomass, how much carbon there is in the trees, what type of trees, and then also the ground. Over ice, it's less complicated because you've only got the ice. The information gives you the surface height of the ice. Over the sea ice, it gives you freeboard, which you can turn into ice thickness. So there's a sort of strategy in the way that EDGE is implemented. We have teamed up with, some of you will wonder who this is. So Intuitive Machines bought out Maxar, who flew the Worldview missions. And so this is actually the Worldview Legion spacecraft. It's now called the IM-500 spacecraft. We chose that spacecraft because it's very stable. And we need that for the high accuracy, the geodetic part of the mission. It's also agile, and we need that so that we can pivot and target if there's a region that suddenly needs more attention. And that is probably going to happen in 2030 onwards. We're going to see places that we want to sample more and more rapidly and in more detail. And this spacecraft allows us to do that. We have also chosen a strategic orbit. It's a sun synchronous orbit. Which means that the tracks, the turning latitude is 82 degrees north and south. It's not as high as ISAT-2 went, but it actually gives a very high density of tracks around the edges of the ice sheets where the changes are actually occurring in the very steep, sort of noisy regions with complicated surface topography that we weren't really able to capture very well with ISAT-2. It also places a low altitude over the tropics, and that's because you have very thick canopy there and you want to be able to improve that, what we call the link margin. We also, I'm not going to talk about this much more, but I'll just show this quickly. We have a strategic way of operating the spacecraft. We can either be in this, what we call the reference ground track distributed mode, just the normal mode. We can also go to targeting. So just say there is a place that you want to go more and look at in more depth, you can do that. We also have some other capabilities as well, which are really going to help. And some of these, this particular one on the bottom left called reference ground track densification will be amazing because all 5 of the swaths will come together over the coastal corridors and get a 600-meter wide swath of just straight elevation, which is like flying an airborne LiDAR, but we're doing it from space and we're doing it systematically as well. It's the first time that has been done from space. So what about the transformative science that is going to be enabled by EDGE? Well, we're sort of we like to play on words with the name EDGE acronym. It's kind of at the leading edge of climate science. This is a slide that we've had in our deck since we very first started this project at the end of 2021. Forest fires, sea level rise, these are the big issues that people are grappling with, and all around the world at the COP meetings. This was in COP26, and only becoming more of an issue as we move forward. More forest fires, sea level rises increasing. They're just issues that we need to be able to track. And as I said, EDGE is able to track these tipping points as we go into this realm of irreversible change. We can actually see, we can collect data and see how close to being breached are these tipping points. So the difference between this figure and the one I showed before is you've now got the sampling on the right-hand side. So these hourglasses show the sampling by the 3 different missions. So JEDI, ISAT-2 spanning on either side. JEDI constrained by its orbit, ISAT-2 constrained by its spatial sampling. EDGE doesn't quite get to the limit of ISAT-2, but it has such a fantastic sampling that the surface coverage at all latitudes is way better than both of the other 2 missions combined. This means it's going to give us this fantastic ability to be able to track all of these things that we need to track. Okay, so this is heavily grounded in the decadal survey, which is this big thing that we do every 10 years. And we're just about to start this process again, actually, for the 2028 decadal survey. And so the decadal survey identified all of these science questions. And so we routed all of EDGE into these science questions. I won't belabor this, but people that are interested, look up the National Academy's report, and it's all about thriving on our changing planet. This was written in 2018 now. And so EDGE directly answers many of these questions that the decadal survey recommended, and is the sort of multifunction LiDAR that the decadal survey recommended. Very important questions there, also enabling some interdisciplinary science add-ons, which we're hoping to be able to have looked at. Wildland fire, carbon monitoring, snow, and permafrost as well. All of these are like really important questions that we're dealing with as humans living on Earth as Earth is changing. We also spend a lot of time thinking about what gaps we need to fill. Like, what are our current state-of-the-art, currently flying missions, JEDI for ecosystems and ISAT-2 for ice? What are they able to get at? So there's many things we can get with these missions, of course, like we're all working really hard on these data, but because we're not getting down to the spatial and temporal scales that we need to understand the processes that are really relevant for driving changes, there's many things that we're not able to capture. For example, I'll look at just the ice one, the blue on the right-hand side. For example, grounding zones. So grounding zones are sort of at the limit of what you can sample with ISAT-2, sea ice flows as well. EDGE will have much better spatial sampling capability, get us down to the smaller spatial scales that are relevant for sea ice, and also the temporal sampling as well on the y-axis to be able to get to understanding those processes. Once we can understand them better, we can parameterize them, put them into models, improve our climate models, our ice sheet models, and things like that. You can't model what you don't observe. These are the circles that I mentioned, and this is actually a very nice way of showing it. So JEDI on the left and ISAT-2 on the right. This is Amazon Basin and Cook Ice Shelf. These are 20-kilometer diameter circles. And so JEDI is great. You can see something. ISAT-2 also great. Lots of white space. This is what EDGE will see over the exact same field. So suddenly you can see detail. You can actually see, especially for EDGE, because, especially for the ice, because it's at high latitude and the tracks come closer together. We are now seeing crevasses. We're seeing really important details of the surface that you can't see with the other sampling. I know I'm running out of time. I'm going to just gloss over these and not go into detail. These are just snapshots of what we can do with these process scale observations in the ecosystems. We're able to track carbon fluxes better. This is an example from the state of Maryland, much more accurate and down to the much higher accuracy estimates of carbon flux accounting at the state level, and then scale that up to countries and scale that up to global. On the right-hand side, this is showing how much biomass was lost during a single fire event. This is a holiday fire in Oregon several years ago, and looking at the pre-fire and post-fire, like from the Jedi versus Edge, we can actually showing the Edge actually is going to show us so much better, with way better accuracy, how much biomass was lost during that fire event. Habitat, because trees are carbon, of course, but for animals, they are habitat. So this is an example from Borneo, the orangutan. The edge color is always in gold here because we're the gold standard here, and Jedi is in the green. The sampling of Jedi tracks is much lower than the sampling of the edge footprints, and so we'll have a much better idea of what our canopy health is like for these animals that are relying on it for their habitat. This is a coastal ecosystems example that I mentioned, and just really very nice high spatial sampling, enabling this incredible resolution of the coastal corridors. In the ice, I'm going to just jump very quickly through this. Around the edges of the ice sheet, we have a very complicated surface, and we're able to track very specific things, like on the left, basal channels, very important because basal melting happens underneath the ice shelves. Rifts, these is where iceberg carving occurs from. We can, with Edge, with the gold tracks, as opposed to the blue tracks, which is ICET2, we get much better resolution to understand that process at the scales at which it's needed. Also, for mapping glaciers as well, we are doing a lot of interpolating right now with our data sets, and with Edge, we won't need to. It's kind of like a Rosetta Stone baseline reference data set. Same with sea ice, just unprecedented spatial coverage and detail. And turns out that for the sea ice, it's all about habitat as well, because here we have the baby penguins from Amanda Bay in East Antarctica. They're relying on the sea ice health and the fast ice health for their colony to survive. So this is very nice sort of link between ecosystems and ice as well. I know I'm not doing great for time. I'm going to jump through this and sort of get to the end. I wanted to just tell you that Edge is not only going to be able to do all of this for science, but it's actually got a lot of implementable action data that we can get. Is basically understanding and navigating the situation that we're in with Earth, being able to map Earth and track Earth's height over time gives us this environmental awareness that we need. We need this so that we can really sort of get through this, the next stage that we're in over the coming decades, and gives us this opportunity for being able to understand and have the tools that we need to navigate. There's many products and many applications. There's also, we've got 72 letters of support, agencies that need the data, flood risk, insurance, sea ice, shipping, many things, water security. The data are very needed. And there's a paper that you might be interested in that came out a couple of months ago in New Space. It's led by Jim Garvin. And it talks about the return on investment for Edge. This is something that we need to do a lot more of. We need to show the public the return on investment for the missions. So the cost cap for Edge is $351 million. But the return on investment after 8 years is modeled at 50-1, which I think is a pretty good investment. And I think that, taxpayers' dollars are actually really well invested in the funding and the science that is being done across the board. So I'll leave it there. Edge is coming, and you can follow us on edge.ucsd.edu. And thank you.
Thank you for that talk, Dr. Fricker. That was great. Just real quick question. How have the proposed cuts to NASA impacted this research?
Yeah, well, we were selected. So, I mean, right now things are great. We're just moving forward. We're very. It's a fact that these data are needed, no matter what you think about, what's happening in the Earth system. You need to be able to have parameters to tell you about the shape and structure of the Earth. You need to know about the coastlines. You need to know about the trees, the forests, the ice, the sea ice. The data are needed, no matter what side of the aisle you sit. And so that is actually something that I hope that people remember.
Yeah, you're one of the lucky ones. So thank you so much for your talk. That brings me to remind you all why we're here. A little over 24 hours into our 50-hour live stream, almost to that halfway mark, I think. And that is because of the cuts to the weather and climate research. And one of those cuts that's happening right now is that the current administration is actually trying to dismantle NCAR. That's the National Center for Atmospheric Research, which is a federally funded research lab that does weather and climate research. They develop one of the climate models that we have here, CESM. And that's really because that model is so available and well documented, and they have so many great resources for the science community to use their model. It's one of the most widely used models in our field, but the organization that develops it is at risk of being cut. And so this climate model that we really rely on a lot for research in this country is also at risk of being cut. And just personally, I was a postdoc there for 3 years. It was awesome. I loved being there. And so on a personal level, it just really breaks my heart to see it not being valued. So with that, I really hope you'll call your representatives. We have a little link going across the bottom here where you can, with some resources for how to do that. And without further ado, let's get to our next speaker. That's Emily Williams, a postdoc at UC Merced, who's going to tell us about climate fingerprints on drought.
Absolutely.
Yeah, thanks.
Yeah,
Emily.
thanks so much, Margaret. And thanks so much for the entire team that's put this together. Amazing that we're about halfway through now. Incredible seeing all the science is being showcased, specifically science, right, that's being supported by federal funding, or at least historically has been. So yeah, I am a postdoc. I'm based here in California, where I was born and raised. Specifically, I'm at UC Merced. And for anyone who doesn't know where Merced is in the Central Valley of California. And that might sound familiar to you all because the Central Valley is really where the bulk of the US's agricultural production happens. So if you enjoy vegetables and fruits, nuts, etc., you're probably getting that from the Central Valley. So for these reasons, because of being born and raised here, and then also because of my work at UC Merced, drought and water resources have always been really important to me. And for that reason, that sort of led me into my work. So today, I'm going to take you on this tour of how climate change is affecting drought and water resources in the Western US, show you some of the tools that we use to identify how climate change has these impacts. And then we're going to do a little bit of a touch on how federal funding has made this kind of research possible. So we're going to start off. I'd love to first of all show you this incredible tool that I come back to time and time again. Some of you may have seen this before, but this is the US Drought Monitor. Now, US Drought Monitor, this incredible platform tool, consortium of researchers, all kinds of different things. And as you can see, is supported specifically by different federal scientific agencies. Now, what the Drought Monitor does is every week they put out this updated assessment of drought. It's based on all these different indices. It's based on stakeholder engagement, people who really work and manage resources on the ground and giving input of what's going on with drought. And as you can see, this is rewinding the clock a little bit. So if we look back about 4 years ago in 2022, a lot of the Western US was in this really exceptional drought. That drought had been going on for about a decade. And then for anyone who lives in California or other parts of the Western US, you might remember that 2023 really flipped the script on us. So 2023 then brought this torrential rainfall. In fact, so intense that here in California in the Central Valley specifically, there's incredible flooding. But what it did do, again, if you compare the map between these two time periods, it brought us out of drought, at least for a lot of areas. Now, since then, we've started to have drought conditions creeping back in. So this is the most recent map from just last week. So why do we care? We care because drought, and by extension, impacts on water, matters for so many different sectors. It matters for ecosystems. It matters for our cities and our towns with where we get our water from. It matters for agricultural activities because agriculture, right, irrigation uses water. But what is drought? So I'm talking about drought. You all probably have a really good idea in your head of what drought actually is, but it turns out there's a lot of different definitions just because of how far-reaching it is. So we have different droughts. We have meteorological droughts. These, for instance, happen when there's not enough precipitation. There's something called hydrological drought, which is when you don't have enough, say, surface water, so river water, water in your reservoirs, etc., to meet demand. There's agricultural, socioeconomic. Broadly speaking, though, you can really just think about drought as when local demand is going to be greater than supply. So we have more of a demand for water than we can actually meet with the supply. Now, definitions like this, though, are incredibly important. Thanks, Noah, right, for giving us some of these definitions or providing them here, because you're going to use a different definition depending on what kind of impact you're most interested in. So if you care about surface water, you're going to be looking at hydrological drought. Are you a rancher? Do you work on the rangelands? Then you're going to be really interested in something like agricultural drought. So having these definitions, this understanding of how drought arrives, how it propagates in all these different indices is incredibly crucial for us to be able to manage everything, just about. So I'm going to go ahead and focus on hydrologic drought for the rest of my talk. Again, because in the Western US, we really care about water resources, and we've had challenges with water resources quite a bit over the past couple of decades. We're in this water limited area, right? And again, if we think about, drought as having demand that's greater than supply, in the Western US, it doesn't exactly, but it broadly translates into this sort of equation of irrigation demand, for instance, being greater than stream flow or snowpack. The reason for that is that most of our incoming water, so most of our water supply in the Western US, is coming in the form of snowpack. So we get a lot of snow in the cold winter months. That snow, that water is stored in those months, and then in the spring months, that's going to melt. We're going to get the stream flow, right, that comes through. And then in the summer, in these hotter months, a lot of this water gets used. Now, obviously, this is an incredibly simple way of thinking about our water balance. But one reason that we're really focusing on agriculture here is because in the Western US, agriculture is using actually the vast majority of water. So depending on what state, what basin you're looking at, it's going to be using anywhere between 75 and 85% of our total developed water supply. So thanks to incredible scientific research that has been done by these different groups here, we have this understanding of our water balance. Oh, and interestingly enough, all these papers were made possible thanks to federal funding. So we love to see the federal funding in science. So what if we want to understand how climate change is affecting this equation? How is it affecting the supply side, that snowpack side, and then also the demand side? This is where detection and attribution science come in. So detection and attribution science. This is broadly the area that I work in. A lot of other folks I also know work in this space. And the idea is that we look at different aspects of the climate system or even impacts from the climate system. For instance, we could look at, say, water, at different measures of water. And first of all, we start by detecting. So detecting, has this measure in some way changed without saying a reason for why it changed. But then after that, we go into this attribution exercise where we start to think about or try to establish the most likely causal pathway. So what is likely contributing to this change? So on a good day, when we want to feel cool, I like to think of us as sort of like detectives of the Earth system, right? We're trying to get into the weeds, figure out the likely causal pathways. In reality, we're actually pretty nerdy computer programmers that are dealing with climate model output, observational data, and a lot of statistics. But just like a detective, when we're doing this work, the questions that we ask matters. So when we're asking a question, we're not going to ask something like, was this drought caused by climate change? Instead, we're going to ask, okay, we have this drought. It was really bad. Was it made more likely by climate change, or was it made more intense by climate change? So using that framework, I'm going to spend the rest of my time to give you a tour on the ways in which detection attribution science have highlighted these effects on the supply and demand side, and the ways that federal funding have supported that kind of science. Focusing again on the supply-demand Western US water equation. So let's start with snowpack. For any of you who live in the Western US, you are probably very painfully familiar with the fact that we have been in a really bad snow year. So I would love to highlight this incredible tool, this plot. Again, thank you, USDA. This is another way that federal funding and federal agencies have really supported science and dissemination of information. So this plot, what we're looking at is we're looking at snowpack over time. This is for the whole state of California. And what this curve is showing you is how snowpack, right, normally progresses. This green line is showing us the median. So, okay, November, we're starting to get some snow, great, great, great. And then we're getting sort of peak snowpack sometime around April 1st, and then it starts to fall off, right, as it melts. For those, again, if you remember from the beginning of my talk or live in California, you'll remember 2023 was kind of a crazy year because we had really heavy rainstorms, broke a lot of records. This year is not looking so great, which you can see in the black line. And in fact, we are approaching near minimum snowpack across the Western US. So how does climate change affect this equation? What we do know is that climate change can do two things when it comes to snow. Number one, when you have precipitation falling, if it's warm enough, it's going to fall as rain instead of snow. And especially also if you have a ripe snowpack, if it falls on top of that, in some cases, it can lead to early snowmelt. Second, in springtime, if you have warmer temperatures, you can have early snowmelt. So if we were to go about and try to do an attribution exercise, which we've done, what we do, and in this case, what we did is we go ahead and we figured out what temperature and precipitation would look like in this counterfactual climate, sort of a what if. We make use of climate model output, we make use of observational data, and we can do these different tests to sort of get this sense of what would temperature and precip have been like in a world without climate change. We then go ahead and feed it into a hydrologic model to estimate snowpack. And this is some results from some work that we actually have in press, so hopefully it'll be forthcoming in the next couple of months. But what this shows, you're looking basically at the difference in April 1st snowpack, how much less snowpack we have April 1st, specifically because of climate change from this attribution exercise. Now, I'm going to be honest with you, these are all in units of cubic kilometers. I have no idea what that means, so let's do some social math. Turns out annually what we're seeing is about 3 Lake Mead's capacity worth of water less April 1st snowpack, specifically because of climate change. So again, that was the supply side of the equation. What if we want to go ahead and look at the demand side? Because again, this drought equation, we have a diminishing supply. What's happening though with demand? So for demand, again, I'm going to be focusing on this other side of the equation, specifically irrigation demand. There's only one physics lesson or one physical principle that I want to communicate today, and I promise there's no equations I'm going to be showing. The specific physical relationship is the fact that in a warmer climate, so specifically when the air temperatures are warmer, the atmospheric water holding or the water holding capacity of the atmosphere increases. So there's this awesome article by Swain et al. Came out in 2025. Oh, look at that, was also supported by federal funding. We love to see that. And in this article, they had this really clever analogy that they showed. And this photo is from, or the image is from there. And in this analogy, they talk about, you can think of the atmosphere as a sponge. So if it's cool, the sponge isn't going to be that big. But as it gets warmer, the atmosphere, the sponge increases and can hold much more water because it's a bigger sponge. And when it does that, that means that evaporative demand in the atmosphere is going to be trying to pull water out of the Earth system or the Earth surface. Very simplistic description, but the relationship is, roughly speaking, for every 1 degree Celsius of warming, that capacity increases by about 7%. So we can take this physical principle and then we can apply it using a detection attribution framework to think about how much more irrigation we're going to have to apply to plants, or how much we already have to apply to plants specifically because of climate change. Again, hotter days mean thirstier air. Plants lose water through transpiration, right, as they photosynthesize. And to meet increased water needs of crops, that means that you have to increase irrigation. So we went ahead and we did another study, right, where we applied this framework. And again, we were looking at California Central Valley, where we have a lot of the agricultural production in the US. And we were able to show this really dramatic increase in irrigation demand, specifically because of climate change. What I want to point out is what I want to point out is we have this black line, which is showing the observed change in irrigation demand over time. And this blue line, which is then showing you what it would have looked like without climate change. You'll see that it still would have increased, but not by as much. How much has it increased by? Well, it's increased by around 9.2 cubic kilometers. Again, I feel like that sort of value is kind of hard to think about what that means. But to put this in context, the Central Valley, which has had incredible groundwater loss over the past few decades, during this time period experienced around 80 cubic kilometers. So we're looking at this increase in the amount of water that has to be applied to crops because of climate change. That's roughly 11% of the observed groundwater loss. And that matters because when we're thinking about the fact that with climate change, temperatures keep increasing, that sponge keeps growing, we're going to have a really tricky water balance situation that we need to figure out. So, and this also, thank you, federal funding for science. We really love to see it. So what I would like to do is go ahead and close out with this final message, again, showing the Western US Drought Monitor. We have drought. We've always had droughts. We've always had water challenges. Droughts have come and gone. But climate change has made these worse. And while there's a lot that we do understand about these pathways, the ways that climate change can affect drought and can affect water resources, there's still a lot that we don't understand, even more of the dynamics between these changes in groundwater, for instance. And I don't know about you, but I know for myself, at least, when I'm faced with a really big challenge, I always want to have more information to help me make a decision. And that's the crux of any sort of water management water manager's challenge or a rancher's challenge, right, is you need information to help you make informed decisions. Federal funding historically has really helped us provide that information, create that information to support that kind of decision making. And having more federal funding is going to help us close some of those remaining gaps. So I'm going to go ahead and wrap it up there. Thank you so much. I would love to hear any questions that folks might have.
Thank you so much, Emily. Yeah, let's get to we have a lot of questions in the chat, so let's start getting to them. Do you think if we have more frequent severe, we're going to do a different question. Do you think if we have more frequent severe El Niños, it'll swing California to a wet climate? Or do you think the corresponding droughts would negate the extra water?
That's a really good question. I'm going to hedge a little bit and then end by saying I don't fully know. But what I'm going to start by saying is, for those who don't know, right, so El Niño, La Niña, incredibly important oscillation. Generally speaking, when we have El Niños for the Western US, that does usually translate to both warmer conditions, but also wetter conditions. It's a little tricky. So one thing that we do know with El Niños is that, yeah, we can have these sort of wetter climate conditions, but from a water resources standpoint, if it's wet and warm, it means that we have these really intense rainstorms, right? And that means that we don't necessarily have the sort of the really good ripe snowpack that builds. And the problem is, it's not just how much water that we get from a supply side, it's when and how we get that water. So if that water is dumping all in one moment, not as snow, if it's falling as rain, we can get flooding. And a lot of that water can also run off. The nice thing about a snowpack, you can think about it as like an above ground reservoir, just this natural reservoir. We have it, it's held there, and then it melts and then becomes surface water in the months that we really need it. There's a lot of work going into how climate change has also affected El Niños and La Niñas. It's not work specifically that I've done, but I know some folks have been involved with it. Someone in my group, Madhu, has been looking at how El Niños, for instance, are affecting crops. I know people at UC Santa Barbara who have been looking at how climate change has affected El Niños. So again, a lot of questions that still need to be answered there so we can have really good answers to questions like this.
Such important work, Emily. Thank you. There's a couple more questions in the chat that I hope you can get to, but I think we should move on just in the interest of time, trying to keep us on time here. But thank you so much. So just to remind everybody why we're here, we were here last year live streaming for 100 hours. This year we're live streaming for 50 because there's a new round of budget cuts and proposed budget cuts that are coming through and affecting our ability to do science. And so there's a proposed budget for the fiscal year 2027, which cuts the NSF and NASA Earth Science budgets in half, eliminates the research part of NOAA, and really just damages the training programs for the next generation of weather and climate scientists. And so all of this research that Emily did a really nice job of pointing out exactly where research was federally funded. And so that really highlights what we're losing with something like a 50% reduction in the funding for weather and climate research. So that's just a proposal. It hasn't happened yet. There's still time to contact your reps. There's a little link crawling across the bottom of your screen, wclivestream.com/act, where you can contact your reps if you feel so compelled. And that brings us to our next wonderful speaker, Galen Mckinley, a professor at Columbia University. And Galen is going to tell us about how carbon goes into the ocean. So go ahead and take it away, Professor McKinley.
Hello, can you hear me?
I think we're waiting for slides.
I cannot hear anything.
Well, we can hear you.
Okay, I'll try to go ahead and get started even though I can't hear anything. Okay, so yeah, hi everyone. It's a real pleasure to be here on the live stream. I am Galen Mckinley. I'm a professor of Earth and Environmental Sciences at Columbia University, and I want to talk about the ocean, and I particularly want to talk about how the ocean removes carbon from the atmosphere, how it cycles carbon, and how this plays a role in climate and climate change. So to begin with, I'm sure you're all aware that atmospheric CO2 is rising due to human emissions, but you may not be aware that the ocean and the terrestrial biosphere on net absorb about 50% of those emissions. So in recent years, we've emitted about 10 petagrams of carbon as CO2 to the atmosphere, and there's a very active cycling of that carbon through the land biosphere and through the ocean. But on net, the land absorbs about 2 petagrams of carbon and the ocean about 3 petagrams of carbon. So only about 50% of our emissions actually remain in the atmosphere. So if we're going to understand both the current rates of climate change and what's going to happen in the near and distant future, we really need to understand how these sinks operate and how we expect them to change going forward. So the real challenge in this is that air-sea carbon fluxes, I'm interested in the ocean side, of course, these fluxes really vary across space and time. This is an animation of hourly air-sea fluxes from a model run by NASA, the Echo Darwin model. Air-sea fluxes here, blue is uptake by the ocean, red is outgassing from the ocean, and gray are winds. And you can just see in this hourly animation how much variability there is across the ocean, you know, also both with time, also north-south, for example, here between the high latitude Pacific and the equatorial zone. So a lot of variability, and the real challenge is that the ocean is not terribly well sampled. So how do we understand this variability? And how do we really put this into context with this net effect of the global ocean taking up about 30% of all of our annual emissions? That's really the question we're trying to get at. So to begin with, we need to understand the processes of the ocean carbon sink. And here is a schematic of those processes where we think about the carbon in the ocean as the sum of both natural carbon, i.e. carbon that has been there since before humans started putting a lot of carbon into the atmosphere, plus this anthropogenic component, that's that additional amount only due to human activities. And so if you look in the top right here, you can see that there's a schematic of the atmospheric CO2. You can see that the natural is sustained at the pre-industrial background level, about 280 parts per million, and the additional is that anthropogenic that's growing rapidly over time. And so in the ocean, most of the carbon, the units here on this, the central profiles here are going down into the depth of the ocean. The units on the natural side are about 2,000 millimoles per meter cubed. And that is the vast majority of all the carbon in the ocean. That carbon is processed through a biological pump, modified by the ocean circulation. I want to explain these processes to you. Because of these activities of biology combined with circulation, we actually end up with more carbon in the deep ocean than in the surface on the natural side. The profile for the anthropogenic side is opposite, with more carbon in the surface ocean and less at depth. And the ocean circulation here is pushing that perturbation due to human activities down into the ocean slowly over time. So what are these processes in more detail of the natural carbon cycle? So first of all, you got to understand that the surface partial pressure of CO2 is really the primary control on air-sea CO2 exchange. This is, goes back to concepts such as Henry's law in high school chemistry, for example. So if the partial pressure of CO2 in the ocean is higher than that of the atmosphere, the carbon is fluxed out. And if the partial pressure of CO2 in the ocean is less than the atmosphere, the carbon is fluxed in. So what we really need to do to understand and quantify the air-sea CO2 flux is quantify this distribution of the partial pressure of CO2 shown in the top map on the left, and where greens are values that are higher than atmospheric and yellows are less than atmospheric. And on the bottom flux map, you can see that where the greens are strong is where we're getting red or outgassing from the ocean, where the PCO2s are lower. In the yellows, for example, we're getting strong blues on the flux uptake of carbon into the ocean. So the flux map shows us that the mid-latitudes and high latitudes are really taking carbon up into the ocean, and in the red, the carbon is being fluxed out of the ocean. So there's a lot of chemistry that happens, and a main reason why the ocean can hold so much carbon is because the carbon that is dissolved in the ocean very rapidly dissociates into different ions, particularly bicarbonate and carbonate ions. And these are very large reservoirs of carbon in the ocean. So in fact, more than 95% of all the carbon in the ocean is in the bicarbonate and the carbonate ions, and only a small percentage, really more like less than 1% or so in most locations, is as dissolved CO2. So really most of the carbon in the ocean is in these other ions, and that's partly why the ocean can really hold so much carbon and store it away from the atmosphere. I also want to talk about solubility of carbon in the ocean. So as you may be aware, the solubility of gases is higher when temperatures are low and lower when temperatures are high. So if you have a hot Coke in your car that's been sitting there all day, you probably don't want to open it up because you know it's going to explode. While if it's wintertime and it's been cold in your car all day, you're probably fine opening that Coke up because the carbon's going to stay in the Coke for more readily, right? So the same thing is happening in the ocean. We have more solubility of carbon at high latitudes, less at low latitudes. And that means when circulation acts on the ocean, such as the Gulf Stream carrying warm waters to the north, those waters cool as they encounter cooler and cooler air temperatures going north. That raises the solubility, lowers the PCO2, and leads to uptake of carbon into the ocean in regions such as the higher latitude North Atlantic. The other part of this cycle is the fact that there is biology going on in the ocean. So in the upper ocean, in the presence of sunlight, biology can take up inorganic carbon from the water, make organic carbon, and that reduces the PCO2, the partial pressure of CO2. So we can see from a satellite image taken by NASA here that we have high productivity in the bright greens, for example, in the subpolar North Atlantic, much higher productivity there, for example, than in the subtropical Atlantic. These patterns of productivity in the ocean are structured by the ocean circulation to first order. These are the kinds of data that we get from satellites that NASA has really led on launching in the last several decades, really critical data sets. A schematic here of biological cycling to show you kind of the processes where we have sunlight, where we have phytoplankton growing, taking up that dissolved inorganic carbon, taking up nutrients, entering into a food web, and some small part of that remainder of organic matter ends up escaping into the deep ocean and removing carbon net to the deep ocean. And these cycles of biological productivity, export to the deep ocean, physical transport and mixing are really part of linking between carbon, nutrients, and oxygen in the ocean. So we talk about biogeochemical cycling, coupling of carbon and nutrient cycles that happen due to biological processes, moving things vertically, and then the ocean circulation returning much of that matter to the surface ocean on seasonal and longer timescales. So the ocean circulation really is a critical piece here, moving waters towards the north in the Atlantic, moving waters to the deep ocean on long timescales, and setting the stage for all of this carbon cycling. I want to say just a bit about that circulation. Real quickly, we have a surface flow in the ocean where we have the Gulf Stream here and Greenland Current, for example, happening here in the North Atlantic. This process is due to winds pushing on the ocean, and things like the Coriolis force causing waters to move from high surface height to low surface height, and then around those highs in the surface height due to Coriolis force. And this also is associated with vertical motions of nutrients in the ocean, leading to higher nutrients at the high latitudes under that surface low, and lower nutrients under the surface high in the subtropics. Okay, I'm running out of time here, so I just also want to note that this circulation of the ocean, if we look now at horizontal, sort of vertically sections through the Atlantic here, we also see the linked cycling of carbon, nutrients, and oxygen here, where we have waters moving into the deep ocean in the northern North Atlantic, filling the ocean with lower carbon waters and lower nutrient waters and high oxygen waters. So all of these data that I'm showing you here were taken in coordination with National Science Foundation and NOAA, and really critical to understanding the basic cycling in the ocean of carbon and nutrients. Okay, so now, I wanted to just mention the anthropogenic carbon component very briefly. I've shown you that there's these very complex processes of the natural carbon cycle operating. And on top of this, we're trying to find this very kind of small signal of anthropogenic carbon going into the ocean. It's much smaller quantitatively. If you look at the numbers here, only about 50 micromoles per millimeter cube compared to 2,000 in the natural. How do we find that signal? Well, we do that by combining a variety of independent approaches, including these interior observations, including numerical simulations, and including surface observations combined with machine learning. And we try to pull all this information together to really understand how the ocean carbon sink is happening. If we only had one of these approaches, we probably wouldn't believe those estimates terribly well because of the sparsity, because of the some significant uncertainties. But because we can get reasonable estimates across these three different approaches, we do have confidence that we can constrain the ocean carbon sink and understand how it's contributing to modulating climate change. Much of the ocean carbon data critical to these processes are collected by NOAA, collated with data from other nations by NOAA, and served to the world by NOAA. These are really critical data sets for our ability to monitor the global carbon cycle and then monitor the pace of climate change. So I have a few links here in case you'd like to learn more, and I'm gonna end my talk there. Happy to take any questions if there's any time. And if I can hear.
Thank you so much, Professor McKinley. That's awesome. I know you can't hear us, but maybe we can put this question on the screen. Is it possible for us to clean up some of the carbon the ocean absorbs? If we put that on the screen, maybe Professor McKinley can go ahead and answer it.
Is it possible for us to clean up some of the carbon the ocean absorbs? I guess I don't really know what that means. So the carbon in the atmosphere is extremely diffuse at 400 parts per million, right? So that's many zeros there. So it's very diffuse in the ocean. The anthropogenic component of the carbon is also a pretty small component of the total. The ocean, chemistry allows that absorption to occur. So perhaps the asker is referring to questions of ocean acidification, which is a result of the ocean's carbon sink. That more carbon in the ocean does lower the pH of the ocean. And, we don't really have a remedy for that, particularly since the ocean covers 70% of the planet. And this process is happening kind of everywhere at kind of a low level. That would be very difficult to engineer a solution to that issue. So I don't think so.
Yeah, that's a tough one, trying to undo ocean acidification. Okay, thank you so much, Professor McKinley. I know you can't hear me thanking you, but thank you so much. So next, we are going to have a different kind of talk. But before we do that, let's just remind ourselves why we're here. We started this last year in the presence of deep cuts to weather and climate research in the US, and we're still being clobbered by big cuts to funding for weather and climate research at the federal level. A lot of those cuts are happening in real time, and some of them are proposed. And right now there's a proposal for the Office of Management and Budget to be very involved in the funding of scientific research, not just weather and climate, but all sorts of scientific research. And that's a pretty unprecedented type of proposal. The Office of Management and Budget has not typically been involved in that type of thing. So it's a little, I'm going to say, dystopian to have this being proposed, that political appointees would have to be involved in the approval of what kind of science gets funded. That seems a little bit counterproductive, at least to me. So I think Andrew Williams gave a really nice overview of what that would mean and why that would be disruptive to weather and climate research in the US. And so if that bothers you, if the threats of cutting NCAR bothers you, if the threats of cuts to NSF and NASA Earth Science Research bother you, I really encourage you to contact your reps at wclivestream.com/act. We have a script all ready to go for you, which is great. And our next two speakers are going to be having a conversation between two generations of climate scientists, Rob Socolow and Nadir Jeevanjee. So why don't I welcome you guys to the screen? Thank you so much for joining us.
Thank you, Margaret. I guess we can't see Rob right now.
What am I doing wrong here?
We can hear you.
Yeah, I see that. I don't know why I'm not visible. Any suggestions? In the show, everyone can see and hear you, it says.
Everybody can hear. Are there 3 dots? Are you seeing 3 dots that you can click on? Is there an
I think the 3 dots off in the corner with my name. Let's try that.
Are there any options there that look promising?
Edit avatar, visual effects. Stop. What's visual effects?
And there's nothing covering your camera?
No, I was on something this morning. I'm looking at camera with a name, standard. Let's see if there's another camera. Oh my goodness gracious. Let me try this. Oh, how about that?
Yay.
And then
There you are.
Right? Yeah. Oh, good.
I'm going to let you guys take it away.
Great. All right. Well, so Rob, you and I are both scientists here in Princeton. And you've been a mentor of mine since I arrived here about 10 years ago, but you've been in Princeton since the early 70s.
Right.
Decades-long career working on environmental and climate problems of sort of all stripes. Many of the problems on sort of the energy and solutions side of the climate problem, but, fundamental work in energy efficiency, carbon capture, nuclear proliferation, had a big paper in the 2000s on stabilization wedges to mitigate climate change, a paper with thousands of citations. And so you've worked kind of across fields that, intersect or have been informed by climate science. And another thing you and I have in common is having switched from physics and in fact theoretical physics to these environmental science fields. And I'm wondering if you can tell us a little bit about this transition and also the role that climate science has played in your motivation in studying these issues and how it's informed your worldview over the years as you've pursued these problems.
Sure. Okay. So, yes, I studied physics until not long after I turned 30, and I was really happy with it. But then there was something missing. What was missing was the social side. And just when I was restless, we landed on the moon, we had Earth Day, we discovered the environment. I had not learned a thing about global risk all the way through college and graduate school and so forth. That was going to come from the climate change. And what the message, because the nuclear war was on everybody's mind, and we obviously could destroy ourselves. That was in the front of everybody's mind, but it would happen all at once. It will happen because of miscalculations and extraordinary stupidity in how we related to one another. But here was something completely different. It was change that was generated by our doing ordinary things on the planet when we were in the hundreds of millions of people with relatively simple consumption patterns. It really wasn't going to change the planet. If we lived on Jupiter now, with an atmosphere, with everything else the same except our size, we'd probably be getting away with everything. But here was a message which combined science and ethics. I found it absolutely compelling. We actually need to keep track of keeping our planet habitable while we go about things that we never imagined were troublesome. So I said, this is a career for me. I've got a strong interest in ethical issues, and I'm interested in the science. Now, the science that we need to manage the planet so we don't dig a deep, deep hole for ourselves is climate science. So when I hear the climate scientists, I want them to say, I know they feel it, but they sort of lost track of how special it is, that they are doing the key science which will keep the planet habitable. As I take it to 50-year time frame, and the planet's going to be very different. It matters a lot what we do, but we need the signals of what's dangerous and what's not dangerous, and how well we understand what's dangerous and not. Now, if I'm not mistaken, you have yourself been trying to parse what we know well, what we know a little, what we know hardly at all. I think that's a terribly important thing to be communicating, and we're not actually doing a very good job communicating that to the public, and that's all the source of a lot of the lack of appreciation I mean, you guys this is a showcase, this live stream of one wonderful young investigator after another, doing science, not having a thumb on the scale, wanting to get it straight. We need you guys so badly. Over to you for at least, we'll go back and forth, but over to you.
So, you mentioned that just the critical role of climate science in telling us what's happening and what's coming. And you've written before that without climate scientists, we'll be flying blind in this area of planetary change. What are some of, maybe we can approach this both in terms of the past and the present. What are some of the key things, that climate science has already accomplished that have kept us from flying blind? And when you talk about, how important the science is now, what are the things that come to mind that you see as crucial in terms of the climate science that needs to be done?
Well, we're not necessarily going to understand it. I think the goal is to reduce surprise as much as we can. We cannot now rule out what a whole variety of ways in which the Earth could react to our poking it. There's a book by Wally Broker, who's kind of the dean of this subject, and no longer with us, was Lamont Doherty, an oceanographer. And the cover is the inside cover is a dragon. The dragon's about 10 feet tall. And there is a human with a pitchfork who comes up to about the tummy of the dragon and has this pitchfork poking the dragon. And the caption was "Poking the Angry Beast." In that symbol image, which I keep thinking of, it's what I think we're dealing with. We have an Earth that is capable of roaring. We don't know quite well what would make that happen. I don't think it's roaring yet in the way that we would just drop everything to fix, but we know it could. And we have lots of intimations of what could come. So with the oceans, where we need to understand the oceans, including the deep oceans. We're learning at such an exciting rate right now. And then the atmosphere, what's the radiation balance at the top of the atmosphere? The forests, each of those, and the ice, each of those is making each of the research in each of those is making an enormous contribution. But it's a slow process, as science always is. Now that you work on some of those very issues yourself.
Yeah, and it's something we, as I mentioned, I do outreach with a group called Climate Up Close, and we travel to kind of communities around the country, and we deliberately try to kind of, get out of the, highly urban coastal regions and get out into the middle of the country and less developed places to talk about climate science and just to bring our presence and be available to people. And one thing we do emphasize are sort of that climate science spans a spectrum of things that we know well, that global warming is real and humans are causing it. And there's some things that we, have some information about, but not complete information. Extreme events, extreme weather is a good example of that. And then there's things that we're, much less certain about, like tipping points. And that kind of brings me a little back to the, poking the dragon analogy of this Earth as this system that we're kind of unintentionally probing the behavior of. And so what are the things that, come to mind or worry you the most when you think about us poking the dragon? Is it these tipping points, that what's going to happen to the ice sheet? What's going to happen to the Atlantic overturning circulation? Is it more extreme events?
I think in the end, it really is those, because they will come on faster than the gradual change that the tipping point is a reasonable image of where change goes nonlinear. I should maybe explain one other thing because 60 years after getting excited about climate change, or 60, let's say, just under. I have a wonderful perch, and I'm dealing with these issues. I work for setting the doomsday clock of the Bulletin Atomic Scientist, which is trying to figure out each year, are we more or less able to contend with the threats we have generated ourselves to the planet across nuclear war, climate change, biological effects of disease and plague, and then AI. Those are the four at the moment that are front. And each of them, the experts don't know how bad the problem could be. Nuclear is the one that's sort of best defined We just have this horrible arrangement where we're going to, if one of us hits the other will hit back. Never mind that the planet might get destroyed, which we simply need to get past. But the climate one, people in these other fields say to Rob, tell us the threat and tell us the capability of dealing with the threat and the understanding of the threat and the change from year to year. So capability is a big part, and that's the one we're particularly worried about in this program, the loss of ability to measure stuff and to model stuff, which is, I think, frankly, insane at a time when we have a threat of this sort. I cannot understand. It is the goal of this group, and I'll do anything I can to help to get the public to appreciate that this is not what sensible people do. There's not you shoot yourself in the foot or various images. But what do we need to understand? And what do I need to understand to bring to that committee that you guys can help me with? And we get a report, and we know each year that the temperature is hotter. We have all kinds of effects like the storms and the fires. And we're great, but it is hard. It's a slog. And what impresses me is we have to use the science method. And the young people are committed to the science method to get headway on one problem after another, like El Nino, which we heard a segment of this morning. And yet we have this perception in the public being emphasized in various ways that young people are on a holiday, and they're not on. They're working their heads off for our benefit. We ought to be saying thank you every day, and here we are deriding them. So yes, I can't personally point to a single one effect that keeps me up at night related to climate, because I don't know enough. What I do know is that there are a whole variety of ways in which we can make this problem, in which we could be making this problem much worse. You mentioned, I have this counterfactual in my head. You mentioned, I'll say it too, and maybe some of the people later in this program can play with it. Suppose we really just happen to miss the development of physics and chemistry, and we really didn't understand. Let's call us a bunch of avatars living on this planet who nonetheless love fossil fuels and built a pretty prosperous economy globally. And the carbon dioxide concentration was going up, but they didn't have the faintest idea that should be measured. At what point would they say, we need to think about this. Maybe we're doing something to ourselves. It might take a really long time. We'd be dreaming up excuses about natural variability. And I think we might be past where we are right now. Fortunately, incredibly, luckily, we have built the science along with our fossil fuel economy. And we have the ability to understand radiation through gases. And we have an understanding that we have a problem by burning fossil fuels. We could go on a very long time burning fossil fuels, drive the carbon dioxide concentration to very high values. Nothing's in the way. There's plenty of fossil fuel. It's an awfully attractive fuel compared to the alternatives, I think, and others don't necessarily agree with me. So I'm not sure we'd have the feedback that would get us into a safe place. The guys on this program, the gals on this program, are the feedback loop.
Yeah. I mean, something that strikes me, even though, I am a climate scientist, I work in a federal research lab where we model the oceans and the atmospheres and the land surface and the ice. It's something that this live stream really just makes plain and brings to the world is just the sheer breadth of climate science, which, kind of spans the work that needs to be done, from the satellite measurements of so many different quantities, including the radiation balance of the Earth and clouds and photosynthesis and on, to in situ measurements of the ocean variables via buoys, weather stations on land, campaigns to understand the ice sheets. I mean, the planet is huge, and it's such a massive endeavor to try to understand it. There's also a really great series of articles in Quanta that I don't know if folks in the audience on this live stream are aware of. Maybe if someone backstage can find and put it in the chat. But Quanta is a science magazine, and they picked up on these themes just within the last year, and wrote a fabulous series of articles, I think called "How We Came to Know Earth." And it chronicles some of this and gives some of the sense, as this live stream does, of just the sweep of effort required to get to know our planet.
But that has already happened, or that mostly lies in the future?
The article?
Yeah, the whole.
Yeah, it came out within the. It's a series of articles.
I mean, is the story that they tell the story of how we've gotten to how much effort took it
yes,
to get where we are, and there's a second set of concerns. What is it going to take to get the next serious increase in understanding?
Yeah, I think it's mostly kind of retrospective.
Right, and a lot of that we went global in our science, Earth science, in the 50s, and the International Geophysical Year was 57, 58. We discovered the Allen Belt. We started the Mauna Loa measurements. We had the Sputnik at that time. And that's really, in some sense, that's where the clock begins, in my sense. We studied the planet as a whole. We saw all kinds of things that took us by surprise. And the climate science, one of the things that appealed to me when I made this career shift was it is global, and I like global. I like the idea that I'll be part of a world effort that absolutely depends on global communication. We need to get data sets from here and there and combine them. And that's another dimension to the normal way in which science is done. But so the question is, why is it so hard to get this message across? I think, the one answer is it's natural to shoot the messenger who brings bad news, or even news that's just doesn't let you be complacent. And so we would like it not to be true, that we have the ability to change the planet. And that's the easy part of the answer. The hard part of the answer for all of us is how are we contributing to this? What's our share of responsibility for this lack of this ineffective communication? So when I talk to people, there are ways of disarming this opposition and changing their minds. First of all, is to emphasize that we're talking about doing climate science well, and it is possible, especially as the public and the media get involved, to communicate they're doing something other than doing science well. We have to be vigilant and call those issues out. Just as in the health area, we have to explain what we know and what we don't know, so that people don't get suspicious that they were on a joyride. And the other is really, so climate change is not the only important problem. And I think one of the things that some of the people most known for fighting climate, deep down, they're worried that we're giving it too high a priority. Yes, it's important, but other things are important too. The developing countries having ability to move out of poverty. If this is in the way, I don't want to hear about it. It is one of the best examples. If we've got to shut down fossil fuels, and what are we getting in return? How good is that? I'm going to bring on, in my case, nuclear war through nuclear power. Wait a minute, be careful. So I think admitting that there are problems that make this not a slam dunk, you've got to you're learning as much as you can to bring a priority into a discussion with other priorities. Again, that's part of what our bulletin doomsday clock forces on us every day. So I think if we just work harder at being honest, explaining that we're being honest, it's not taken for granted that we'll be honest, as it is with anybody else. We have to earn trust, and we just haven't found the mechanisms for doing it adequately.
So let's talk about that a little bit more, because there's the field is well aware of the the importance of this science and in compiling it and trying to record it in a way that it can inform each policymakers, if not the public. And I'm thinking here in particular of the IPCC exercise that we're now gearing up for the 6th or 7th round of. So has that not done the job of portraying climate science both and communicating both its value as well as the uncertainty and the need for further research?
Well, IPCC, which most of the listeners here knows, is the Intergovernmental Panel on Climate Change. It produces the best global summary of all the global scientists' efforts, emphasizing what's learned in an interval. The interval is about 6 years, and we're on our 7th round right now. There is a norm within the IPCC which really has troubled me for a very long time, which is that the rule is that you're supposed to report consensus and not disagreement. Now that you'd have a much better feel for whether that's damaging internally, but I think it's damaging externally. And when I know of a field, when I probe a field to understand what's going to happen, the Atlantic meridional overturning circulation, people don't know for sure. And there are often two camps. And there are two camps this happens in science all the time, and eventually some experiment is done, usually an experiment that but it takes a long time. It picks one over the other. But at a given time, there's very creative conflict. When I started before I went into this field, I was involved at the very beginnings involved in the sense that undergraduate or graduate students involved. Two theories of how the Big Bang was under challenged by something called continuous creation. Fred Hoyle was somebody I was fascinated with, was an exponent of that. He was seriously contending with Big Bang until the measurement of the background infrared radiation, and then that pinned it down because it was clear we could put the whole picture together. Not every tipping points may not be vulnerable to that, but some of the questions we may get that kind of insight. A key measurement made in the oceans that helps understand AMOC. Why aren't we willing to tell the public that we don't know stuff? Or am I off base here, Nadir? You can tell me better than most people can.
Yeah, I mean, I think AMOC is the Atlantic meridional overturning circulation is a great example where I think if someone were to Google it, the different things that would come up would be very confusing, because there's a whole array of not just literature, but articles and messaging and people opining about it, and the IPCC does treat it. I mean, the last IPCC report from 2021 has, in a couple of different places, tables of tipping points. But it's interesting. There's something about the framing where, if it's something like AMOC slowdown or shutdown, they'll describe it just in terms of low confidence. They'll say, okay, there's a possibility of some AMOC slowdown by 2100, or significant slowdown by 2100, parentheses, low confidence. And that's true. And
low confidence isn't the same as saying it's bimodal. There must be times when scientists are pretty sure of either of two things with good arguments on both sides, can see the other side could be right. And that's not low confidence. That's high confidence in two competing alternatives. And that's real. But we hide it.
I think there's some truth to that, Rob, that I don't know that I'd say it's being hidden or deliberately. Maybe it is. I've not participated in the process, but certainly, saying low confidence doesn't tell the full story of what's happening in the science and between the scientists.
Yeah, hiding may be the wrong word. It feels deliberate, but it is embedded. It is an accidental consequence of a belief that somehow the public can't handle.
Yeah.
The next word is usually the truth, but the public can't handle the complexity of an interim state of affairs.
Yeah, and it's interesting actually because just this. In fact, I think so some oceanographers have actually organized. They've gotten organized around this issue. One of the leaders is Graham McGilchrist, who was on this live stream last year. And they organized a series of webinars, 4 of them with 2 speakers each, kind of presenting differing points of view on the AMOC. And I think that was taking place over the last month. And these are, broadcast. Anyone can, could join the webinar and listen. And then I believe they're having a workshop.
So is AMOC an example where right now it is a bimodal distribution of favorite theories?
I mean, it's not my field, but my perception is, that maybe that's an accurate description. I do think there are scientists who, feel that they are seeing, so-called early warning signals or what they call.
There's nothing wrong with that.
Sorry?
There's nothing wrong with that state of affairs. I think the public could get, maybe, it's just one of many suggestions we're going to need. One of the ways of getting the public to sort of relax and enjoy this exploration.
Yeah. Well, and I think, it's interesting that, I think this effort that these oceanographers are taking part in, will help kind of bring this to the fore and kind of bring it out into the open. So, these uncertainties and disagreements won't be, in closed door session at the IPCC, but I think they're having workshops, they'll write reports, they're having webinars. This live stream is obviously bringing science out in a way that climate science out in a way that I certainly haven't seen in my career. So, maybe we are beginning to see a bit of a community response and
I'm also worried about insider baseball. Do we need to give some idea why you and I care about AMOC? It's the ocean currents that actually determine that Northern Europe is as warm as it is. It'd be a lot colder if those currents shut down. They really could shut down, and so we're talking about the livability, not the habitability, but the livability of Western Europe being at stake in some sense, and a plausible way in which you get from here to there.
Yeah.
Would you add to that? I mean, saying AMOC is without saying what it is.
Yeah.
We shouldn't be doing a program.
No, I think that's great. There's a couple of other topics I want to get to, and I also want to leave time for questions. And so I think this is sort of related to what we've been talking about, but in a 2020 essay, you describe yourself as a witness for the middle. I think it might be interesting for this audience to have you explain what that means and what does that imply for climate science?
Well, it's another witnessing the middle is looking for common ground, never treating the person who doesn't agree with you as an enemy, always trying to understand where they are, building coalitions. We don't do enough right now, in particular in the U.S. We don't do that very much. We're perfectly happy with 51-50 votes in the Senate, and then 2 years later it goes the other direction. And many other countries, some other countries, Australia is an example, have a similar story. We shouldn't allow that. We need to understand each other to the point where, say, at least 3/4 of us say this is the right move for now. And that means giving some stuff up because it will last longer. You're not going to get investments from the business community if they think that the policy that makes it profitable will be withdrawn with 50% chance, let's say, over the next 5 years. So it means, first of all, building the middle, I think it involves conceding that the science is making visible that the science is imperfect, but the science method is working, because people really need to be reassured of that. Then it means that we concede that climate change is not the only priority, as I said. And then the third is that we concede that the solutions we have available are not terrific. They all have their problems. If we're going to run the world on solar energy, that's a lot of invasion of land. If we're going to call upon nuclear power, I feel myself that it's going to increase the chances. The countries will build nuclear weapons who are enemies of each other, and there'll be nuclear war, which may not be able to be contained. It shouldn't happen in the first place, but could be, in fact, globally significant wherever it started. So if we talk that kind of straight, my experience is people want to talk to you. They don't feel put off. I think this group, Livestream, is doing a good job of not putting people off, not being strident. But I feel it needs third-party validation. Now, it should be that business community is endorsing this group. It's the younger people, it's the next generation of climate scientists saying, we're scientists, we're getting something straight. They don't say, because they really are, they don't say enough, but others really need to say it for them. What we're doing is terribly important for all of us. That is the missing part of the message at some level that should be said by business leaders, by government leaders, by NGOs.
Is some of this perspective informed by, together with Steve Pacala, you ran an institute, the Carbon Mitigation Initiative at Princeton for many years, that was actually funded by BP.
Right.
And
there's been a reversal in the view of whether oil and gas and coal companies can become part of the solution to climate change rather than made to disappear. There is a technology called carbon dioxide capture and storage. When you burn a fossil When you burn a fossil fuel, it's a second decision to have the CO2 go to the atmosphere. It doesn't have to. It can be captured in the smokestack or various variants of that, put below ground again. It's more expensive, but it's a circular economy for carbon. I've been fascinated with it in part because the fossil energy industry then has a job to do that they can be paid to do. There's a subsidy for not emitting carbon dioxide and a penalty for emitting it in a new policy. We don't have to exclude them. I've gotten a lot of flack in the last few years as people have changed their minds, and the industry hasn't made it easy. They've changed their minds about whether we could make, if that worked, we'd want to have it anyway. I think we need to keep it, that option open. So the polarity, the polarization between those who are climate activists and the corporate world is not going to help. We need the corporate world. We can't do this all with, well, let me say this. I have watched in my career one version or another of, we don't need to worry about this problem. It's going to solve itself. Nuclear power was going to be too cheap to meter. Then a colleague of mine in geosciences became quite famous for saying, we're going to run out of fossil fuels. We won't burn them for long enough to actually drive the atmospheric carbon dioxide very high. His name is Ken DeFace. He got lots of attention because people wanted it to be true. But he was using an analogy with that didn't include unconventional fossil, which is now all over the place. Shale gas and shale oil, for example. And we may be doing the same thing with renewables. I hope not, but really could be. Others think, look, we'll have behavioral change. We don't have to consume so much. Yes, we don't have to consume so much. But we better not put all our eggs in any of those baskets. And one after another, we're trying to talk ourselves into not having a problem. The public sees that and they say, well, I guess I don't have to worry about it if they're not worrying about it.
Yeah. Getting back to the state of science briefly, and then I want to maybe turn to questions. So you mentioned the, turning back to the science, you mentioned the International Geophysical Year and Sputnik being a part of that. And you were a young person.
I watched Sputnik as a junior in college from a bridge over the Charles River at 8 o'clock at night. You have to have the sun hitting the Sputnik, but the sky dark. And it was unbelievably exciting. It wasn't just exciting for me. It was exciting across a lot of countries. Whoa, look, and Russia can do this. And actually, we can't quite yet. And we have been very casual about our science. I didn't learn calculus in high school, and neither did almost anybody I knew. And we've had very little reform of curriculum. 2 years after when I started graduate school, a lot of change was happening in the high school curriculums in chemistry and physics and math with a real intensity. And then I was made aware by the country that they really wanted me to stay in science if I was at all inclined to. And I was not that committed. I was pretty committed. But when the government says, we want to give you a pre-doctoral fellowship, and in my case that, and a postdoctoral fellowship from the National Science Foundation, I was eager to get on my own money and not depend on my parents. And this was a big plus. And there was the draft board was saying, you're definitely going to not get drafted if you become a graduate student in science. If you're in history or English, well, maybe, but maybe not. It was a tremendous oomph, a tremendous shove, if you like, toward working in this field, which I wanted to do anyway. We're in an anti-Sputnik moment right now, where exactly the messages that I was getting are inside out. Well, we can do without you. It baffles me that we would be getting to that point, but I recognize it as so different because I was the beneficiary of this endorsement of the fact that we needed to get things straight and use the scientific method to do it. So, have I answered your question? And your career, you changed fields too. What kind of it was partly an ethical pull, if I'm not mistaken, that got you from working on some very interesting basic physics questions, math and physics questions, to going into this stuff. How would you describe your conversion?
Yeah, literally. I mean, I was, theoretical physicist in graduate school in the 2000s and late 2000s and early 2010s, and these problems were on the front page. And I was a TA for a graduate course that, or I was a TA for a course that, you know, kind of opened my eyes to the ways that physics was the underpinnings for renewable energy technology of every stripe under the electric grid, climate change, nuclear energy, and then the idea of just, you know, applying the physics that I knew and loved to these front page problems was exciting. And
you're spending a whole bunch of your time borrowing it from the time you do basic science with this communication objective.
Yeah, I mean, that seems, that's right. I mean, when doing science that, you know, is on the front page, then you have to ask yourself whether you're comfortable just focusing on that or whether you want to have some impact on the broader context.
You and I both have worked, I don't know if we're running out of time, but with the American Physical Society, the community of physicists, which includes lots of people who really wonder if this is straight science. And you have to be confident you can explain to the lab that you work in, and that's a neighbor of mine, geophysical fluid dynamics. I've known it since almost its beginning. They really emphasized over and over again, we are going to be credible in science. We're not going to let anything get in the way. If it's a hot potato and doesn't really have a core of science, let it be. But get the science straight. I mean, we have these amazing models that came out of their insights into the first coupling of ocean models and atmospheric models and things like that, that I'm just so proud of being next to it.
Yeah, it's a phenomenal place. And, you know, I gave a talk last night on this live stream trying to tell the story of some of that science. You know, certainly in the, you know, for modelers, you know, it's, I mean, there's so much nitty gritty. I mean, that's true across our field, but there's so much nitty gritty, and folks who I think who are drawn to modeling, you know, are often happy to keep their heads down and, you know, and work on that nitty gritty and get these models to run and to develop them.
No, there's a set of places where the physics, where the climate science is unclear, and the people who want to challenge climate science, for whatever reason, sometimes characterological. They like doing stuff. They like being challenging consensus. They have some things to poke at, right? We aren't done. We've got weaknesses in the program. You're dealing with them at the American Physical Society now. You're trying to figure out how to get an exercise that does justice to the state of affairs, so that at least the people who want to be informed about whether these challenges are at all well-founded or not can get a grounding and get a good grounded answer. I was involved with that a few years ago. You're involved with it now. Some of it's very, very difficult, but first of all, conceding that we don't have everything straight yet is pretty important. Talking straight.
Yeah, that's right. I think that's part of the challenge, is how to convey, you know, our certainty in the things that we do know, while also being honest about what we don't. And you know, there's folks who've been climate communicators for a lot longer than me, and you know, I think in the past they've the community sometimes felt a need to sort of circle the wagons, and you know,
yes, that's exactly what I think it does not work.
Right.
We haven't tried this out on you, but there was a period when the cirrus clouds at the high altitude, which actually warmed the planet, we're going to get more. We're going to disperse, and that would be a negative feedback. That was a favorite. Is that still out there as a possibility, or have we nailed it down more?
The potential cirrus clouds feedbacks, I think we understand those better. I think
and what would have been nice to have this negative feedback, it isn't really there.
Correct. It's not really there.
So I mean, that's what we need to tell that story, because it was very prominent among the naysayers that, look, we could get, here's an escape, and we don't know if it's true. And it was, the model had the idea had a name that I'm missing right now.
Yeah.
Some things are not gotten resolved yet. They're still there. They could be reducing the rate at which we're going to see stuff. We can pin them down. We pin down the cirrus clouds, I guess, with a lot of measurement, satellite measurement, maybe, as well as ground-based measurement, and got models of the clouds. I'm guessing now. I'm looking at you. Something of that sort.
Yeah, no, I mean, you know, we've made good progress on some of those things. Cloud feedbacks in particular in the last 10, 15 years. You know, I think we know them a lot better. but still means issues that we've been discussing are uncertain. And yeah, not all of that has been communicated, kind of broadly.
My message to the young people is stick with your science. Be sure you're explaining the science as fully as you can. What makes you excited about it? What we really do know, pretty nearly, very high confidence, and then what you're working on, which is probably what we don't know so well, and why you're working on it, and that we are possibly going to get that one pinned down.
We are at time, and I do want to take maybe one or two questions if there is time. Margaret, I'll leave that.
I thought you would jump in if you had a question you were going to throw at us.
Just really quickly, is there a stigma within the scientific community against people who have degrees but who are not currently researching or working for an organization? I wonder if citizen scientists are taken seriously. So maybe you can comment on citizen
science. I hope
science.
the answer is it depends on what they have to say, not with who they are. That would be my answer. You always want to hear from somebody, no matter whether they're out of work or they never worked in the field, but just been doing it as a hobby. They may have an important idea. Bring it on. One of the most important things about science is the idea does not depend on who presents it.
Yeah, and there's examples of that. There's someone named Nick Lewis who's been very critical of, some of the literature, but he submits papers. They get published in the same journals. He shows up to conferences, and there's a dialogue. Richard Muller, I guess he has a position, but he was also, somewhat outside the field in physics, but decided to engage and ended up putting together a surface temperature data set that was independent of the ones that were already there. And that was controversial at the time, but I think in the long run, it has strengthened our field.
And in that case, when he found out that what he thought we might be exaggerating warming, he found out we didn't. And they wrote that up in the Wall Street Journal because he had gotten people who read the Wall Street Journal hoping that it would turn out that we weren't warming the planet. And he had to say, look, let me set it straight. Thought it would. I was not convinced by what I read. Now I'm convinced by what I've done.
Yeah.
That's the way we should be working.
Yeah. So I'm worried about the time. Thank you so much, Rob and Nadir, for this great conversation. This has been really interesting. And let me just remind our audience why we're here. And I'm going to go off script a little bit here and play off of what Rob was talking about, and remind everybody that during the Cold War and World War II, physicists and chemists were so important in America in the development of Los Alamos and Lawrence Livermore and other research facilities to develop nuclear weapons as part of the Cold War. And that was a really important thing for national security. And that really highlights the importance of brain gain over brain drain. And obviously climate change is a different kind of problem from the arms race that we were experiencing back then. But the benefits of having brains on our own soil and having this research happen right here, federally funded, is still there. I think, in the face of one of the greatest challenges that we've faced as humanity, do we want to be reliant on other countries for their estimates? Do we not want to be studying it? I think that we do, and that's why these federal funding cuts are, in my opinion, so scary. And so I really hope that you'll consider contacting your representatives. WCLivestream.com/act has a nice script for you. And feel empowered that we as Americans get the opportunity to contact our representatives when we're worried about something. This is something that I'm worried about. This is something that I know all of our speakers are worried about. And we have this great opportunity here in America to speak up about it. And so that's why we're here, in addition to just hearing interesting science talks and getting to share with the public what it is that we think about every day. And so with that, let's bring on Jared Rennie to talk about Show Me the Data. Take it away, Jared.
Yeah, thanks, Margaret. I am also going to go off script for a second here because you were talking about the importance of sort of science and how it was, very beneficial for things, in World War II and the war and the Cold War and such. And I mean, first off, 100% agree there. Also, for those, we're recording this, just after Memorial Day and right before the anniversary of D-Day. And there's literally a movie out right now called Pressure. And the movie is about basically the forecast for D-Day. I literally have the book in front of me right now. And, you know, how, for those that don't know, D-Day was supposed to happen on June 5th, 1944. But I don't know how good this is coming in. I'm literally winging this right now. But, you know, talk about the synoptic weather map on June 5th, 1944, how the weather was going to be pretty terrible on the beaches and the surrounding area. So they decided to move it a day to June 6th. And it was all because of the weather. And now looping in to sort of my talk, the importance of the data that goes into these things, you know. So, you know, modeling's great, forecasts are great. But, you know, I think Rob said earlier that, you know, you got to be passionate about something in the science. I am so passionate about data. I will not stop talking about data. You all have only given me like 10 minutes to talk about data, and I've already wasted 2 minutes. So, so this title is called Show Me the Data. I did give something similar at last year's live stream, but I have updated it for 2026 style. If you were on the stream last year, I made everybody yell like Jerry Maguire, like, show me the data. Like, I'm not going to do that today. I don't have the energy for it. But what I am going to do is I'm going to kind of first point out that some of you might be like, wait a minute, don't you work for NOAA? No. I do not. No, not right now. Right now, look at this very important thing here. It says, I am a private citizen. I am here. It is after 5 p.m. I am home. I am here as a private citizen. Please keep that in mind. All right. So some of you may have seen this secret building in Asheville, North Carolina. It is called the National Centers for Environmental Information. Not part of them, private citizen. They do three things. They archive environmental data, they make pretty graphics, and they tell you the Earth's climate is bad, very bad. So the data is important to tell you all that. They have lots of data, petabytes of data, servers and farms of data. The forecast by the end of this decade is going to indicate that we're going to have, you know, hundreds and hundreds of petabytes, and we're probably going to go, it's exponentially increasing because of all the satellite data and the reanalysis data and the modeling data that NOAA and other entities provide. Basically, if it's scientific data that you use in your projects, NCEI archives it. My motivation is that accessing their website is not the greatest, I'll be honest. It can be a little bit confusing. You may not know where you need to go to get the data you need. And then also once you get it, you may get it into a format like this, which I know what this looks like. This is actually, I think this is airport weather data for Columbia, South Carolina. But some of you are looking at this probably going, are we in the Matrix? So my motivation is to try to take the data and making it a little bit more actionable. And there's great examples out there from all different walks of NOAA. But what I specifically do is try to find ways to make NOAA data available and visualize it. And I think the important piece that some folks have already talked about is to telling the story, you know, making it local. I am a computer programmer at heart. So, you know, most of my time is I'm writing code in Python. I'm posting on GitHub. I'm making all these notebooks available. I'm tapping into like JavaScript web features and AWS and Google Earth to be able to provide these data to whoever really wants them. I mean, it could be from a scientific perspective, a university may want it for a project. It could be a TV weather person that wants to know, you know, put it into their graphics for their, you know, 6 o'clock or 11 o'clock news. So my motivation is to make many different products that have very good scientific applications like this one. I'm going to announce right now, there's a website called isjaredmiserable.com. Again, very, very scientific, very peer reviewed, very much on actual data. You can go there right now and you can find out if I'm miserable. I took these screenshots last night. I was miserable then. If you go now, I'm not miserable. I'll give you a little hint. It's not the heat, it's the humidity that kills you. But there are lots of features in there, web features, plotting features using NOAA and non-NOAA data to basically tell a story. And this particular story is if I'm miserable or not. But there are more important stories to talk about. And that's kind of what I want to talk about for the remainder of my time. So I have 3 bullets here. 3 things I need you to remember. Oh, sorry, this is actually the 5 bullets that no employees still have to give to their supervisors. Sorry, that was a mistake. We actually were told this morning that we don't have to do this anymore. So just know that folks were still giving 5 bullets to their supervisors for the past year and a half, but don't worry, we don't have to do it anymore. So back to my 3 bullets. Okay, first bullet, the data. The data is so important. Yes, it's great to make the modeling better. Yes, it's great to make the resolutions better. Yes, it's great to make visualizations better, but it's all really reliant upon the underlying data. We archive it at NC, or they archive it at NCEI, and lots of folks use it. So obviously within the past few months, there's been, questions about the observations. The one that got sort of high traction over the past few months have been the upper air observations. I know the Weather Service is working on this, and this is certainly an issue, but we all must remember that this isn't necessarily the end all be all. There are other observations out there that are, a few decades old, like the Cooperative Observer Network or weather stations at airports. They're also having issues getting upgraded and being reformatted and such. And this is all important. All this data is important. You think about the radar network. The radar network started in the late 1980s, early 1990s. That's already, the first problem is that it doesn't do the greatest in mountainous areas. But also it's also a infrastructure that's a few decades old. So that's something else to think about. We also have to think about the satellites. The GOES-R program was super successful. They're out there, providing data at every minute. But we're always thinking about the next mission. So far, according to current budget looks pretty good for the next geostationary orbiters that are going to go out. That's called GeoXO. But then we also have to think about our polar orbiting satellites as well, that there are, some issues with that. And then I think there's some funding issues with that. I'll let you all go check those another day. The second thing you need to know is that there is good in public-private partnerships. Not always, but there are some really good examples out there. The best example I can give you right now is this data set, the $1 billion weather and climate disasters that NCI had produced up until, a year ago for reasons. So our friends over at Climate Central said, hey, we can take this on and do the same type of analysis. So Climate Central is now taking this on for 2025 and onward, and they're making it better. They're thinking about $100 million disasters, different types of disasters that can go into it. That's a really great example of working with private companies to kind of supplement what NOAA does. Speaking of private companies, AWS, Google, Microsoft, they have all the data in the cloud. NOAA has something called the Open Data Dissemination Program, which is super successful. A lot of the radar, satellite data is in the cloud, very easily to be accessed. And and it's all out there for people to get. It's a lot faster than going to the NCI website, I'll tell you that. And you may have saw that NCI just announced that they're completely going into AWS. So, the entire suite of products and the entire services and the websites and everything, that's all going to be converted to AWS. So stay tuned for that. And then the third bullet, and this might be a little controversial, but if you know me, I can get controversial. When it comes to AI, I, for one, welcome our new AI overlords. I absolutely don't have time to go into deep detail about this, but all I want to say right now is that AI can be used as a tool. There's like 500 bad things about AI, some that are really bad, but in our field, there's like 2 really good ones. And how can we harness that as we move into the future? So these are just some quick examples using AI as code assist. If you have legacy code that's 40, 50 years old and your boss left the institution for, reasons, and you wanted to better document it or upgrade it, AI can certainly help with that. You can also build chat bots based on the data, and you can say, hey, I'm having a hard time getting snowfall data for this event. Maybe we can throw it at a web JavaScript tool and say like, hey, give me give me the top 10 most snowiest days on the record based on this data. And it can pretty much spit it out for you really quickly. This is just another example for our storm events database, which is currently being upgraded. I know I blew through a lot of that pretty fast, but as you can tell, it's my motivation is to get people access to data a lot faster so that they can make the decisions that they need. You think about, we have something called the industry proving grounds, where, you know, we take data and we give it to insurance companies, reinsurance companies, retail, and infrastructure, architecture. You know, they all, you know, regardless of what people might say about climate, they know that that data is important to help their infrastructure and building stuff that works for the next 30 years. So it's our motivation to get data to the people. I have a GitHub page if you're interested in looking. If you are a computer programming nerd like I am, you can find all these different notebooks that are in there. These are ones that I've built since my last time on this live stream, getting data from NOAA and non-NOAA data. So USGS data you can get. We have some fun ones in there, like probability of a white Christmas or a white Thanksgiving or a white Halloween or whatever. We have gridded data in there. We have the ability to convert data into like other formats, so you can load them in Google Earth or shape files. And then again, if I had another 10 minutes, I'd talk about heat thresholds. That's a whole nother passion of mine. But those are just some examples you can go take out right now. There's a little button there that you can go see to launch data. It's a notebook, so you have to know a little bit of Python, but we try our best to get it so that you don't really have to install anything. So I know I'm way over and way out of time, but thank you all. And I'm here if you have questions. But yeah, show me the data, baby.
Thank you so much. That was an awesome talk, and you got a lot of love in the chat, in case you didn't know. We have a question. What excites you most about the transition to the cloud? From all things Pi.
There's the thing about the cloud is, again, kind of like AI, like there's a lot of things that aren't the greatest, you know, because there are issues with like the private companies and who owns the data and things like that. I think for me, just better data access. I mean, the amount of times I'll go to a website and I will pick on NOAA, but it's not just NOAA. Like NASA and USGS has this problem too, where, you know, you want to get the data, but it might be down. It might be doing maintenance or something, or there's a reboot of a server or something, and you can't get the data. But I mean, with Amazon or Google, most of the time there's very little downtime. I say that, but there was a day in October that I won't talk about. But other than that, like better data access and better ways of just visualizing the data. You know, can we put it in better databases? Can we throw it at Esri to make mapping stuff? I didn't say this earlier, but that website I did build, the Is Jared Miserable site, like I built it myself. I call it my night and weekend job. And, you know, building the web stuff and JavaScript and all the stuff, it's 100% at AWS on my own personal account. Again, weekend job. And it cost me $1 a day to do it. So, I mean, there's certainly a lot of power in it.
That's awesome. Yeah, thank you so much. I think it's time to move on, and you're getting a new host, y'all. Let's introduce Haley. Hi, Haley. Welcome. Thank you so much for taking over here at hour 20. We've just wrapped up hour 26, I think, moving into hour 27 of the live stream. So I will let you take it away.
Thank you so much, and hope you had a great time hosting. I am back. Yes, thank you in the chat with a very red light. Sorry about that. So super excited to be back on the stream, back from work, and see a bunch of familiar faces in the chat again. So awesome to see you all. So just really quickly before we go to our next speakers, which I'm really excited about, we are now in the keynote section of tonight's stream also. So these will be slightly longer talks than we have been having for the past, since last night, the past 24-ish hours. But just before we get to that, really quickly, just reminding us all while we're here, the short answer is to go to the link at the bottom of the stream, wclivestream.com/act, in order to contact your representatives around 3 main things. So first of all, the administration's proposed budget, which decimates and in some cases halves funding for federal science in climate and weather across different agencies. It slashes programs for training young scientists as well, which is how most of us on here got here. We also want to protect NCAR, the National Center for Atmospheric Research, which is currently, they're attempting to break it up. And then lastly, we want to reject the proposed rules by the Office of Management and Budget around federal grant making for science. So please take a second, call your representatives, write them a letter. If you write a letter, it'll be delivered in person tomorrow at a press conference, which we're really excited about. So please send in your letters early and call your reps now and often. So with that, I would like to bring up our next speakers. So we have two people joining us, which is amazing. Faith Kearns. Hello, welcome, and also you know and love Virginia. Faith is a scientist, communications expert, and a strategist, and Virginia is a science communicator who makes media, trains scientists, and studies how we talk about science. And so they are going to take over for the next 40-ish minutes, and make sure you put your questions in the chat. So thank you all so much.
All right, well, let's see here. It's going to take me a second to figure out this arrangement. Just give me a sec here. Slideshow. Ooh, no, not that one. All right, I think I got it. All right. Well, hello, everyone, and thank you to Virginia for inviting me and being an encouraging face for the first little bit of my presentation here. So I'm going to talk a little bit about a climate and climate adaptation issue, which is an interesting one, which is about when wildfire meets water system supplies infrastructure. A lot of people will be familiar with this issue from what happened in LA, but I'm going to give a little bit of the backstory and kind of where we are with this very, very emergent topic. So let me see here. How do I advance? I'm not even sure. Okay. Well, am I advancing my slides? Let's see.
Looks like you should be able to, Faith, but I don't see your presentation settings, so I'm not exactly sure how.
Yeah. Oh, maybe I can just do it this way. I see. Okay. So let me see. Got it. Okay. So I think, you know, pretty much people are familiar these days with the fact that, you know, climate change is really fueling a lot of wildfires, particularly in the West, but really all over the country and all over the world. And this particular issue of what we're calling urban conflagrations is also growing. People, again, may be familiar with the concept of the wildland-urban interface. It's a term I don't use very often because I find it confusing and not that useful. But what we're really finding is that fires are sort of moving into urban areas and causing some really interesting and difficult challenges as that's happening. And I just want to give a little bit of a backstory on why this is even an issue. So I have been working on wildfire and water issues for most of my career for 20, 25 years at this point. And when I first started working in wildfire, this is a picture from a community wildfire day in Northern California. We used to do these kinds of things when I was working at a wildfire center at UC Berkeley in the early 2000s, kind of go out and show residents of a local area what would happen to their various, home surfaces if they were to catch on fire. So this is an example of showing how siding might burn during a fire. And the really interesting thing was at that time when we were thinking about water and wildfire and particularly structures, we were thinking about how to protect houses from burning down. So doing things like screening your vents so that embers don't get into them. But also you have to be really careful to not have your house retain water, right? So it was already this really delicate balance of just how do you build a house that's both fire resistant and not gonna be full of mildew and mold, right? And also at that time, people were working quite a bit on sort of how fire affected riparian areas, streams, things like that. A lot of this work was done by ecologists and foresters and fire scientists. And so that was really the extent of kind of how we were thinking about wildfire and water up until fairly recently. So the thing that really changed things was the 2017 Tubbs fire in Santa Rosa, California, both in the sense that that fire came from a wildland area into an urban area and actually ended up jumping the 101 freeway in California. I was actually in Santa Rosa the day that fire started. I was actually giving a talk on how to talk about difficult things like wildfire to a bunch of folks that were training to be California master naturalists. And I remember standing in an area very close to where the fire started and had that feeling that's extremely familiar to Californians. The wind was blowing in a particular way. The temperature was so, and it definitely felt like a fire could start. And as I drove away about 2 hours later, I learned that that fire had started. And the thing that was kind of wild about that fire in particular was that it ended up being really the first very well-known example of a wildfire directly burning water infrastructure within city limits. And so what ended up happening was it melted some PVC piping that's pretty common, and it ended up with a lot of benzene in the system. And so at that time, I basically kind of thought, well, this is a whole new, frontier in terms of this water and wildfire issue. And because I had worked on both things, I ended up applying for a project to try to figure out what do we even know about how wildfire and water infrastructure really interact. I do want to say before I get too much further, because I think we're getting into really tricky territory where there's a sense that fire and water should not ever mix, right? But that is not the case. These are some photos from after the Camp Fire, which is a one in 2019 in Paradise, California. I toured stream in Big Chico Canyon with Don Hankins, who's a fire scientist at Chico State. And he was showing me all the beneficial impacts of fire to these sort of natural stream areas. Very different than in town, where basically the fire had burned things down to their foundations, homes and buildings. And even the smell of these two places was so different, even though they were maybe 10 miles apart. So I just want to make sure that people don't take away that fire should never touch water, because that's absolutely not the case. But when it comes to infrastructure, that's a whole other thing. So with this project that I applied for in 2019, I ended up working with a colleague at UCLA, Greg Pierce, to write this report. And there just was almost no information on this topic in the academic literature. We ended up pulling together a very transdisciplinary group of practitioners, researchers, from all sorts of fields to even try to figure out what we know about this issue, right? And I remember sending this report to a few reporters. There was one who was semi-interested. The others were just sort of like, I don't get it. What are you even talking about, right? But of course, the 2025 LA fires happened, and that sort of changed everything. It turned out when you search for this topic, our report was basically the only thing that was showing up. And so Greg and I were fielding calls from reporters all over the world about what happened during this really devastating event, which if folks who weren't following that closely, there was a huge amount of focus on the water system and how hydrants had failed during those fires. Water wasn't getting where it needed to be. It turned into a very large, sort of political issue. One of the things that came from that work was, luckily for us, UCLA stepped forward and supported a ton of work over the last year, really organized by the UCLA Luskin Center for Innovation, and with a working group that includes me, Greg Pierce, Edith de Guzman, and Eric Porce, plus a bunch of other people. But the four of us are really pursuing this core of research on this topic. And so we've been able to do some really, really interesting things, one of which is to really try to inventory this issue and say, this is not just in LA or even just a California issue. When you really start to probe, these things are happening all over the place, including in New Jersey, just recently in Alabama, the places that you wouldn't even be thinking that this is happening, it is happening. This is an article that I wrote in High Country News just about a fire at the Grand Canyon that actually ended up basically blowing up a water treatment facility, some chlorine water treatment tanks ended up exploding during the fire. It meant that they had to stop fire suppression activities in the area because it's so dangerous. They had to evacuate a bunch of hikers from the bottom of the Grand Canyon. So this is really like an issue that is both incredibly emergent, that we're sort of just on the edge of even figuring out, what we should be doing here. And so the workshops we've been doing have been super helpful and allow us to do things like really look at, how many places is this happening? Greg led an issue brief on sort of looking at this concept of what happens when the hydrants run dry, because it really was an interesting narrative from the LA fires that didn't pop up so much in some of the other events where this had happened, including in Colorado and Oregon and other various places. So again, I just really want to stress that this is not just a California issue, which I think we can sometimes think when it comes to wildfires in particular, right? And so some of what we're finding that I'm particularly interested in is that this issue really requires both social and technical approaches. And so I've been doing some things like there's a really interesting fire chief in Lake County in Northern California who actually has been very progressive about this particular issue. And a lot of it comes down to the fact that he is a fire chief who grew up in the county where he is now the fire chief. And many of the folks that he works with also grew up there. And so he's always had like pretty personal relationships with water managers in that area, and they've been able to establish a committee on water and wildfire, bring water managers into their incident command, all sorts of really interesting and progressive stuff. And so I think that's something that we're going to see. And then the other issue, just because I am a communications expert, is also really looking at communications as a real sticking point on this particular issue. And so one of the first workshops that we've had a series of 3 that again have been these very transdisciplinary workshops by necessity, because this issue is not fall into anybody's own silo or kind of work. It's water utilities, fire departments, which by the way, usually do not speak to each other at all. And so trying to even get them in the same room has been really challenging. And so for the first workshop we were really just sort of focused on like getting a handle on this issue. And it was fascinating because there were about 40 people there, and communications came up over and over again as like, we need to communicate better about expectations around water systems. We need to communicate better about almost everything that you can think of, and as somebody who does communications work and really understands the limitations of communications, I was sort of sitting there going, this is so interesting that a bunch of mostly non-communications folk thinks that this is a communications problem, right? And I do think there is a communications component to it. So we ended up having another workshop focused just sort of on the communications issues, which sort of had a dual track, one of which is just this concept that is pretty well developed around trust in public water systems, and the fact that there's already a lot of mistrust. Think of the Flint water crisis, think of all sorts of issues. People have problems with the smell of their tap water, all sorts of different things like that. And so this is already sort of this background issue of general mistrust in institutions, general mistrust around tap water anyway. And then, the disaster piece, which also has another component, which I think we're all feeling a little challenged by these days, which is just how do we communicate during disasters in general. Twitter used to be a really great place to do that. And increasingly it's not, and there's just a big confusion, and I would say a little bit of a void around how to do this, right? And one of the main challenges when it comes to water is that there really are 2 different systems, one of which is governed, right? So there's a formal regulatory system where regulators, utilities, all have to issue official notices when there's a boil water or a do not drink notice. But a lot of times they just push that out, right? There's not a lot of what we would call two-way or multi-channel kind of communication. It's just sort of like, we have a boil water notice. And then there's all these informal systems, which many of us probably get most of our information from these days. It's, you know, basically through our peers, whether that's in person or various kinds of social networks, right? And so you really see that, like, in that system, it's all shaped by sort of relationship and connection, and it's very networked. It's almost the total opposite of what's going on with the formal system. And so those two things can kind of get in the way of each other in a certain way, right? And so you might kind of, yeah, so there's an official notice and then there's what happens with it. And that's the part that's getting really messy, right? Because it's sort of like talking about, how do people actually get information during disasters? And it really is from your friends, your family, whoever you run into. If you're in a disaster situation, a lot of times even your phone isn't working that well. And so many of us have probably seen over time that, you know, within the first couple hours of a disaster, social media gets pretty polluted. It's very hard to find the latest notice. So you may be seeing something that's a day or two old, depending on how an algorithm is giving you, you know, information. And so, yeah, so it gets really, really, really messy. And so the idea that people, yes, there are formal notices coming out, but then that people are, then what happens to them? Who even knows at this point, right? And this is part of just our overall communications landscape right now. So this is just an illustration to sort of show that, you know, 20 years ago, we already had a pretty big social media ecosystem, but it's almost nothing compared to where we are now, right? The latest graph that I have is of 2018, which now has to turn into this thing where you can't even see the words on it. It's so sort of disjointed and multi-level. And, you know, I haven't been able to find one that's updated for this day and age, but certainly, you know, thinking about the way that AI summaries are changing search, and you really, most of the time, yes, I know there's a nod to sort of like giving information sources, but most of us aren't necessarily clicking those. It's not totally obvious where information is even coming from. So we really are in this very fragmented and constantly evolving communications landscape where people are getting their information from all sorts of different sources. You know, like, so you can get things on TikTok, Instagram, whatever. Again, you don't even know, was that from 24 hours ago? Is that from, you know, 15 minutes ago? There's a lot more focus on these private networks, right? So like WhatsApp, small text, you know, text chains, Nextdoor. I know in my area, I live in very rural Arizona. Most of my emergency information comes through Nextdoor, actually. I can't really find anything otherwise. And then there's just this overall issue that people don't trust a lot of the information that they are getting. And so this is just even harder when you're dealing with something like water and wildfire, where you might be getting, and this certainly happened in LA, very technically complex information about things like, you know, volatile organic compounds in your water, right? And those things all get really scary. People are, you know, trying to make decisions that might affect the health of their kids, their family, a school, whatever, right? And as this says, right, information travels faster than corrections, and that's something that we're definitely seeing be very complicated around some of these issues. Also, one of the things that I don't see in a lot of the existing literature is actually some of my own work. I wrote a book called Getting to the Heart of Science Communication that really is about kind of information as a sort of almost an aside to the human relationships that kind of shape what we actually think and what we know and what we trust. And so I think that that's kind of the forefront of where we could do some work, is really thinking less again about this information transfer, the deficit model, all the things that Virginia knows well, and just kind of trying to figure out how we actually get the right information to people during what are very tense, heavy situations, right? People are feeling stress, trauma, and they're very worried about their own literal lives, right? And so I think this becomes an issue where we really have to be sensitive about timing and where people are. And the thing that I keep trying to get across to people is information outside of the context of any relationship, whether it's with an institution or a person, almost doesn't exist. Like you may think you're putting information out, but if there isn't sort of a relationship to really hold that, especially when the information is really challenging, it's really hard to even figure out what we're doing, right? So the idea is to start sort of building that infrastructure before the event happens. So at this point, I just want to say thank you for listening. Again, I want to mention a thank you to all of our collaborators and then supporters. Primarily a lot of the work that we've been doing over the last year, which has been super productive, and which people can easily find on the internet, has been supported by UCLA and the UCLA Sustainable LA Grand Challenge. Sorry, all of the words are always hard to get together. And so with that, I'm open to questions, talking with Virginia. Should I turn my slides off? Like, I don't really know what we do from here.
I think you and I can start talking, and I think we can trust that the director will take your slides down for us. So
oh, there we go.
Okay. So Faith, there are some questions in the chat. I do want to get to those, but we have about 18 minutes before our time is up. And so for the viewers, Faith and I have been friends for a bit. We both work in communications and science communication. I also have worked specifically with fire. I was part of a fire science government group, and the team that I was on, our job was to connect the people who were doing fire science, because that is a whole field of study, is fire science, with the people who use the information. And that means everyone from local firefighting people to managers to private landowners. So there's a huge communication gap just between the scientists and everyone else before a disaster even happens.
Totally.
So I've been thinking a lot from the fire side about how communications work. So fire is a huge thing you touched on. You touched on water as a huge thing. And then you talked about the information environment. So I see questions about all of them. And I'm going to get to the questions in the chat, but I want to cover kind of a couple of the really complicated stuff about all those three things in case y'all viewers want to put more specific questions in the chat. I want to start with water. So someone in the chat was talking about, let's see, isn't the entire United States, including Florida, in a record drought? And the way that I learned about drought is that, because somebody else was talking about how it's crazy to think about somewhere like Florida being in a drought ever at all, because it's near tropical. And so it is getting a lot of rainfall regularly. And the way that I learned about drought is that drought is a combination of the natural conditions like rainfall and what happens to water and human usage and existence. Drought is by definition a human-centered interaction thing. And so, somebody else mentioned data centers earlier in the chat. And so Faith, I just want to get you to talk about the water landscape broadly. What's happening with water and drought and water usage across the United States? What are the big patterns? What are the hotspot issues and where are they?
Yeah, I mean, that's a big question, but what I would say is, drought is a confusing topic. I think colloquially people can have this understanding. It's just like, it's dry, right? And maybe that places like Florida don't ever enter into drought, and that's primarily a Western issue. But there really are at least, people have made attempts at sort of talking about different kinds of drought. So your basic one that I think we mostly think of is meteorological or hydrological drought, like lack of rainfall or just background very dry conditions. But there can also be, for example, agricultural drought, which I have argued in writing in public that California is almost always in an agricultural drought, because I think there's almost no time of year when some farmer wouldn't tell you that we're in drought. And that has primarily to do with water availability just for agriculture, right? And then we can have sort of what people would call sociological or socioeconomic drought, where people don't have water access in their homes, but that doesn't necessarily have anything to do with whether it's raining or not, right? So, and that's just one classification system. And then there are things that, like they call them flash droughts now, that places that are considered generally wet might go through short periods of like 4 weeks where it's very, very dry. And I think that's a lot of what you end up seeing in places like Nebraska or Florida or whatever. I was actually in Florida in January or February, and half the state was on fire. It seemed like I was like escaping on an airplane watching all this news about fires in Florida. And of course there were a bunch of other fires in the Southeast more recently. And so, when we talk about the whole country or half the country being in drought, the hardest thing about that is depends on the week. So you can go look at the National Drought Monitor, and it's a constantly shifting landscape. But I will say that my feeling is definitely that things are very dry. It's been pretty hot in a lot of the country, especially sort of the lower half. And then another issue that I think is really coming to the fore has to do with groundwater. And so the groundwater sort of, and this has much to do with data centers, et cetera, is, that groundwater withdrawal is also creating arid conditions in a lot of places. And that can happen regardless of whether it's raining or not. So I appreciate those questions because it is a somewhat constantly changing state of things, and the definitions can get confusing.
Perfect. And I want to add, so there's a comment in the chat. The talk was fabulous from the perspective of climate science and communication, but also just about the challenges and importance of communication more widely in our society. Thank you. And
yeah, for sure.
I think this is so important because, while we're sticking to this water, I'll get to, fire and communications environment, but just within water, I used to think, it's very important. Someone must be working on it. And now that I'm older and somewhat more cynical, I think someone's working on this, right? And I'm thinking about, I think you have done some work recently covering some of the deep groundwater kind of water issues in the West that span states. And I think that is especially challenging because when one river, for example, out west runs, from top to bottom in the country, and so many different states touch it, people taking water out upstream means people downstream have less. And so you get in these situations where governments are supposed to coordinate across states, and then federal policy then can make a huge difference. So I just want to tie this all back to, we at the Weather and Climate Livestream are here because we are urging people to contact their representatives. And water is absolutely something that is hugely affected by state and federal level policies because we are all drawing from water bodies that do not recognize state or county or even country boundaries.
Yep.
Okay, so I mentioned that you kind of brought up 3 broad subject categories. Water. I want to get to fire. So I'm thinking about when you were talking about where people get their information, fire is such a tough one because so much of the fire science is about good fire. This is called prescribed burning. And one thing that we know from fire science is that there are certain landscapes, especially, that are supposed to, historically, they would burn every now and then from a lightning strike or something like that. There are some landscapes that are dependent on that fire in order to thrive. I live in New Jersey where there's 1 million acres of pine forest. If you've never visited the New Jersey pine forest, please do. It's not at all the stereotypical New Jersey people think of. But pine forests, there are pine cones in the pine forest that will lay on the ground or be in the trees. And until a fire comes through, they're just pine cones. When a fire comes through, it heats them up and they explode. And it sounds like gunshots going off, and the seeds will spray out. Without that fire, the seeds don't spread. Right. And so a prescribed burn, though, to any community nearby looks the same as just a wildfire. And so I'm thinking about how people get information from a disaster is, it's often uncoordinated, but sometimes it's just nearby. And the signal they get first is a disaster is happening and oh my gosh. Yeah, and so I just wanted to talk about I wanted to ask you about the difference in communications. Like, how do you build up to help people recognize the difference between something that looks the same from the outside, but is actually quite controlled and is going to be good and reduce danger in the future? What do you do to lay that groundwork well before that even starts?
Yeah, I mean, I think this is one of the trickiest issues that we're facing right now. So a lot of times people will see smoke. Let me see. I feel like there's two questions going on here. One of which is kind of how do we find fire information? So I will definitely put in a plug for Watch Duty, which is an app you can download and put on your phone. Everybody really should have it at this point. 20 years ago, when I was working at UC Berkeley, we were doing early iterations of that kind of mapping before Google Maps ever existed. Like, we were developing tiny buttons to go on our little, arc maps kind of thing. And so things have really evolved to the point where something like Watch Duty can exist. And I think is excellent at showing you this is a prescribed fire, this is a new start, this one's almost out, etc. That app alone has solved a lot of issues. And I'm actually hoping that they will consider also putting water information there in terms of active boil notices, because it's really on that same kind of level and they're already tracking that kind of thing. So there's that piece of it. And then in terms of distinguishing between sort of the good and bad fire, I mean, that's partly why I put in a plug for the water thing, to just sort of say, like, fires can be really beneficial. Like, you can go, I mean, I can go into a forest. Again, I'm in northern Arizona. We have our own sort of ponderosa pine particular ecosystem, and you can see that the system I grew up in is totally transformed by not having fire. And it actually makes you feel kind of claustrophobic. There's way too many small trees, et cetera. Clearly needs to burn. You can go up by Flagstaff in northern Arizona and see examples side by side of where they've done forest treatments and where they haven't. And just the human mind, I think, kind of knows what a healthy forest looks like. I mean, mine anyway does, which might just be my training. But I do think that, like, the challenge with the good fire is that it still puts off a lot of smoke. And so I've been facing this here where I live in a very fire prone landscape where they are constantly doing prescribed burning. I live in a valley, but they're constantly doing prescribed burning up at about 1,000 or 2,000 feet higher than I am. And so many times during our very nicest time of the year, when you really want to be outside, the sky, it's so smoky you can't go outside because they're prescribed burning. Right. And so it's been a very interesting personal experience for me of just realizing how hard that issue really is, because you can kind of tell people you're going to get smoke whenever, so you might as well plan for it. Yeah, it's tough. It's tough because sometimes I am like, I don't want this smoke. I think I might rather, I won't say that, but I do think there's a real challenge around talking about the value of prescribed burning versus just fires that happen.
So I do want to pull up, there was a question in the chat about this. Do you find that cooperative agency to agency or institution to agency communications play a role in improving public communications and understanding? What does cooperation, I know you said that some people are not talking to each other, but do the communicators talk across those boundaries?
No, I mean, it's been very, very, very interesting.
Yeah,
so
I know the answer to that one.
Sure. Within the fire community, I do think there are better interagency coordination. Like you were saying, you are a part of a group. There are many types of groups like that do this sort of, interagency communication. And I do think on the fire side, that has helped a lot. But we still, again, like Watch Duty came along and solved a problem that people were not able to solve. And they are not a part of an agency, right? This is a private group. I mean, many of the folks involved have been up close and personal with some of the challenging communications, and so they know what needs to happen. But it was astounding to realize that the water and fire people don't talk at all. I would say that, when we did our first report starting in around 2019, I tried to get participants in the workshop. They didn't see it as their issue. Many of them still don't see it as their issue. They just assume when they need water, it will be there and they don't really need to worry about it. But I think there are people who obviously know that's not true. And so it's been very interesting seeing a lot of like aha moments, both between, look at, even in California, there are something on the order of 3,500 individual water systems. how do you coordinate 3,500 water systems, right? And there are small groups that attempt to do that for, like, say, rural water systems or small water systems. So all to say, these are huge, complex. We all know the United States is an enormous and complex country. And then you take these issues that, like you were saying, Virginia, really cross all institutional boundaries. And so it just is a huge challenge. But I will also say, when we have had these meetings and workshops, the spirit that people are coming to them in is really heartening. Like, people really want to deal with these issues. They are super excited to have a forum in which to do it, because who's pulling these people together, you know? So we've been able to make a lot of progress, and it all feels very good because people are just kind of excited to be talking about these things. So I think maybe we just need more ways that people can do that.
Yeah. So I want to highlight that you answered another question in the chat. Is there any particular reason why interagency communication is so poor? So Faith said there are so many water kind of divisions within California. In the fire science group that I worked in, our team of 5 covered the Northeast Atlantic. The North Atlantic. So it was like Delaware up to Maine or something like that.
Yeah.
Meanwhile, California was a consortium of small groups that there were like 20 different groups that were coordinated by a single person. So it just depends on the municipalities, and there are just so many people and agencies working on it. We are down to about 2-3 minutes, and I know I named 3 kind of big topics you brought up: water, fire, and then information. I'm just going to go straight to the chat for the last question that should take us to the end of our time. Do you think that overall people are actually informed? This is the information question. I didn't say that part out loud. We're on number 3. Do you think that overall people are actually informed about planetary issues, but just don't know how to interpret what they are learning, or they don't know how to suss out the inaccurate and exaggerated information?
Do I think people are informed? This is challenging. I was just talking to my family about this, where it's just, I'm generally somebody who believes that people are smart and, well-informed and trying to be well-informed. That is my orientation toward the world. But I do think that we are starting, or maybe have been failing people for a decade or two, on what I would call an ecological or environmental education. I do not anymore think that people are getting a very good sense of, like, drought conditions and high winds. And I mean, in California, it's pretty hard to miss the wind issue, but like, just what leads to the conditions in which a wildfire could even happen, right? And so that seems like a really important sort of missing thing, is just teaching people to kind of read the land, read the situation, and figure out what might be happening. And then I do think our fragmented information ecosystem is not helping at all. And so I've even seen it so much worse just in the last few years, where it's like, people are like, oh, I heard this on Reddit, I read this on TikTok, and you have no way to kind of be like, and they can't find the thing that they heard. And so it is a very complicated and complex landscape to even figure out what inaccurate information is. I think we have a real challenge on our hands if that isn't clear in terms of what I think. Yeah.
I would add to that too. You brought up environmental justice earlier. I'm from Kentucky, and I remember a couple of years ago, because of a federal policy, again, we're here because of funding and policy for a lot of environmental things and science things. I remember a couple of years ago when my parents finally got good internet because of a federal program that was bringing broadband to rural places. I know when I was doing fire communications, I feel like every year we had a huge topic at our annual conference that was, how do we reach people on reservations where there's not high-speed internet? So some of my work specializes in using WhatsApp and some of the communications tools that require less bandwidth and less, they're kind of optimized for cell phone usage instead of like a laptop or some desktop computer. So I think, to the person who asked this question, Sydney, it's not just about the information that exists, but it's about who has access to information at all.
For sure. So,
Faith, I want to give you the last word. We're at time. Is there any parting message that you want to leave us with?
No, I would say just everyone, thank you for listening, and thank you for participating, and please act as you feel on this kind of information.
Thank you so much, Faith, for being with us.
Thank
Everyone,
you.
I'm going to pop back out. I'm not your host right now. I was just here to support Faith. So thank you, Haley, for coming back. I'm going to hand it back to you.
Hello, everyone. Thank you both for that amazing talk. That is so interesting. And it's a great segue into our next talk, which will be a panel. I will introduce them all in a second. But before we do that, I just want to go back and remind us all why we're here tonight, why we're here for 50 straight hours, and why there's a couple people walking from New York City to DC right now. And that is because climate and weather science in the US is at risk. So specifically, the administration is changing the rules so that political appointees, and rather than peer review, determine who and what gets funded and how they can share their findings. Political interests are being used to justify the planned dismantling of the National Center for Atmospheric Research, which is in Boulder, Colorado, and is the cornerstone of a lot of the weather and climate science, both in this country and around the world. And also, the administration's proposed budget for the next fiscal year, which is currently right now being considered by Congress, would absolutely gut weather and climate research across the federal government and programs for young scientists. So that is also a good segue to our next panel, which is of my former colleagues, people from all across NOAA. So I would like to bring up everyone from the next panel. Here we go. And I will introduce everyone really quickly, how this will work. And then please put your questions in the chat. After the introductions, we'll go through some just quick, prepared questions, and then we'll turn it over to the chat. So if you have questions about NOAA and everything that is going on, please ask away, and we'll make sure to get to them later. So first of all, I'll just introduce myself. I realized when I was hosting earlier this morning, I never actually said who I was or what I did. So I'm Haley Krim. I am a climate social scientist. I used to work at NOAA in the Climate Program Office Communication, Education, and Engagement Division, which you might also hear about a little bit about from Tom. And now I work at MIT on similar things. So I now want to introduce in alphabetical order. We have Dr. Alexandra Avila, who is a former marine scientist from the Olympic Coast National Marine Sanctuary. We have Tom DiLiberto, former climate scientist and public affairs specialist, both in my old office and also at NOAA Public Affairs. Ellen McCrae, the former NOAA Regional Climate Services Director for the Eastern region. Dr. Anna Vaz, who's a former fish biologist at NOAA Fisheries. And Dr. Steve Voles, the former assistant administrator or the director of the NOAA Satellite and Information Service, who's currently on administrative leave. So my first question, which I will turn over to you, is could you all just say a little bit more about what you did at NOAA and how your work affects the lives of people around the country? And I will start it off with Alexandra. Oh, who might be frozen. Oh, are you frozen? Oh no. Okay, well, we figured that out. Tom, are you frozen?
No, I'm just very solid and not moving. Hi, everybody.
Making sure it's not me.
I'm Tom. So I always joke when people ask, like, how does the work at NOAA affect people? I usually ask folks, who here's been outside before? And even that's not really true because people inside are also affected by the things that NOAA does. So it literally affects every aspect of our existence on this planet. And the work that NOAA does, that the NOAA says is from the bottom of the ocean to the surface of the sun. It gives an idea about like how widespread things that people do. Now, at my time at NOAA, I worked at the National Weather Service, making forecasts for weather and climate events. I then worked at NOAA's OAR, doing communications work with climate.gov as their meteorologist and climate scientist. And then I was a public affairs specialist helping to communicate all the amazing work that NOAA does. And it really, truly touches every aspect of the way we live our lives. And the reason why I do that sort of stuff, why it always interested me, and I'm sure a lot of folks here too, it's because we just wanted to help people. I think that at its core, that's what NOAA's about. It's providing information to people so that they can make the best decisions to keep themselves, their families, and their loved ones safe.
Amazing. Thanks. Ellen, how about you next?
Haley, thanks for having us. This is really exciting to see everybody. I feel like one of the biggest things about leaving NOAA was missing my NOAA family, so it's nice to have us all together. What I did at NOAA, and you described it in my introduction, was working in climate services. My role was to basically make sure that people on the outside of NOAA were actually using NOAA's climate information, and figuring out who those people are and what they were doing with the information. And really, because climate information was free and available from NOAA, its value is determined by who uses it. And so it was really critical for us to think about both not just state and local communities that were using it, but also other federal agencies that were using it, other industries that were using it. And every day, my boss would say, so who's your target today? Because it would change all the time. So it was really great to think about this both geographically and by different industry sectors. And so how it impacts the US, we used to say we touched every sector of the US economy. Because of the kind of information that Tom just described, that it was so valuable for everyone that ever goes outside or wants to know what's going to happen in the next couple of days with a weather forecast, or needs to plan ahead and think about their preparedness in a changing climate. All of that was well within the wheelhouse of NOAA, and it was really fun to be there.
Amazing. I totally agree about how nice it is to be back together. Awesome. I'll turn it over to Anna.
So that's great to go after, Elaine, because I was one of the users of all the data inside the agency. So my title was a fish biologist, and I was with the Southeast Fisheries Science Center. But my day-to-day duties, while a federal employee, were to use all climate and oceanographic data and climate models, forecasting, and understand how they influence our ecosystem, our fisheries, and develop tools that our decision makers could use for the management of our fisheries resources. So I worked in the whole southeast of the US and Caribbean. My community is impacted from my work, especially the fishermen, but also our planners and people related to the blue economy in any way. So it goes way beyond just the people who are in the water. We have charter boats, we have tourism for fishing, we have the whole processing, restaurants, divers. We have a very broad economy that thrives in the living resource that we can support at NOAA with our work.
Great, thanks so much. And it seems like we lost Dr. Villa, but hopefully she'll be able to make it back on. So now, Steve, I'll turn it over to you.
Yeah, thanks, Haley. And it's great to see everybody here and to be a part of this. I think I'll follow up on what Tom said up front, where he said, do you go outside today? I'd say, do you breathe today? Because, what I did at NOAA was running the Satellite and Information Service, which is basically the system that flies and operates all the satellites to give you global environmental data, and then manages the data and information system, the National Center for Environmental Information, which stores and archives and makes it all available and hopefully accessible to people who want to use it. So my job was managing the development and application and deployment of satellites, but really, as I'm listening to all of you guys talk, we had similar jobs. It was storytelling. It was telling people why it's important, because most people don't think about satellites or information or environment. They don't think about where the fish come from, other than which aisle in the grocery store. So my job was to tell people who we wanted billions of dollars from to fund these programs why it was in their interests, and then talk to my organization who were really focused on their individual elements, why their elements fit with everybody else. So it really takes all of us to be successful, and it was a key part of being with NESDIS. We were never the ones on the front lines or on the front page. We were always the ones backing it up with the information to give the NWS a chance to speak, or to give the fisheries a chance to make their fish rulings, et cetera. So it was great being an enabler of science and information. But it's all about storytelling, about trying to remind people about how they actually live in the world, and the world is not a shopping mart where they just buy what they want. They're impacting and a part of it.
Absolutely. And this is totally reminiscent of our last panel on science communication. And I love hearing that as someone who, worked on climate communication at NOAA. Yeah, absolutely. It is all about storytelling. And next, I want to ask a question that has been really popular in the chat, which is how did you end up working at NOAA, and what really inspired you to do the work that you do? And so I will switch up the order and start with you, Anna.
So I have many answers to that question, but I fell in love with the ocean, and I decided I was going to study the ocean. I was 9 years old. I lived in the countryside of Brazil. So Jacques Cousteau inspired me in the afternoon TV. I want to live these adventures and travel around, and not even knew oceanography existed. And I follow the dream, and NOAA is the agency to study oceans, is the leading agency in the world, right? Since I started my undergrad, it was my dream to get to NOAA. I'm also a naturalized citizen. So for me, it's part of giving back to the country that I chose to make my own and to raise my family, to give back to my communities, to have a job in the civil service. So that's deeply meaningful for me personally. But NOAA is just a very vibrant community of people that are talented, as you can see here, passionate about the mission. And it's just a unique place to work and to be able to develop your science and management storytelling career.
Amazing. And it looks like we have Alexandra back, and it seems like you're moving perfect. So just wanted to give you a chance to answer the first question, and maybe also the second at the same time. So what did you do at NOAA, and how does your work affect the lives of people around the country? And also what inspired you to do that work?
Yeah. So sorry, I was having a little bit of internet issues before. I am now on my phone, so hopefully this will be good. So I was the marine scientist at Olympic Coast National Marine Sanctuary. One of the main duties that I had there was helping with the oceanographic mooring data, and that's been collected since the year 2000, which is really important for climate models going forward. And all the data is being collected, but also for fishing community to know what's going on. And one of the projects I was working on was having live ocean data, because the data that's been collected was not live. It was going back after the fact to collect the data and see, oh, it was hot this day. Oh, the pH was this. So having a live buoy is really important for fishermen to know, hey, is it a good day to go fish for this or for crabs? How are the oxygen conditions? If there's no oxygen or very low oxygen, that means that the crabs are going to die. So maybe not a good day to go crabbing or to take out your crab pods out. So that was the biggest project I was working on, but also there was collaboration with local university, with other NOAA line offices to do other studies there in the sanctuary as well, and long-term monitoring of species that migrate all across the coast, like whales, like sharks. So I was really excited to be working on that, and also doing a 304D consultation with the tribes, which is their right to hunt and fish in that area. So making sure that they have those access for their treaty rights. So what inspired me, I grew up in Ecuador, so that's in South America. I grew up in one of the most biodiverse countries in the world. And of course, the ocean's right there, the Pacific Ocean, and we have the Galapagos Islands there. And having access to that all natural beauty was awesome. And I think it inspired a love for nature, for the ocean, for conservation. And I loved watching the fishermen come up on shore and show me what they caught, and looking at all the cool, weird critters, sometimes very unique things. So I really wanted to work with fishermen and help protect those resources for future generations, so that we can continue to fish for generations to come. So that's the whole purpose of sustainable fisheries, is to help maintain those fisheries in a healthy level. And what did I do here for the community? I mentioned it briefly. Basically, a lot of this oceanographic data helps fishermen in the local community to make sure that they can be able to fish when it's safe for them to go fish, protecting some of the habitat that is important for fish, that's known as essential fish habitat, just making sure that the oceans are healthy. And of course, educating is a big part of well, not just Olympic Coast National Marine Sanctuary, but of the Office of National Marine Sanctuaries in general, is educating the public about our oceans and about our sanctuaries and what the resources are there, and why it's important for local communities to have these, and why it's important to protect them.
Great, thank you. So now we'll go back into the second question, which is what inspired you to work at NOAA, and I will turn it over to Steve.
So I'm a child of the space age. So I came to NOAA sort of in a back doorway, and not because I was studying the Earth and I loved it so much. I did love the Earth, but I was a space cadet in the 60s and 70s, and Star Trek and Lost in Space and everything else. So I worked for NASA for 20 years, 25 years actually, before I came over to NOAA. But at NASA, I fell into or chose to work in the Earth Science Division running the satellite program there, and just fell in love with all the wealth of information and observations that were possible and what we could see and understand on the planet, and seeing the planet as a whole, as an integrated whole. Never been to space, like they always see the astronauts say, when you see the Earth from space, it changes your perspective. Well, I got to see that from 50 different satellites from space, and so I got the global perspective that way. But coming to NOAA was really a surprise to me, but a welcome one, because I got to not only see it, but actually influence how we deliver that story to the rest of the world and to the nation. And the Satellite Information Service was really the best job ever, because you could not just process other people's data, but you could define what we're going to be collecting for the next 30 years. And that was really remarkable. It allowed me and made it possible to be a part of an ongoing history of 50 years of NOAA development and operations, but also to look forward another 20, 30 years about how we're going to be doing this into the future, to get information to these people, to Anna and to Alexandra and to Ellen and others, so that they can do the things they want to do, and really enabling the people to exercise their passion and to give them information that they could do things with it. And it's always been driven by puzzles and trying to understand how things work, and seeing the Earth as this integrated system is one of the biggest, most exciting puzzles to try and study. And it's been great ever since, doing all that work, and seeing the application of it has been the greatest reward ever.
I will say the highest concentration of sci-fi nerds I've ever met is everyone at NOAA, including myself. So totally agree with that. Awesome. Tom, what inspired you to work at NOAA?
Oh, I'm a weather weenie through and through. I've been obsessed with clouds and the weather since I was a little kid. When I was in 3rd grade, I said I wanted to be a meteorologist and I wanted to work at NOAA. It was kind of synonymous with what I just wanted to do. And if you love the weather and you wanted to forecast it, I mean, how can you ever beat working at NOAA? And I was lucky enough to say that I was able to do that in some capacity. Yes, my interests have shifted since I was in 3rd grade a little bit, not a ton, a little bit, but it's still kind of the place that I wanted to always work. I always felt, and I still feel, that when it comes to weather and climate and our atmosphere, there's a service aspect to this of making sure people are safe, and being able to use the skills I have and the things that I love to be able to keep people safe. I mean, there's nothing better than that, which is why, I mean, there's no other place I would have wanted to work than NOAA.
Totally agree. Ellen, how about you?
Well, I just love hearing from all of you guys that this is like a life goal since you were little. And I think it was probably the same for all of us. I grew up on the ocean, but I went to college off the ocean. And my dean said to me, just pick something in the course catalog that you like. And I picked oceanography. And I was like, this is awesome. There's actually a class in something that I've always been curious about. So then it became, off to graduate school. And then, the place to go out of the sciences has always been in my mind, to the US government science institutions. So I actually did summer internships at the US Geological Survey, and they hired me, and I was so excited. And I worked asking the pure science questions and diving into the observing of basic contaminants and paleoclimate information in the sort of rawest sense. But then I did a leadership program, and my details, or my trial period, if you will, was to go over to NOAA and work for the assistant administrator at the time. And he was in the middle of doing a whole exercise called One NOAA. So I grew up thinking that, if we could just get all of these different pieces of NOAA together, it would be incredible. And I say when I grew up, because when I started at NOAA is when I grew up or something. But what I mean is that it was really this sort of holy grail to have all of us working together. And so I joined NOAA and moved from the research questions that were at USGS to what was emphasized to me was the solutioning space. It was thinking specifically about the product and service development. And I was so excited because it meant that we were actually going to be able to provide actionable research, actionable responses to all of the communities that I'd worked with. So it was truly a pleasure to be a part of NOAA and feel like I could pull the answers that all of my audiences needed from any part of the agency. And that was kind of my one NOAA approach. So anyway, I loved it. I think we all loved it.
I feel like there's so many variations of the same story. It's amazing. It's such a good place to work. So my last prepared question, and then we'll turn it over to questions from the chat, is obviously we have seen massive threats to NOAA in the last 2 presidents' budgets. And on top of the fact that the agency always could have used more funding to best carry out like a full scope of its massive mission. So if you were in charge, where would you direct funding or effort or attention right now in order to make NOAA better? However you want to take that. It can be in your own office. It can be overall. Get creative with it. And I will start with Steve.
Damn, I was hoping to follow up on others on this one. Okay. I guess I'll start with where there are 2 parts. The second part I'll say first is that to get more money, we need to explain what we do better and have people appreciate what we do. So let's assume that has to happen. But where the more money would go, I wish we were one NOAA, but we're not. We weren't. We were many NOAAs. We weren't. Everybody wasn't their own individual. There were very large subcultures within NOAA that were very strong. But they tended to be too strong, so that the original loyalty was to your home org or your home office or your home discipline. And it allowed us then to keep our heads down and not really to be aware of the dependencies we had. So I think if we had better funding and more funding, it would be towards really looking at the ways that finding finding the commonality across the NOAA elements. Could be data and information management. It could be training for personnel. It could be setting up cross NOAA career development programs, which are required and necessary, that you're going to move around and other places, so that you see the connectivity. But really focusing on that, so then we could still have the excellence in the different in research or in fisheries or in coastal studies, but they're based on a common backbone of information and shared interest, which allows us to have all of our data interoperable without a second thought, without a second dollar. It's all covered. All of our systems work together, and all of our systems are supported in a more sustained way. So it's not supplemental money or research. Research is considered different from operations. You can't do operations without research to back it up. They have to be considered equally important. But something which recognizes and forces us to recognize the complementarity of all of our different systems and get us to really be a whole Earth system program and organization, one NOAA, which is all focused on that while still maintaining our individual excellence. But the first part's got to happen too. The rest of the world has to recognize that what they get, how they live, depends on how well we do. And we need to make that story better for everybody to understand.
Absolutely. Thank you. Now, Tom, what would you do?
Yeah, that was great. If I had control and where I would direct money, I mean, it's very true. NOAA can still be quite siloed in a lot of different ways, especially when it comes to certain topics like climate that can kind of go across all sorts of different aspects of NOAA, but also gets into like how our data is being used and how we can how NOAA can better provide information so the people on the ground, decisions of communities across the country and across the world can use that in a way that actually helps. And I think that in the end is incredibly an important aspect that can always use more funding and more thorough efforts to be able to translate. What's that last mile? And that goes from weather information to fisheries information, especially climate information. It's not just enough for NOAA and the government to produce climate tools if there's no explanation for what those tools are and how to use them. And I think that aspect was tried with, there's always little bits of it, but it could be a more thorough. It also could involve better collaboration across the U.S. government, so that we don't have folks reinventing the wheel in different agencies across, whether you're working at the U.S. Geologic Survey or whether you're working somewhere else, NASA versus NOAA. So I think that's always just an incredibly important thing. And I think also another thing I would really focus on too, if I had money too, but it's not really a money thing. It's also making sure scientific integrity and those sorts of policies are incredibly strong and enforceable across not only NOAA, but across the government, but especially across NOAA, and making sure that NOAA scientists are able to speak up about the science that they do without fear of anything potentially negative happening to them, because they're just speaking about the science of which they're experts in, creating a more an atmosphere of scientific creativity and expression that is following a true sort of like science-minded sort of outlook.
Completely agree with everything you both have said. Ellen, I just saw you unmute. How about you go next?
Sorry, I was like, I think I figured out your order. So, all right. Well, so I would foot stomp the things that Tom said here. I mean, in part, I think if we had a dependable budget, there are some things that are inherently governmental that the world relies on NOAA for. And that I think is a little bit at risk right now. And what I mean by that is the staffing. So I guess the first thing that I would do is make sure that we have the people that we need to make sure that the observing systems are stable and quality assured, quality controlled, and that the data on which everybody depends are quality are up to snuff, if you will. So that stuff has to be trusted. It has to be authoritative. And a lot of people depend on that coming from the federal government. That being said, I do think that the interagency space is a really wonderful one that you mentioned, Tom. And that is because the interagency space is really where the public interacts. So when I was going out to customers in different states, for example, you know, they really don't know the difference between what USGS does, what EPA does. But if you have all these interagency groups, I was leading a group called the New England Federal Partners. We had one in the Mid-Atlantic. We had another one in the Southeast. We all knew enough to be dangerous about the missions of each of our agencies. And so when somebody would ask a question, we would be able to direct air quality questions to EPA and landslide questions to USGS. So it was really helpful to help them navigate the government, really. And so I think I would love to see in the budget some interagency emphasis and the ability to share funds so that it's not just so siloed in line items. I think that the other part of being in the government that is really satisfying as a scientist is to not only offer up the inherently governmental observations and the data, but to turn that data into information and to make that first interpretation kind of like the Weather Service does with the all caps forecast, right? So it's like, if we're going to do the first interpretation, it's to make sure that that is fit for purpose and that that interpretation is valid and based on the experienced science. So I would like to see a rehiring of a lot of the scientific expertise that was lost. And then I think that in addition to that satisfying piece, there are some of us that we would say, you know, should stay in their offices, and there are others that should get out of their offices and go talk to people. And that technical assistance, I think, would be incredibly valuable for the US public to have a deeper understanding of what it is that the government is providing and a good interpretation of what that means for their own daily lives. So those are the things that I would love to see. Overall, more money to be put towards being responsive to our partners. How can we be responsive to the scientific needs of states and local communities and tribes and industries, all of whom are paying their taxes? So all of whom deserve the interpretations that come from the data that come out of NOAA.
Completely agree. I feel like we're building an amazing agency right here. Alexandra, how about you go next?
Yeah, so basically agree with everything that it's already been said. I think it is really important to communicate with other line offices within NOAA, but also with other agencies. As someone who's worked in the Park Service, the Forest Service, U.S. Fish and Wildlife, and then NOAA, even within a couple line offices within NOAA, communication among agencies is very important. Not only not to like double our efforts, but maybe to divide and conquer the work that's being done in collaboration is for any research is really important in that. Also, of course, I'm biased towards sanctuaries. I would love to see sanctuaries funded and fully staffed. There's a skeleton crew right now, and I know this is true across all line offices, and a lot of the work either is not getting done or one person is trying to do the job of 3 people, and you can only do that for so long before you burn out. So seeing well-funded staff across all line offices, I think would be very important to protect this long-term monitoring that from like IOS, that basically all the oceanographic data that's being collected through like decades of monitoring. I think is really important. The tribal partnerships that we've had here, like or partnership with communities or universities, I think is really important to maintain, because if you don't maintain it, then that trust is lost and it's really hard to get back. But more importantly, I think as scientists, as federal agencies, NOAA and other agencies, we've failed to communicate our science and why it's important, and to connect with the public to help them understand why our work is important, why it matters to them. Usually most people, when they think of a federal employee, the first thing they think about is the Park Service, because they're usually front and center. You have park rangers explaining the importance of the natural resources. I think we need to do a better job at educating our communities, our students, our schools on why the work that NOAA is doing is important, why Weather Service is important, why Fisheries is important, why NOS, the National Ocean Service, is important, why all these different line offices, why NESDIS is important, all the data that we're getting from NESDIS that is being used in a bunch of different models, that is being used by a bunch of scientists. Most people probably aren't aware of that. And so I think we have to either better train our scientists to become better science communicators. I'm a very big fan of science communication, or hire communicators themselves to help the scientists communicate the science. Just to show why it's important and connect with the communities that we're serving.
Absolutely. And lastly, on this question, Anna.
I really want to go work for the NOAA that we just created here. I think I'm just going to emphasize a lot of the points, because a lot of my points were touched by my colleagues. I think what Eileen said of our services is very important. I think we needed a review of everything that was cut and lost, what is threatened to not being able to meet congressionally mandated obligations of NOAA that we need to fulfill. We need to get back scientists and staff and resources for these obligations to be met, because those are duties to the public, our legally and congressionally mandated duties. I think that is like #1 priority over here. And we're talking a lot about this interdisciplinary, like a lot of scientists like me, my job was exactly to be a liaison between OER and fisheries. So I was working also with the Fisheries Council, with communities. So that I think there are roles that we need to invest in the future. And in that light, I feel is, a lot of just problems we have, environmental and political, are because they're not like just natural systems and science, is people. And we need to move from make science for the people, but with the people. And if I had then a leftover fund after funding all the congressionally mandated services, I would invest heavily on human and social sciences, educators, anthropologists, behavioral scientists, other people that can go with the communities and really help us understand and interact with them and change the way we do science, get from the science that we're just delivering something, but understand what people are getting and want, and we can give that feedback and build just NOAA and our science with them. And I think that's particularly important for our indigenous communities, for our traditional knowledge holders. We can't let it go of all the progress we made slowly over the last years in inserting them in our sciences and giving them voice. We need to really foster that relationship, because there's a limit to what we can do with the data collected and the models, and we really need to reach to people and do science with them for that to be meaningful.
Again, completely agree. I think we have set out the plan for the future. That I would absolutely love to work at the agency that we just created. And I feel like we were we were going in that direction before, and I'm sure we will get there in the future. So I will now turn it over to questions from the chat, and anyone can answer any of these questions. Feel free to just popcorn style if you would like to answer, and we'll kind of go quick because we're coming up. We have 6 minutes left. The first one covers a lot of things that came up many times, and it is, do you think it is more important to adapt science information so most people can understand, or to improve public education so people can understand the science as it is? And anyone who wants to take this one on can go for it.
I'll go for it. So I think it's not an either or, I think it's both. So one, as I mentioned, we need to do a better job at communicating our science in a way that's understandable. That does not mean dumbing it down, but explaining it in a way that's clear. But also, I think our public education system has been lacking funding, and we really need to improve that. Education is so important. So we need to do better at educating the public, educating kids. And I love, honestly, one of the things I love doing most is going to little kids and telling them about the ocean, third graders, fourth graders, middle schoolers, high schoolers, and just tell them why the ocean is so great and telling them about different careers in marine science. Because of course, usually people think of, oh, marine biologists, like, well, there's so many different things you can do in the ocean. And really, if you, excuse me, and even if you're far away from the ocean, we're all still connected to the ocean. So understanding how that weather is going to affect us, how our rivers connect us to the oceans, how our climate and weather are associated with that, and how basically we're all in this together, and we need to work towards doing a better management of our natural resources.
And I'll add, I was going to say the same thing. It's not an either or, but I think I think there is a choice here, and I think it would be to adapt information to the people to meet people where they are, and teach them or explain to them the world they live in from your perspective. You're never going to they don't need to know the science as we know it. If they want to, fine, we love it, but it's the relevance of living in the earth, we're living in their environment, in their community, and talking to them in their language and in their relevant history and in their context is the best way. And that doesn't mean more scientists. It means more communicators and more, I think it was Anna who said, better educators, better communicators who can talk to people in an environment and in a conversation that they understand. Our job is to translate it into a way that's more understandable. So I think it's adapting our communication style so people can understand the relevance of what we do and how it's important for them.
And could I add something? One of the recommendations of the UN Decade of Science is that we foster ocean literacy in all our curriculum. And I think that would be an amazing path to really connect us to the communities. Brazil was one of the first countries to pass a law to have blue schools. So every curriculum in the entire country, with the countryside, will have ocean literacy. And I think that would be a game changer for us if we can. Like, I live in Indiana. If I go to my schools and I connect the kids why it's important, the ocean is important for their lives. And if they can have that through their education, that would be phenomenal, because we really would have engaged citizens in all this that we are now talking about.
Absolutely. And just to throw out a little plug for some work Tom and I did, we worked on climate literacy. So both developing trainings and also the climate literacy guide. So it goes hand in hand with ocean literacy. There's also energy literacy. So absolutely, that public education is so important. Next question, we have 2 minutes left. Again, for anyone who wants to answer, what's your favorite model, tool, or data set that NOAA produces?
Oh, pick me. So one of my jobs was to go ask people that same question. It was so great. And so what was my own? Climate at a Glance. So Climate at a Glance was this awesome way of just plugging in your location, and it would just give you the history. So I just love that one. And it's one that all of my users like. Also a few others that are now offline, but nevertheless, really good. And so, yeah, I would say that there are also data sets that are very important. One of the things that I'm working on now is prioritizing data sets for different sectors. And there are some very key ones that NOAA produces that we have to have, and also that USGS produces and others. So fundamental landslide information from USGS, earthquake data on a real-time basis, stream gauging data from the USGS that form the basis of the water forecasting that's done in the river forecast centers. Yeah. HERDAT2, IB tracks. We're just going to get into whole like alphabet soup, but all good stuff.
Yeah, and also there's so many that don't. ENSO blog, rest in peace, from climate.gov. I know, as an ENSO person, I can't resist saying that. I love the U.S. Climate Resilience Toolkit. And the number of folks who've used that in communities across the country and world to help them make up plans is great. Although I gotta say, I'm a buoy person, I'm an ENSO person, I'm an El Nino person. Oh, the Tau buoys. Oh, I love the Tau buoys. I wrote a love letter to the Tau buoys as an ENSO blog post back in the day. So huge fan of just all the observational data sets that exist across NOAA that let basically allow for the global economy to run. It's what they're all based off of, is a lot of NOAA data.
Can I jump in and say the ones that require the most complementary integration of different data sets? So like the ocean color data sets, which show for harmful algal blooms, which come from 5 different satellites that were never meant to work together, and yet we managed to make them work together and provide a real-time operational data set. So it's an example of integration and fusion, which really shows the power of multiple observations.
Amazing. Any last ideas from anyone who hasn't spoken?
The $1 billion wedding climate disaster. It was very useful for me to talk about science in the Midwest and why ocean science was important. But yeah, I like the observational data. Argo, especially in the XBTs, like little things we throw in the ocean and they go collect a probe, go collecting temperature data out to the bottom. That is really amazing because we can get a reading of the ocean and we have very long time series in certain places. That is what we have for global models. So that's fantastic.
The best observing in the world.
All right. And
honestly, I just wanted to add the Oceanus Explorer, the data, like the deep sea stuff, all the cool fish. I think that's some of the really cool data sets that I've worked with and that I love seeing.
So the ocean mapping stuff is so interesting. Amazing. Well, we are at time, but thank you all so much for all of your service during your careers at NOAA and also for joining us on the live stream. And I know some of you are speaking in the coming day before we end the live stream. So everyone make sure to stay on the live stream so you can hear more about what all these amazing people do. And thank you all so much.
Thank you, Haley, for all your work organizing this.
Yep.
Thank you for having us.
Thank you.
Lots of love for NOAA in the chat. And also the Argo floats, which I know people were going crazy about yesterday. Amazing. It is starting to get kind of dark here where I am. So that means it's time for our next speaker. But before we do that, I am going to remind us all again why we're all here. And that is because we are at a really crazy turning point for US science at the moment, specifically around climate and weather, but not exclusively. So I just want to highlight a couple things. They are also highlighted in writing at the link that is scrolling on your screen right now. So wclivestream.com/act has all the information about this, as well as ways that you can take action by calling and writing to your representatives. Specifically, we are focused on the proposed budget cuts for fiscal year 2027, which do things like eliminate the research arm of NOAA, the Office of Oceanic and Atmospheric Research, where I used to work, Tom used to work, I believe Ellen used to work. Now I'm trying to remember where all the offices sit. But it's a huge potential loss. That budget also cuts the NSF and NASA Earth science budgets in half, literally, and does a bunch of other things that would be really disastrous in terms of climate science funding and weather science funding. Also, the administration is trying to dismantle NCAR, which provides the computing backbone for a lot of weather and climate science, both in the US and around the world. And lastly, as of last week, the Office of Management and Budget has proposed some incredibly extreme rules to basically politically interfere in the scientific process and de-emphasize peer review and limit the types of grants that can be given and the things that can be studied and how those findings can be shared. So write and call your representatives to make sure that these things don't happen. And we have more scripts and templates and things for you to use at the link that is scrolling at the bottom of your screen. And with that, I would love to bring on our next panelist, who is Sarah Perkey. She is a professor of physical oceanography, and I will turn it right on over to you to talk about deep ocean warming.
Awesome, thank you. Well, I love the segue from that last question. What I'm really talking to you today about is Argo and the Argo program, and specifically a little bit more about Deep Argo, which is an expansion to Argo that we're trying to get into the deep ocean. So I guess I do want to start by thanking all the organizers of this and inviting for the invitation to come talk to everybody today. This is a great cause, and I'm very excited to be here today to talk to you about the deep ocean. So this talk follows a bit on a talk that I got to give last year. And so I'm going to race through some of the upper Argo stuff and then try to get into some deep Argo and some of the new work that we're doing right now. But to set the stage, I always like to start with these first couple of slides, just to explain to everybody how important the ocean is in regulating our climate. And so in this figure here, what you can see is a heat balance of what is coming into the system and what is going out of the system. And there's a lot of energy coming in through incoming solar radiation. And then there is some of that's reflected, some of that's absorbed, and then let out in long wave radiation. But for the last few decades, we've been in an imbalance. And so if you can see on the bottom left-hand side of this figure with the big red circle, it shows this 0.6 watts per meter square imbalance, showing that the Earth is absorbing more energy than it is letting out. And so we can measure that, and we have through time. And so what this plot is now showing is the cumulative, that integrated energy in zetajoules that have come into the climate system. And so the big fat back line shows the year-to-year variability in that accumulated heat. And you can see recently it goes up and up and up, with some error bars based on our best estimates of how well we can constrain that addition from year to year. And so what we can see is that over the past basically 8 decades, the Earth has accumulated close to 400 zetajoules of excess energy. And so the next question is, where does it go? And all of those blues on there, the light, medium, and dark blue, represent sinks of that excess energy into the ocean. And so what this means is it means that over 90% of this accumulated excess heat is getting absorbed by the ocean. And for the most part, that's a positive thing, right? It pulls it out of the atmosphere, it brings it into the ocean, and some of that, which I will talk about in a bit, is getting into the deep ocean, where it's going to be sequestered and taken out of the climate system that we live in for quite some time. And yeah, so of that, this percentage over here, about 10% of that is going into the very, very deep ocean that I'm going to talk about in a little bit. But just as a point of reference, that purple line all the way at the bottom, that's the atmosphere. And so when we talk about extreme weather, we talk about the 2-degree limit of what we want for the climate that we live in and sensitivity. We're really talking about a very small percentage of the total energy imbalance that's coming into the climate system. And we can thank our oceans for that. And the ocean's ability to absorb this excess heat is really regulating how fast we feel climate change. And so we want, regardless of whether you live in the middle of the country or next to the ocean, the oceans are playing a very fundamental role in mediating how fast climate change is affecting us, because they are very, very efficient at taking up this energy. And And where I'm going with this is just understanding how the oceans take up this excess heat and how that might change in the future is something pretty fundamental that we're going to want to know in order to forecast the future and understand what climate is going to look like in a decade or 2 decades or 3 decades. Okay, so now I'm going to talk a little bit about Argo and ocean technology and how that enables us to get these estimates of ocean heat content. Okay, so over on the left, this is a schematic. If you're not familiar with Argo floats or profiling ocean robotics, this is a schematic and basically shows how these floats work. They are density driven. And so an important thing to know is that the ocean is density stratified. So what that means is there's lighter water at the surface and there's denser water at the bottom. And what the floats essentially do is they change their density and then they're going to move up or down to get into equivalent density water. So when they have an external bladder and when the external bladder is extended, the volume of the float is more. It essentially is making itself bigger. And since its mass stays the same, its density is going to go down and it's going to be able to go up. And when it pulls its external, it has oil. When it pulls that internal, it deflates this external bladder. It makes itself smaller and then the float can sink. And using this technology, we have built a number of models that essentially allow for these profiling floats to move up and down in the ocean. And so what's shown in the middle is a picture of one of the original ones, and then a more modern day one over on the right. And so through an international partnership between the US and over 30 different countries, we have built a network of these profiling floats that are now literally littered throughout the global ocean. And so this is a map showing the location of each of these individual robots out in the ocean, and there are over 4,000 of these floats. And they are sampling the ocean continuously. And what each of these individual floats are doing, it basically gets deployed from a ship. It sinks down to 1,000 meters. It drifts for roughly 10 days. Then it goes down to 2,000 meters. And as it comes up, it samples at least temperature and salinity and pressure. And then when it gets to the surface, it transmits that data back to us here on land. And then it goes down and does it again. And each of these individual floats can live up to 10 years in the ocean, profiling up and down and profiling every 10 days. And what we do is what we have done with that data is that basically the goal is to have a float every 3 degrees by 3 degrees of the global ocean. And we're essentially getting a weekly or a monthly snapshot of what the temperature and the salinity of the ocean looks like everywhere. So these are weather balloons of the ocean. And then what we can do is we can make these lovely maps of things like temperature anomaly. And you see there's all kinds of variability in the ocean. On annual, but also on month-to-month variabilities. And one of the most important things that we can do is we can map how the global average ocean temperature is changing. And also that will map onto how the heat content is changing in the ocean. And so what this is showing is a figure that shows depth versus time of and how the temperature is changing from the 30-year mean. And so everywhere it's blue, so the mean is going to be in the middle of the time series, and then places where it's blue was relatively cold and then getting relatively warm. And what we see is that there's warming most intensely at the surface, but there's also warming that extends all the way to the bottom of the ocean. This is great. This data is used for a huge number of things. It was designed to take the temperature of the ocean, but nowadays it is used really for a number of applications, and I don't have time to go through and highlight all of them. But just to say there are applications on the applied or operational side. So Argo for temperature and salinity is primarily funded through NOAA. Thank you, NOAA. And that directly goes into a number of operational uses, including weather forecasting, looking at fisheries management, marine law, looking at extreme weather. The oil and gas and energy sector uses it, as well as a number of military applications. On the right-hand side, I'm highlighting the other primary use of the Argo data, which is really fundamental science. And this observing network which is taking data continuously. That data is typically up and open and available to the public, processed, QC'd, available to the public within hours of the floats getting to the surface. And as a result, the scientific community now relies on this data and has used it for thousands of applications. And so since the program started in the early 2000s, you can see the number of annual papers that are being published, scientifically peer-reviewed papers that are coming out using this data. And most recently, the numbers are over 600 a year, so that's roughly 2 papers a day that are coming out using Argo data. So that's all great, but what I want to spend the rest of the time talking about is looking at what is happening below 2 kilometers. So Argo and the technology has traditionally been limited to the upper 2 kilometers of the ocean, but as we saw in the plot, the warming doesn't necessarily stop at 2 kilometers, and we want to extend Argo all the way into the deepest regions of the ocean, and so that we can get a whole global picture of what the ocean is doing. So people, I think, just bringing this to the general public, people think about the deep ocean as very remote, and it is remote, and it is a very challenging environment to work with. So over on the left is a schematic kind of showing different species of things that live in various depths and where we're talking about. So core Argo is kind of operating in the upper third of the ocean at about a mile deep. And the pressures that these floats deal with on a weekly basis as they dive into the deep is very high. The water weighs quite a bit. And so just for reference, we're talking about pressures of about 200 times that of the surface. It's about 3,000 PSI, which means that that's about 3,000 pounds per square inch. And so what that means is that each of these floats is experiencing about 1.5 tons of force on them, which is a lot of force. If we wanted to extend it 3 times deeper to go down to 6,000 meters, we are now talking about pressures that are 3 times as great. And so we're talking about 9,000 PSI, which is 9,000 pounds per square inch, which is 4.5 tons of force. So this is a lot of force. And we need to build equipment that can do this every 10 days and hopefully last for years and years and years. And so this is not a small engineering feat. In exploring the deep ocean, we also want to back out for a second and just look at what is in the deep ocean and the role it plays in climate. So this is a very simple schematic of a cross-section of the Atlantic Ocean. So you have Antarctica down here, you see South America, North America, and Greenland up here on the right. And then what we've done, we've cut the ocean and we're looking at the side. So we have the surface ocean, but most of the deep ocean is filled by water that is coming from the high latitudes. And so we see the 2 water masses there being the North Atlantic deep water that's coming from the North Atlantic and the Antarctic bottom water. And so these waters are formed at high latitudes, and then they sink into the deep ocean, and then they move into the interior. And so when thinking about the deep ocean, it is important to think about what's happening at the poles. So for the bottom water, for example, it's being produced at a number of locations around Antarctica, and this is a model simulation showing the temperature and the quantity of water that's coming off of one shelf, the Ross Shelf around Antarctica. And so when this water is being formed, its origin is in these really dense shelf waters that are formed through very complex interactions between the atmosphere, the ice, and the topography that allows for this dense water to form. And eventually, through other kind of dynamics, this dense water is going to be forced off the shelf, and it's going to flow into the deep ocean. And this is the source of water that fills all of the abyssal ocean pretty much around the world. And so when we think about this, it's important to keep in mind that conditions where these waters are being formed are also experiencing a fair amount of climate change. So when we look at Antarctica, this is showing warming, and also to highlight on here is the ice extent, which especially over the last few years is changing. But without getting into too much detail, Antarctica is not isolated from many of the changes that we're seeing around the globe. And those conditions are changing, and it is logical to think that it might start to affect the production of these deep waters. So I just put a question mark here about the remoteness of the deep ocean. It's a very challenging environment to get to, and in some ways it feels very far away, but in other ways it's just to say that it's really not. It is still feeling it's part of the climate system, and there are still connections from the surface into the deep ocean that hopefully will show you is moving relatively quickly. Okay, so how are we observing the deep ocean? For observing the deep ocean, historically, we've had to use ship-based observations. And so I want to highlight a really important observational program that sometimes people don't think of when we're thinking about ocean observing, but really does serve as the backbone to most of the autonomous observations that we observe, at least for Argo. And that is the Go Ship program. And the Go Ship program is a program, again, that's an international program. It takes ships out and it measures the physical and chemical properties of the ocean from the surface down to the bottom, roughly every decade along each of these sections that you see here. So what that means is you go out on ships, we take a rosette, we put it into the water, we let it go all the way down to the bottom, we sit and we wait for it to come back to the surface, and then we pull it on and we take lots of water samples. And what we get are these beautiful sections every 10 years that show us things like temperature and salinity, but also things like the chemistry, the oxygen and the nutrients, and various tracers. The second way is with the new Deep Argo program. Again, thinking about the deep pressures, these floats look a little different, but they essentially work the same way as core Argo, which is they will sink down to the bottom. But instead of only being able to go to 2,000 meters, they can go all the way to the bottom. And this is a float over here on the left that we built here at Scripps. This is the current distribution of the Deep Argo floats, and so it is not global yet, but our hope is that we're going global soon, and there's about 200 active floats right now from a number of countries, which are shown in the different colors. Okay, so if we take that data together, we get this picture of deep ocean warming, and indeed the deep ocean is warming similar to the surface. It is warming at a slower rate, but is still definitely seeing the signal. So what you can see in this figure is a global map. The red are showing areas where it is warming, with some areas like in the North Atlantic that are blue that are actually cooling. If I look at the zonal mean, which is shown over here on the right, you see this red swab kind of coming into the deep ocean, following those paths of water going into the deep ocean. So the next question is really, how is this deep water warming? What are the mechanisms that are causing it? And there's really two avenues here that we're exploring. The first one is looking at whether it's just that the water coming through the system is vected. And so the water that's at the deep ocean is relatively old. And what this is showing is this is essentially an age estimate from transient tracers using CFCs. So blue here is showing waters that are relatively young. It's more like a decade before the deep water gets from the surface into the deep ocean, versus yellows, which are more like 30 years, and reds saying that that water is really most likely over 80 years old. And so one of the questions we have is, we're seeing warming in areas that is still very, very old water. And it shouldn't have been influenced necessarily by the climate system quite that quickly. But there is a second mechanism that we're still trying to understand better, which is when we have strong convection. So if you think about this as a layered system where we have deep water being produced, so this is showing strong deep water production, we have this nice swath of Antarctic bottom water that's continuously adding cold water to the deep bottom part of the ocean. You're going to have warm water above it, which is diffusing heat from the surface, and through various mechanisms where we can mix heat down. So you have warm water sitting above. But if we had a situation where you slowed or you weakened the deep water production, then you would very quickly see a contraction or a falling, a decrease in that amount of cold water, an expansion of the warmer water above. And in this way, if you looked at a given location, it would look like an increase in temperature, when really you're seeing an imbalance between the renewal of the cold weather coming in and the diffusive rates of heat coming down. And we do have some model support behind this. So over on the left is the same zonal mean that I showed from the observations. And then on the right, it shows a model where from an ocean model, this is a Lee et al. 2023 paper, where they forced the climate system and they saw a very steady decline in the deep water production in the Southern Ocean. And then they looked at the warming, or they looked at the age difference, which is over on the right. And what you see is that water is just getting older, and that would equate to a warming signal. Okay, so pulling this together, here we can look at the surface ocean warming and the deep ocean warming, and make the estimates that we know. Right now, in the deep ocean estimates, which is something I personally work on, we at best can really look at decadal changes or multi-decadal changes because we just don't have enough data. Versus in the surface ocean, we can look at month-to-month changes at a given location about how there's fluctuations in the heat. And so by extending Argo into the deep ocean, it means we will have a really much better picture on a month-to-month basis, year-to-year basis of how the ocean is changing. And then in the last 2 minutes, if 2 minutes left, I just want to talk a little bit about the future of Argo. I talked a little bit about core Argo mission and the deep Argo mission. In addition, there is the expansion into the biogeochemical sensors. And so over on the right here is shown a BGC float. And these BGC floats are going to allow us, in addition to measuring things like ocean heat content, to be able to measure oxygen, pH, nitrogen, chlorophyll, backscatter, and downwelling irradiance, which will tell us about deoxygenation, carbon uptake, nutrient availability, and some information about primary production and phytoplankton. And so the idea is that in the future, leveraging the technology and existing data structure data system that we have with Argo, if we could turn a third of our Argo floats into deep floats that go all the way to the bottom and a third of them into these biogeochemical floats, we would be able to really expand our knowledge and understanding of the ocean. And with that, just kind of a note on where we are. So I think BGC has had this huge effort to kind of push forward over the last few years, and it's about 70% of the coverage that we need. But Deep Argo is still only at about 18% of the program implemented to get global coverage of the deep ocean. And looking forward, because we were asked to kind of say a little bit of about the future of it. So the U.S. at present contributes over 50% of the global array, and about 50% of the cost of that program. It is a semi-expensive program, but in the grand scheme of things, we think we're very cost effective. So compared to ships, for example, it is very cost effective. So we're getting a profile for about $270 per profile. And if you've ever been on a ship or done any field work, you would know that that is a pretty good deal. At the moment, 85% of the active floats were funded through NOAA, and about 15% were funded by NSF. We just got notification, and that 15% represents all of the BGC floats in the US, or most of them. At the moment, we don't, the NSF grant that was funded off of has ended, and there's no follow-on. And so what we're looking at in the next years is a 15% decrease in the overall Argo array, and really representing all of those BGC floats to decrease. And with that, 1 minute over, but I want to thank, again, the organizers. Put this website for more information about Argo and the Argo logo, and thank NOAA for their continued support of the program. And I can take questions.
All right, thank you so much. I don't know if you were watching the chat, but there's massive love for Argo in the chat. People are going absolutely crazy for it. And we have a couple great questions, and I'll just put them up on the screen. So first of all, what makes Deep Argo sink deeper than normal Argo?
So we're, again, just leveraging the same information, the same, it's the same as the core Argo float. So we are going to change its density. And so with the Deep Argo floats, because they go from the surface all the way down to the deep ocean, we need to have a larger relative volume change. So we actually do that by making them, they're a little bit smaller, but to change its density, we are changing, because the mass stays the same, so it's mass over volume. So we just have a bigger relative change in volume that we can do to make them get all the way through the water column. And I guess we could do that with a core float too, but the main difference between them is the crush depth. So with the core floats, if they get much below 2 kilometers, they are going to crush from the pressure. And so the Deep Argo floats, I didn't show you the guts of it, but it's within a glass sphere. And that glass sphere is actually the best that we found material that will allow us to get to the very, very high pressures that we get in the deep ocean without crushing reliably. So yeah, good question.
So interesting. So next question is from Kelsey. You mentioned earlier that the average lifespan for an Argo float is around 10 years. What happens to them when they no longer work? Are they recycled or scrapped or something else?
So right now, for the most part, when they reach end of life, they just sink down to the bottom of the ocean. We did a pretty extensive environmental impacts report, we being the International Argo Program. And what we found was one of the biggest environmental impacts of the float is actually the carbon that we use to deploy them. So to get them out into the ocean, you have to put them on a ship. Most ships, we do try to use sailboats when we can, but I would say 99% of them are going out on ships that burn carbon. And this is actually the worst thing that they do for the environment. And so if we needed to pick them up, we would be doubling that cost, that carbon cost. And so as a result, what we do is we try to make them with materials that are the least impactful on the ocean. And so with the core floats, it's mostly aluminum, which is not a terrible thing to have in the ocean. Or with the glass one, glass is obviously not a terrible thing. We want to minimize the amount of plastics, and then there are batteries in them. And so that's probably the worst thing to leave in the ocean. So it is something, I mean, we're all very environmentally conscious, obviously. And so it's not a perfect solution, but it is the best solution that we have right now, unless someone out there wants to invent a biodegradable Argo float, then we could start looking at other things. But right now they just sink down to the bottom and float, basically.
It's cool to see how you think about the whole life cycle of the float, though. That's really interesting. Next question. Do scientists get attached to and project onto the Argo floats like we are in the chat? Do you feel like it's more of a coworker or more like it's a tool?
That's a good question. Well, I would say if you are feeling particularly sentimental to a particular Argo float, we do have the Adopt the Float program, which is one of our outreach programs. There's a few Adopt the Float programs. You can reach out to anybody basically in the Argo program. It's mostly geared towards elementary, junior high age kids, where a classroom can adopt a float. They then get to name the float and decorate the float and follow the float on its quest into the ocean. Our lab produces about 80 to 100 floats a year. And, I love each one individually. I think that they are great. I like to see them getting decorated and kind of named by various people in the community, but they are fun for sure.
Based on the chat, it sounds like you may have some more adopters coming your way. The next question is, how dependent is the entire array on U.S. satellites continuing to retrieve the profiles? And does a risk to the satellites mean that the whole international effort would be at risk?
So they use, most of them right now use Iridium. And so as long as the Iridium, so we use commercial Iridium providers. So if those went down, then that would be problematic. But for the most part, hopefully Iridium communication doesn't completely go away. So we are reliant on that. We do try to diversify as much as possible. So kind of the U.S. Iridium provider isn't necessarily the same as many of our international collaborators. And we've used different companies as well as like DoD in the past, and so some of them are DoD. Yeah.
Interesting, but hopefully, there's enough diversity in the system to keep it up no matter what happens. Great. We're almost out of time. Giving another second in case anyone has questions in the chat, just because people are so incredibly excited about this. You should go back and look at the chat on the YouTube if you're not. People are really, really into this project and into these little floats. I am just so interested. Oh, I also wanted to shout out, people were really appreciating the maps and charts and the different types of projections. If you wanted to say anything really quickly about the types of ocean-focused map projections that you were showing, because people were really thinking those were beautiful.
Yeah, for the Argo, like most of are coming from Ocean Ops. I should have put that on there, which supports a number of the ocean observing networks, but they are publicly available and updated monthly, monthly. And hopefully the link is on here, but I can put it here. So oceanops.org to produce all of these nice plots, and they're great. And they give you up-to-date numbers on all the different types of floats, and you can look at a number of different options on how projections and various other things. So that's great.
Amazing. Thank you all so much for all of your excitement in the chat. There are actual plans happening to adopt various floats with different programs and everything, and including the group that is on the chat right now. So love that. And I really hope this happens. And thank you so much for sharing everything about Deep Argo. Sarah, thanks for joining.
Yeah, thank you.
Have a great rest of your night. And with that, that is also the end of my hosting time tonight. You can see the sun went down during that last talk, and I did not have time to turn the lights on. So I will go do that and bring up our next host, McKenzie, and pass it on over to you to host the next section. Thank you so much.
Yeah, thank you so much, Haley. Thank you for all that you've done. It's been really great. And still daylight here, so I'm over in Colorado, but it'll probably set now during my session as well. So, but yes, thank you so much. So hi, everyone. Welcome to hour 29 of the Weather and Climate live stream. My name is McKenzie Larson. I'm a fifth-year PhD candidate at the University of Colorado Boulder, and my research mostly focuses on Colorado downslope windstorms and winter storms. And I'm really looking forward to spending the next 2 hours with you all as your host. But before we start, I want to remind everyone why we are here. And that is because U.S. scientists have been world leaders in weather and climate prediction. We have some of the first computerized weather forecasts happened here. We are also home to developing very complex models of the weather and climate. We also have a very vast observation network ranging from space with satellites, going down to plane, airborne measurements, all the way down to land surface measurements on boats and floats like we just talked about in the last talk. And all of this amazing research that's done in the US is all thanks to you, the public, because our taxpayer dollars are what allow for US federal funding. That's essential for our field and to continue the research that is going on. However, currently the administration's proposed budget for fiscal year 2027 is currently jeopardizing this research and the scientists that conduct our science. Currently, there are proposed cuts in half for the NSF and NASA's Earth science budgets. And another big question that a lot of us have, especially myself, is how can we train the next generation of young scientists to better inform our weather forecasts and climate understanding if all of these cuts happen? So for example, for me, so I'm a graduate student, I have very thankful to have a federally funded fellowship that allows me to conduct my research. So without mechanisms for supporting and empowering young scientists, what will happen in the future. And so we've already seen negative impacts from funding cuts, such as short-staffed weather forecast offices, shrinking and shuttering of research labs. We've also talked about when I was hosting overnight around midnight Mountain Time, we were talking about summer internship projects for undergraduates, which are really, really important for especially for me, especially, as well as a lot of other folks that I've talked on here as well, really informative experience to get you to where you are today within the weather and climate research realm. So I want to encourage everyone to visit our website, wclivestream.com/call or /act to contact your representatives and senators to protect our weather and climate research. And so now we're going to continue on to our third hour of keynotes this evening. And our next speaker is going to be John Morales, who is an award-winning broadcast meteorologist and hurricane specialist, who will be talking about the Great Miami Hurricane of 1926. So welcome, John. We're so excited to have you, and please take it away.
Oh, thanks so much, McKenzie. It's great to be here speaking to you today from the studios of WTVJ. It's South Florida's first TV station in Miami. I was chief meteorologist newsroom that you see behind for, well, let me see, I think it was 13 years. And prior to that, I worked for 2 other television stations as chief meteorologist here in the Miami market. So all in all, over 3 decades as chief meteorologist down in this area. But importantly, that followed a career in NOAA and the National Weather Service. At the very onset of my career in the 1980s and the very early 1990s, I was an operational meteorologist working for the National Weather Service in those important field offices that, if you recall, last year's weather and climate live stream, we were so trying to protect. And indeed, our 30,000 calls and contacts to our electeds, to representatives, did play a role, because in the end, appropriations committees on both the Senate and in the House of Representatives pushed back severely on the Trump regime's indiscriminate cuts to NOAA and the National Weather Service, cuts that have cost us severely in terms of our ability to properly monitor, forecast for, and warn for extreme weather events that can not just take lives, but also ruin lives. So what we're attempting to do this year in this new Weather and Climate live stream is to not just remind ourselves of those challenges and hope that we continue to get pushback from Congress to the draconian cuts that are being set forward by the White House, but also think of some of those national labs, right? Like NCAR, like NSSL, the National Severe Storms Laboratory, which would be on the chopping block if the White House had its way. The Hurricane Research Division right here in Miami, and so many other crucial aspects of basic research that have helped put this country where it's at over the last 80 plus years, and that due to the sledgehammers attacks that we've seen on science have sadly set us back. And well, this could very well take not just a couple of years to fix. It could take decades, perhaps even generations. Hopefully, we will turn the tide on this. And in the meantime, I do want to present tonight on the great Miami hurricane of 1926. This is the 100th anniversary of that Category 4 hurricane, which struck Miami with a very wide wind field that impacted not just a few communities in, call it, Miami-Dade County. So we'll immediately bring the comparison to Hurricane Andrew from 1992 to the forefront here, because I want you to realize that while Andrew was a Category 5, it had such a compact wind field that in the end, it was only southern Miami-Dade County that got impacted, 34 years ago by that hurricane. And, you know, if you lived in Fort Lauderdale, even if you lived in northern Miami-Dade County, what you saw there was nothing like the area where the radius of maximum winds hit, which was from Kendall Drive, if you're familiar with South Florida, at Southwest 88th Street, down towards Homestead and into the upper Florida Keys and Key Largo. That was ground zero for the impacts of Hurricane Andrew. I'm going to show you a graphic here that's going to compare the wind field from the Great Miami Hurricane of 1926 to Andrew's wind field, and you're going to see what a humongous difference it is. And one of these days, there's going to be another hurricane like the Great Miami Hurricane of 1926 that will strike South Florida. And when that day comes, we're bound to have the costliest disaster in the history of this country, just because there's so many more things in harm's way down in this area. And when you look at the track of this hurricane, where it hit, what its intensity was, you're just going to think of what that might look like in the present era to have an event like that. So let's get into it. Thanks for putting up with me here during my opening remarks. So, you know, think of when this happened, right? 1926. So we're coming off of some very serious disasters. You know, the Great Chicago Fire, right? In the late 19th century, Chicago had its fire. Early 20th century, San Francisco had its earthquake. And then South Florida had its hurricane. And all three events are to a degree comparable in terms of the impact, the magnitude of what was observed because of these disasters striking these different communities at this time. Now, here's the track of this system. And again, we need to place ourselves in that era, right? So this is prior to satellites, prior to radars, and greatly we were relying upon ship reports. Or if a tropical cyclone happened to cross over an island that was populated, we would get reports from there. But this hurricane didn't strike those islands. This hurricane passed just to the north of the northern Leeward Islands, which are part of the Lesser Antilles. It passed north of the Virgin Islands, north of Puerto Rico. And it wasn't until it got to the Turks and Caicos that we actually got in situ reports of what was going on with the intensity of the system, which indeed went through a rapid intensification cycle like the ones that we're seeing a lot more often these days. Well, they would happen back then too, right? It doesn't mean that we couldn't get rapid intensification cycles even in the era before global warming has led us to the precarious situation we're in right now. They could happen back then as well. And this system went through rapid intensification. It became a very strong Category 4 hurricane, struck the Turks and Caicos. Many were left homeless with thousands of structures destroyed. Then it crossed the Bahamas and eventually into South Florida. Now, you'll see that track across Miami proper and across the southern portion of the Florida Peninsula. And to a degree, it's not quite the same track as Hurricane Andrew, but to a degree, you're reminded of Andrew because of that east to west movement of the hurricane as it was crossing through this area. So, for sure, a storm surge was a part of this for, well, not just the Turks and Caicos and the Bahamas, but certainly South Florida. At a time when this area, when South Florida was growing very, very quickly, and we're going to be talking about that too. Let's look at the tail of the tape from this hurricane. Just incredible statistics. Landfall near Perrine. Perrine, Florida is not far from Homestead. All right, these are neighboring communities in southern Miami-Dade County where Andrew struck, except the wind field in this system was so much larger that we saw a much more massive impact of it as it was crossing the area. Large radius of maximum winds. We had maximum sustained winds of 145 miles per hour, which makes it a solid Category 4 hurricane. So what's a comparison of a Category 4 hurricane? Hurricane Maria in Puerto Rico was a Category 4 hurricane when it struck that area. So there's one comparison. And because wind gusts in hurricanes are often no less than 25 or 30% above the sustained winds, but often can reach 50% above the sustained winds, gusts in this particular hurricane, the Great Miami Hurricane of 1926, likely reached 200 miles per hour. The barometric pressure, a record at the time for a U.S., for anywhere in the U.S., the lowest barometric pressure ever measured in the United States at that time was brought by this hurricane, 930 or so millibars, 27.5 inches of mercury. Keep in mind the normal barometric pressure. If you look at a mercury barometer right up on a wall, and the column of mercury is in a normal condition supposed to reach 30 inches, but the pressure was so low that the air molecules could only push up that column of mercury up to 27.5, 2.5 inches lower than where it normally would be. Gives you an idea of just how low the pressure was in this particular hurricane. Now, keep in mind, nowhere near the record. The record for the Atlantic Basin is 882 millibars, which is below 27 inches of mercury. So that's Hurricane Wilma from 2005. But nevertheless, this was a formidable system. Storm surge. So we talked about the winds. Of course, they bring rain. Might have been some tornadoes in Florida for sure. But we had a very deep storm surge in a place where storm surges like the one seen in Katrina in 2005, or like the one seen in Camille in 1969, are simply not possible. Okay, so I want you to understand that having 10 meters of storm surge, or 30 feet of storm surge in the southeast coast of Florida is a physical impossibility because of the shoaling characteristics of the bottom of the ocean floor. It's too deep, too fast offshore here. There's no platform offshore that makes all that water just rise so much more in a place like Mississippi, in a place like Louisiana, in a place like Alabama. Here on the east coast of Florida, you just physically cannot generate a storm surge that's 30 feet high. But you can certainly generate this type of a storm surge, which was very impressive. 14 to 15 feet above ground in the Coconut Grove neighborhood just south of downtown Miami, 12 feet in Miami proper, 11 feet in Miami Beach, which is a barrier island. All this happening the morning of September 18th, 1926 at around 8 o'clock in the morning. Now, Hurricane Andrew was really puny by comparison in the sense that the wind field was so much smaller. This was, again, these are quotes from the Miami Herald in an article during a previous anniversary of this hurricane. The hurricane strength winds expanded across 135 miles instead of just 25 to 30 miles. And because of the slow movement of the hurricane, because Andrew was moving so much faster, this extended during many, many hours from many parts of southern Florida. Now, this is going to be tough because I'm not sure. Oh, yeah, I think you can see my cursor. Okay, this is good. This is excellent. So there's Andrew's wind field. I don't know if you can see the label there. It says Andrew down there. And this was the wind field in Andrew. And the Great Miami Hurricane is this wind field here. I mean, it's got to be double, if not triple, the size of the wind field of Hurricane Andrew. Now, and we'll talk about this later on in my presentation, but you can imagine, even if it struck near Perrine, Florida, in southern Miami-Dade County, with Miami, the heart of the city, and the part of the city that was being developed 100 years ago, right near the Miami River, right? The part of the city that is several miles removed from Perrine would have had a much, much greater impact from the Great Miami Hurricane of 1926 as compared to Hurricane Andrew in 1992. And there's the wind fields of several other hurricanes if you're interested in what that looks like. All right. So I spoke about the time in which this struck, the time, the era for Miami. There was a humongous boom in the city going on at that time. The Gilded Age, mid-1920s, prior to the stock market crash of 1929 and the Great Depression, right? Well before that. There's a lot of real estate being sold in South Florida. A lot of folks are buying plots of land left and right. We can go off on a tangent of the environmental degradation that ensued because of that, when basically the Everglades were being drained in this area, and ecosystems suffered tremendously because of some of the canals that were being dug for the purpose of drying out the land and for the purpose of this boom. But the truth is, it did happen, and there was an immense boom going on down here, where developers were buying things left and right. Look at the statistics. Just in those 6 years, the population grew from 42,000 to well over 100,000 people. So we more than doubled the population. And look at the other statistic: enough lumber arriving in South Florida to encircle the equator with an 8-foot boardwalk. just an incredible time in this area, to a degree comparable with what's going on right now. You've probably seen, glitzy magazines with pictures of Miami on the cover, and how Miami has become this international cosmopolitan city, which it wasn't, say, 20 or 30 years ago. And with that, a great amount of inequality has come to the city. It's been accentuated in really very difficult ways in this area. But Miami is in a boom right now. Real estate prices have been shooting through the roof. We have a lot of people from finance, finance companies that are moving down here, tech companies that are moving down here. But you know what? We haven't had a major hurricane strike in South Florida since Andrew, because where Hurricane Irma in 2017 brought us 80, 90 mile an hour winds, Hurricane Wilma in 2005 brought us maybe 90, 100 mile an hour winds. Those were gusts. They were not sustained at 145 with gusts to 200. We haven't had that since Andrew. And 34 years is a long time. And I'm fearful for when we get the next Great Miami Hurricane of 1926, because again, I am telling you, it will become the costliest disaster, not just in the history of Florida, in the history of this country. Look at some of the pictures from 1926. Our skyscrapers from back then were going up in some parts of the front of Biscayne Bay. So as you know, Miami Beach is right on the ocean, but it protects the bay from those ocean waves. And then off to the west of Biscayne Bay, that's where Miami sits, at the mouth of the Miami River. And this was what you were seeing back then at the time. And here's what's really interesting about this year. There were other major hurricanes that happened in 1926 prior to the Great Miami Hurricane. There was one in July that struck Florida. And there was one later as well that struck from the southwest. It was a very busy year. And for some people with great perception skills that have street smarts and are aware of their surroundings, news did spread about some of these other systems. And some folks took it as a warning of what could come. And indeed it did. But it's interesting to see that, we don't have to be in the year 2025 like last year when we had 4 of the 5 hurricanes become category 4s or 5s. 1926 was quite the busy year too in terms of intense hurricanes. And going back to what I was talking about in regards to knowing the status of the hurricane when there's no satellites and no radars and you have to depend only on ships and on reports from the islands, warning for hurricanes was hard too. Again, we're not keeping track of them in real time. We're getting reports from the Turks and Caicos. We're getting reports from the Bahamas. We're doing what's known as single station forecasting, and we're sitting in Miami looking at some high cirrus clouds that might be arriving, and I go, wonder what that is. Then having a weird wind direction, or maybe starting to see the barometric pressure fall in your home barometer. Or as often happens, having a hellaciously hot day with bright, very hot sunshine in the day prior to the hurricane, right? All signs, when you do this single station forecasting type of scheme, that there might be something on the way. And as you read this, right, and you look at some of the September logbook from the local weather bureau, indicating what was being observed in the days leading up to the hurricane, just your standard rainy season stuff, right? Sunshine followed by thunderstorms in the middle of the afternoon, and then suddenly a hurricane is at the doorstep. Very difficult to warn populations. If you ever have read Isaac's Storm, about the 1900 hurricane in Galveston, Texas, highly recommend that you read that so that you get an idea of what it was like to try to warn populations on very, very, very short notice that a disaster was at the doorstep. So scores of people dead in this hurricane, tremendous, tremendous damage to the city. And it basically stopped that boom in its tracks. There was, again, a tremendous growth to the city at the time and the county as well. And in the aftermath, yeah, there was a lot of, people coming together to help each other and try to recover. But at the same time, the area took a big financial hit, which was only compounded by the start of the Great Depression that began in 1929. So this is an interesting one. Pardon me as I lean over and read things here, but it's a little bit small for me. Martial law was enacted at the time. I'll bring this up very briefly because I don't have a lot of slides about it, but you can look up some of the racial challenges that went on, Florida, 1926. You can imagine how it was down here for frontline communities, for the, a lot of the immigrants that we had here from the Bahamas, which are still, have flourishing communities here today in places like Coconut Grove. Those folks were just getting here at the time and suffered tremendously because, of course, they were being marginalized at the time. But anyway, there's a picture of some folks, I believe, in Hialeah after the hurricane, additional pictures of the disaster at the time, and a few more. And I'm going to get to eventually, I wonder if I have this picture in here. Ocean Drive, another view. Oh, yeah. Here's my reminder of racial inequalities. Look at the caption for the picture on the right. There was an actual headquarters for that back then, believe it or not. Well, they got damaged. Good thing. Anyway, more pictures. I digress. But this is important stuff, right? I mean, we got to remember where we've come from. This is the type of history that is getting shunted in this country and set aside, particularly in the state of Florida, where you can't teach that anymore, right? Anyway, I was told to not speak of these things as much, so I'll try to hold my mouth. I love this quote. Look at the quote in the upper right. Talk about these natural protections that we have that no longer exist in many places because they've been uprooted. The mangroves underneath seem to have acted as mattresses in preventing erosion and keeping the storm surge from getting so deep. Love that. These are some of the solutions now that we see, communities scrambling to try to go back to because of the importance of natural solutions that were there in the first place, right? And we tore them all up. I like this positive note here about, again, the community coming together, neighbors helping neighbors, folks, trying to get this area to come back from what was quite a terrible disaster at the time. And this is it's funny because Miami is a city. It's a great place. I mean, listen, the cultural diversity here is wonderful. Puedo hablar español with everybody because soy puertorriqueño, right? And it's wonderful in that sense. You visit down here, there's a vibrancy. And especially when you get to meet, don't just go to the glitzy places. Meet everybody. Right? It's great for that and seeing all those communities. But one thing is that this place is people are working so hard to make ends meet. It's so expensive to live down here, rents and homes and everything, that sometimes families, the heads of households are working 2 jobs, 3 jobs just to make ends meet. What I'm trying to say here is that oftentimes there's no time to meet your neighbor. There's no time to interact with others. It's tough in that sense. But when these disasters strike, you see a lot of this: neighbors helping neighbors, greeting each other for the first time in months, asking what you might need. I wish it was like that more of the time, but certainly when disasters strike, we do get that. Interesting tidbit: the University of Miami. I did not go to the University of Miami, nor am I affiliated in any way to it. But I can tell you that the Hurricanes are named the Hurricanes because of this hurricane. They had a great football team, but their games got delayed by this. And did you know that the ibis, the mascot for the Miami Hurricanes, the ibis is often the last bird to leave and the first bird to come back after a hurricane strikes. So it's a tough bird and a valiant bird. And therefore, it's the mascot for the University of Miami Hurricanes. All right. Now, let's jump to the present. Let's think of Category 4 and what it means on the Safford-Simpson scale. And there's your definition right there. Remember, Safford-Simpson scale no longer talks about storm surge. It's exclusively a wind scale, and it describes what you might expect with Category 4 conditions. Well-built frame homes can sustain severe damage. Trees uprooted or downed, power outages, not just for a day or two, but potentially for weeks. In the case of Puerto Rico, it was months, right, when Category 4 Hurricane Maria struck. Now imagine this happening, a Category 4 hitting in the present era, in densely built out, extreme sprawl megalopolis, South Florida, where the city starts in Homestead and doesn't end until you're past West Palm Beach, because it's city after city after city after city, everything paved over. Almost every single home might have cinder block walls and stucco on the outside, but you know what that roof is made of? Wood trusses with plywood paneling on top, a few nails, and either shingles or tiles on top. That's it. It's not cement. It's not poured concrete over rebar like it is in places like Puerto Rico, like I grew up, where the homes are stronger than they are in this part of the United States of America, or the majority of the United States of America, right? Imagine what's going to happen when we get another Cat 4 striking us. Well, that's actually been studied. So there's your citation: normalized hurricane damage in the US, 1900 to 2022. And Katrina is number one for sure. But if you normalize the Great Miami Hurricane of 1926, it would be the second costliest disaster in the history of this country. And I would argue the costliest. I mean, Hurricane Ian in 2022 became the costliest disaster in the state of Florida, north of $100 billion in damages. I argue that if you get the Great Miami Hurricane striking in the same intensity, same wind field, same angle of approach, where much of the metro area in Southeast Florida gets struck, and I already described that megalopolis to you, it's going to top 150 billion and possibly approach $200 billion in damages. So in this era, in which the propensity for tropical cyclones to reach Category 4 and 5 magnitude all across the tropical belt of the planet is greater than it was in the past. Human caused, right? Because of the injection of greenhouse gases into the atmosphere. Well, even in an El Nino year like this one, where all the buzz is about how inactive the year might be in the Atlantic because of the super El Nino, quote unquote, there's bound to be a string of 4 days, 6 days, 8 days in which we don't have the wind shear, in which the sea surface temperatures of the Atlantic or the Gulf are near maybe not record levels like we saw in 24 and 25, but still pretty darn hot compared to normal, where we have the fuel present without the impacts of the El Nino that could lead to rapid intensification and the potential for another a great hurricane like the 1926 hurricane. So with that thought, I ask you to not let your guard down during the 2026 hurricane season in the Atlantic. It could still be dangerous. It only takes one. And that old adage of it only takes one is much more important in this era of climate-fueled extreme weather disasters than it was in the past. Thanks for your attention, and we've left a little bit of time for questions.
Awesome. Thank you so much, John. That was a really, really great talk. Can you hear me all right? We're good? Yes,
I
awesome.
can, yes.
Okay, perfect. Yeah, this is a really great talk. So I'm in Colorado now and I have been for a while, but I'm from South Florida, closer kind of to the Everglades. And what made me wanted to get into weather research was absolutely Hurricane Irma. So I remember kind of my high school football field was flooded and there were fish from the canal in there, and it was just fascinating. But
I know where you went to high school.
Yeah.
All right. Anyways, we digress.
Yeah, we could talk after. But kind of leading into how you ended your talk and talking about how we all need to be prepared for the summer, there was a question from Tree that asked, what can communities do to be more prepared for this upcoming hurricane season and the current hurricane season?
Yeah, great question and very important question. So, first and foremost, you have to make a plan. And the only way you can make a plan is to know what the vulnerability of your house or your neighborhood or your community is. And it's different for every community, right? Some, and if you're from South Florida, you know this well. Some communities are so close to the water or at such a low elevation that storm surge is a factor. And no matter how strong your house is, it's not going to be able to stand up to a storm surge. So what do you need to do? You would need to have a plan that includes evacuating that home because, it might withstand wind, but it won't be able to withstand the storm surge. So first, you know your exposure and vulnerability. Then you make a plan. The plan, it must include your household nucleus, put everybody to work. Make sure everybody has a task so that you properly prepare your home. And if you're going to stay in it, great. Make sure it's properly protected, that you keep the wind out at all costs. Don't be opening windows on the lee side of where the wind is hitting, because that's not right. Okay, that only makes it worse. You need to protect the envelope of the house with shutters to make sure you're secure in there, and have the supplies that you need, not just for 2 days, not just for 3 days, but possibly for a week. You need to stay well informed, so that you need to charge all your devices and have the ability to continue to do so after the hurricane. If you're going to use a generator, you're not going to use it indoors because you will die from carbon monoxide poisoning. Yes, believe it or not, some people, turn on their generators inside the house. Okay, that's why I'm bringing that up. And then listen, evacuating, if you need to evacuate, evacuations are not the same for all families. For some families, it's hard to make that decision because it's costly. And you may not have the means to transport yourself and your family out of harm's way, or you just can't afford it. So you need to check up on others, make sure the authorities are checking up on everybody. And yes, do listen to the recommendations from those, whether it's the civil defense or emergency managers or police. Make sure you follow the instructions and recommendations, because oftentimes people think that they know what storms are going to do because of their lived experience. And they'll say, I've lived here 30 years and nothing has ever happened, so therefore nothing's going to happen this time. You know what? That lived experience could lead you astray, and so many people die because they stay in place and they don't listen to evacuation orders. So make sure you follow instructions.
Awesome. Very, very well said. I think we have time for one more question. This one comes from Sydney. This is was put in the chat when you were showing the different plots of the other storms that happened in 1926. And so she's asking, does it change the impact based on which direction the storm approaches from? So like the angle of approach that you were talking about, and how does that impact people?
It absolutely does. So that is particularly true for the storm surge, because the shape of the coastline, whether it's convex or concave, the way the bottom of the ocean floor is shaped and how quickly it drops off offshore plays a role too. The speed that it approaches, the width of the wind field, all those things are crucial in terms of determining how deep and how far inland a storm surge is going to penetrate. And you know, McKenzie, I know you know this very well, having lived here in South Florida. There are some communities, you know, say east of Highway US 1, which are always in the evacuation zone because they're too low in elevation and too close to Biscayne Bay to be safe. And if the hurricane is coming in at a right angle, and by right, I don't mean correct, I mean at a 90-degree angle, okay, to the coastline, and it's got a broad wind field, and the shape of the coast is so, and the bottom of the ocean is so, that can exacerbate the depth of the storm surge and make it worse. That's why I explained earlier that there are places along the Gulf Coast that can have a 30-foot storm surge, whereas that is a physical impossibility in Southeast Florida because of some of those factors.
Yeah, absolutely. We are waiting for our next speaker. So if you have time, would you be willing to answer a few more questions? Would that be all right?
I absolutely can, yes.
Okay, absolutely. Awesome. There was a good discussion in the chat about this, but I am excited to see your kind of more expert answer about this. Tree asked, are fast-moving or slow-moving hurricanes more destructive? Would fast-moving have stronger winds, but slow-moving cause more destruction in a given area?
Yeah, slow-moving hurricanes are definitely the worst in terms of rainwater, right? The slower the hurricane moves, the longer it's got to be able to deposit, imagine the rate of rainfall in a hurricane, right? So that rate of rainfall extending over more hours is definitely not a good combination. We know that empirically, we're observing slower moving hurricanes in the present era. And there appears to be a climate connection to that, having to do with a slowing jet stream and a more wavy jet stream, which is causing hurricanes to move slower. Combine that with the fact that a warmer atmosphere can hold more water vapor in it. Well, a slow-moving hurricane with the ability to hold more water vapor, what is that going to result in? It's going to result in worse flooding. We saw an example of that in 2024 with Hurricane Helene, when it impacted Western North Carolina, Eastern Tennessee, and some of the surrounding areas with just incredible amounts of rainfall that led to just horrible erosion in the mountains, flash floods in the lowlands, and river floods in some of those rivers that were of historic proportions. So Asheville and some of those surrounding communities got hit really hard by the remnant of a very powerful hurricane that deposited all that rain there. And while I'm on the subject of Helene, let's talk about what a faster moving hurricane can mean for winds. Because whereas for rain, it's worse to have it move slower. For winds, it's worse when it's moving faster. And Helene was moving at a great clip when it entered through the Florida Panhandle and into the state of Georgia. You know your geography, you know that the Panhandle in Florida is pretty short. Well, it's long east-west, but it's short north-south, right? So the hurricane quickly made it into Georgia and was moving so fast that the winds didn't wind down fast enough in the core of the hurricane. And there were 100-mile-per-hour gusts in northern and northeastern Georgia, 100-mile-an-hour gusts. So a fast-moving hurricane can spread stronger winds further inland. So it's a bit of a mixed answer to that question. It just depends on which hazard we're talking about.
Awesome. Wonderful answers to all these questions. Thank you for taking the time to elaborate on them and answer the questions from the chat and all of our viewers and providing this really, really awesome talk. With that, I think it is time to move on to our next speaker, but thank you so much again, John. There are still a few more questions in the chat if you want to hop on the YouTube live chat to talk. But everyone, please, in the chat, thank John for coming here. And yeah, that was really wonderful. Thank you so much.
Thanks so much for having me. Great to be part of this another year. And I know it's being very successful, and we're going to get a lot of people to contact the representatives and make sure that we protect science in this country.
Yes, absolutely. Thank you so much. And speaking of that, you can use the link that's down in the banner below on here, wclivestream.com/act, to go and contact your representatives. So now, before we move on to our next speaker, I'm going to remind everyone again why we are here. And that is because the United States and our scientists have been world leaders in weather and climate prediction. We have had some of the first computerized weather forecasts. We are hosts of organizations that develop complex models of the weather and climate. We also have a really outstanding observation network where we have satellites in space. We have field campaigns that take airborne measurements on planes. We also take measurements on boats on field campaigns, floats with like Argo floats that we talked about in the last session. And all of this amazing research and science advancement is thanks to all of you, the public, because our taxpayer dollars and is what allows for our US federal funding. And it's absolutely essential for our field of continuing to study the weather and the climate. And one organization in specific that you might have heard a lot about already if you've been with us on the live stream for a while, but if you're not, welcome. One organization that's really at the heart of weather and climate science research is the National Center for Atmospheric Research, or NCAR. And so some of the weather and climate models that we all depend on just in our daily lives are developed and maintained at NCAR. When you open up the weather app on your phone, kind of many layers back to those forecasts you're seeing are likely derived from these weather models that are developed out of NCAR. And personally, I love NCAR. I spent a whole summer there as a student visitor. It's what helped me continue pursuing downslope windstorm research here in the Colorado Front Range, which if you want to hear more about that, I'll be giving a talk at 10:40 Eastern time about that. And so let's see, we'll continue here. The time I had at NCAR really was amazing, and I still talk to all those collaborators today. And without my time at NCAR, I would absolutely not be the scientist I am today. So with all of the cuts that we've been seeing already with this administration, we've seen quite a few negative impacts already. We're having short-staffed weather forecast offices, shrinking of research labs in academia and beyond. Also, summer internship programs have been terminated as well. So we really do encourage you to look at the link that's down here in the banner below to call or write your representatives at wclivestream.com/act to help protect weather and climate research. So next, we're going to bring out Andrew and Virginia to talk about the next aspect of the live stream, what we're going to talk about here.
Hello. So for a last minute surprise, it's just me. So Andrew is one of the organizers for everyone watching, and he is on the phone with someone doing something last minute because there's so much going behind the scenes. So, right. So I wanted to come on because Andrew, who just ran upstairs, and I were talking last night about the changes that are happening and have already happened to the science landscape because of things happening in the government, and then all these proposed changes as well. So I'm a science communicator, which means that I am around science spaces a lot. I have a PhD. I have a background in ecology. And the way that Andrew called it when we were talking last night, he said he didn't realize that there were so many downstream impacts of funding changes and structural changes to the scientific system in the United States. So I just have been itching for a chance to make sure that people on the live stream know that one of the things we wanted to do with the weather and climate live stream is highlight how broad the science community is. So the federal science workforce lost 20% of all of its workers last year with the changes that have already happened because of the government. That's 25,000 people. And not all of those hold, research positions or scholarship positions, because there are so many people that make science happen. You think about the administrators who are there to run a grant. You think about the people who are there to literally manage computer access and all the admin things you don't think about in a building. And my job as a science communicator, I help connect people who are not technical specialists with what scientists are doing so they can use it and make life better and have great decision-making capabilities for whatever it is they're trying to do. So my funding sources the last, I would say, 3 years have been mostly NSF grants. NSF is a federal science agency, with some other federal funding mixed in. So I very selfishly, because I'm an organizer, like I said, just wanted to pop on and make sure that people know that we would like to preserve the scientific system, not just for the scientists and the researchers, but for everyone who makes science happen. And we want to give a specific shout out to all the people who you may not see here because they're not researchers, but they make science happen. I've been talking for a long time, McKenzie. This means a lot to me that people understand how big the community really is, how many people really make science happen, how many people are affected by government changes and policies, and then how many, I don't know, how much good can be done if we keep all of this going. If there's any questions in the chat about science communication or the downstream stuff, I know I see somebody say such chilling numbers. I just wanted to open up for a chat about the other people in education and science communication doing all that kind of stuff.
Yeah, I think that was all very well said. I could feel your passion through the stream, and I think it's wonderful, like helping organize this live stream and try to spread that message. I believe that our next speaker is actually here. If you want to switch over to Anne-Marie. Potentially.
Anne-Marie might still be getting their slides up. They are beautiful clouds and they are coming. I do see a question in the chat that you may have already addressed. Is there a list of the speakers somewhere? I'd like to go back and listen to folks that I'd missed. We haven't published a list of speakers yet because of the shifts in schedules that keep happening during the live stream. But when all of these recordings go up on YouTube, if you look back at last year's recordings, you'll see that there are chapters by speaker. So you should be able to, once these are all published, find your speakers or look through, a couple hour slot and see who was on during that time. Oh, and I see another question in the chat about the stream. Is it possible to participate in the stream next year? And someone said another stream next year. And then someone said, I love these things, but I hope we won't need a stream next year. Ooh, okay, so let me answer the question straight up. Is it possible to participate in the stream next year? If there is a stream next year, I know this year I got involved because the organizers from last year emailed everyone who played a role last year and just said, do you want to be involved? So if you let them know, like if you email us, oh, Anne-Marie's here. If Andrew's here, everyone's here. So I'll finish this one thing and then I'll hand it back. So Sydney, if you really want to get involved, make sure that you get in our system, like by filling out the volunteer form. And even if you just say, I'd like to volunteer for next year, but also Sydney, I think we have some overnight slots that are still available in the next 8 hours.
Yeah.
So if you feel like you'll be awake sometime in the next 8 to 10 hours, you could fill out our volunteer form now and see what's left over. Yes, Andrew, McKenzie.
All right. Anne-Marie, I think, can you just say 1 or 2 words quickly?
Hi, Andrew.
A couple words, that's great. Your slides look great.
Okay.
We're gonna head off. Excited to see your talk.
I love clouds.
Yes. Oh, awesome. Well, welcome, Anne-Marie. Anne-Marie Carlton is a professor at UC Irvine who's going to be talking about air quality, and we're all very excited. So please take it away.
Thank you so much. I want to say thank you to the organizers, and I have a real soft spot for young science activists, and I just want to thank you for inspiring me and for organizing this. I'm going to talk about air quality, and it's a Valentine to independent federal science. So one of the really cool things that EPA did when it first started in 1970 was they hired artists to go out and capture images of what the environment looked like near their home. And Chester Higgins lived near where I live. And so EPA still has this Documerica series on Flickr, if anyone remembers Flickr. But so Chester Higgins took this picture of the George Washington Bridge, or the GWB, in 1973. And now this is the photograph of the GWB from Wikipedia. And we can see that on the left-hand side, the air quality is a lot worse compared to how it is today. And my mom grew up in Queens, and I remember finding this Documerica and showing her this bridge picture, and I was shocked. And she was kind of shocked that I was shocked. She said that all of the bridges in New York City looked like this at the time. But the air quality here is a lot better. There is some haze in the background, but if the air quality was to look like this, it would be in the news. It's not an everyday regular occurrence like it was in the 1970s. I moved to California in 2017, and I intentionally worked to develop a West Coast perspective on air quality. And I learned from one of my friends and colleagues that Bob Hope used to say that he didn't trust air he couldn't chew. And he would say that, you know, from his studios in Los Angeles. And I really had to try to wrap my head around understanding what that meant. And this is what he meant. So this image I really love on the left is from 1954. So 16 years before there was an Environmental Protection Agency. And this comes from Brave New Films. And I think this image with the guy driving around with a gas mask is a really, really nice touch. And on the right-hand side, we're looking at the same exact building, except now you can actually see the building. And so air quality has dramatically improved in eastern cities like New York City. It's dramatically improved in western cities like Los Angeles. Right now, I don't live that far from the Angel Stadium. So this is the A outside Angel Stadium. And on this day, you can see the San Gabriel Mountains very clearly. They're quite beautiful. And on this day, you can't see the San Gabriel Mountains at all. One thing I want to point out is you used to be able to watch Ohtani play here for a lot cheaper than you can watch him now in Dodger Stadium. And the other thing I want to point out is that even though air quality has improved dramatically in the United States, since creation of EPA, since over my lifetime, it still very much remains a domestic issue. People sometimes buy and drink bottled water because, you know, they want to put clean water in their bodies. The volume of air that you breathe is much, much more than that. And so when you take a deep breath, you breathe in all the chemicals that were in that air, and those chemicals actually become a part of your body. And so it can be hard sometimes to have affinity for this thing that we can't really see, but that is constantly bathing the globe. And I'm going to try to help you care about air quality for just a few more minutes. So I've shown you these photographs that I think are compelling, but snapshots in time are not a robust way to evaluate trends. And so lots of researchers and the EPA and NOAA and even NASA using satellite data will make plots like this, where the x-axis is time, and then the y-axis is the mass concentration of some pollutant. And typically when visibility is poor, it's because there's a high concentration of particles in the air. And so what this trend is showing us is the decrease in mass concentration of fine particles. So particles that can make it very deep into your lungs when you breathe. And what we see is that the trend is going down. So this black line is the median, and then this is the confidence interval around the median. But there's something I want to point out, and that this average is really weighted towards the sites that we're taking measurements. So we're going to take a look at the actual sites that we're taking measurements used to make those plots. So here what I'm showing you is a map of the contiguous United States, and each marker on this map is a monitoring location that was measuring PM 2.5 mass during that time period. If the monitoring location is shown as a black square, then that means the trends in air quality improvements for PM 2.5 is within this black part. We call this the interquartile range. If the monitoring location is a green triangle, that means the improvement in air quality outpaces the national average. And if the monitoring location is a blue diamond, that means the improvement in air quality lags behind the national average. So there's a couple things that that jump out at me when I first made this plot. I'm from New Jersey, and there's a lot of green triangles in the United States. There's a lot of black squares in the eastern United States. There's a lot of monitoring locations in the eastern US. And where I showed you those photographs of dramatic air quality improvement, I showed you a picture from this area of green triangles, and I showed you pictures from this area of green triangles. But there's this whole part of the United States with blue diamonds where air quality is not improving. And one thing I want to point out is that this trend, as I've drawn it, is a percent by year. So that normalizes for how much pollution was there at the beginning of the time period. So, it's not just that, really polluted sites like have a bigger mass decrease. That's certainly true. But even as a percentage, we see that this part of the United States is just falling behind the rest of the country. So here's the thing about fine particle matter, or PM 2.5 in the atmosphere. Most of it forms in the atmosphere. Actually, it's not so much that particles are directly emitted, that does happen, but the majority of PM 2.5 mass actually forms from reactions of gas phase pollutants that condense into particles during transport. And the first time I heard about that, I thought it was magic, but it turns out it's just chemistry. So there are emissions from our homes. There are emissions from cars. I grew up in New Jersey, and so I put a picture of the turnpike. This is the largest road in New Jersey, and I just want to point out that that's about the same width as an exit on the 405 in Los Angeles. There's also emissions from plants and trees. So if you've ever smelled a Christmas tree or cleaned with pine sol, you've smelled those kind of compounds. There are emissions to the atmosphere from industrial point sources and also from things like fire. So there's all of these different gases that get emitted, and then as they're being transported throughout the air, they can form particle mass. And a lot of the particle mass that forms is very salty. In the cycling of the Earth system, what happens is there are emissions of compounds like SO2, sulfur dioxide, and there are emissions of NOx from cars, not just on the 405, but wherever they are. And then NOx becomes nitric acid when it gets oxidized, and SO2 becomes sulfuric acid as it oxidizes. And then ammonia is the most common base in the atmosphere. So you have an acid and a base, and then you make a salt. And so this is the magic that turns gas phase ammonia, gas phase SO2 into particle ammonium sulfate. And then gas phase ammonia, gas phase NOx, there's magic atmospheric chemistry, and then these gases turn into particles. The Environmental Protection Agency, the California Air Resources Board, the New Jersey DEP, they've been really successful at controlling emissions from SO2 from point sources, and also NOx from your car. This is why you have to get a tune-up and things like that. But the land sector has traditionally been difficult, and the largest source of ammonia in the United States is agriculture. And that coincides with the location of all those blue diamonds I was showing you before. So here what I'm showing you is a map from 2017. Again, I have a map of the contiguous US, and the deeper the blue color, the higher the concentration of ammonia. This is the very first satellite map I ever made using data from NOAA and NASA. So go easy on me. And then the other thing that I have on this map is each orange circle represents one of the top 5 most polluted cities year-round for fine particulate matter. And that data comes to us from the American Lung Association. Every year they put out a state of the air. So perhaps you see a pattern. All 5 of the top 5 most polluted PM2.5 cities in the United States during this time are in California. The deepest blue is right here in the Central Valley, and those are the top 3 actual sites. And then this is sort of near Oakland. This site is mostly due to fires, and then this site is the Port of Long Beach. And then the other thing that we see is that there is a lot of blue across the Midwest, and that is America's breadbasket. So here what I'm showing is data from the EPA, and each circle in this pie, or each slice in this pie, represents a different sector where ammonia emissions come from. This dark green is agricultural livestock waste. This light green is agricultural fertilizer. Some fraction of fertilizer is petrochemical, and then some fraction of fertilizer is livestock waste. And then all the other sources combined make up these other pieces of the pie. And what this data shows us is that emissions of ammonia from agriculture are a factor of 3 higher than all the other sources combined, including fires, which are growing in importance, especially in the Western US. And so why does this happen? I think that we all can sort of have bucolic notions about agriculture in the US. These cows look very happy, right? Like they just got out of their acupuncture, right? And they're headed to their yoga class. And the other thing I want to point out is that these clouds are pretty nice too. But that's not really what meat production or agriculture looks like in the United States. Most meat is produced in the US at these vertically integrated agribusinesses. And so I'm showing the photograph from a hog concentrated animal feeding operation, a cow concentrated animal feeding operation, and then this is chickens, and then this is another one, and this is what they look like from the outside. You see these are animals are underneath these sheds, and then these are lagoons. There are some CAFOs in the United States that generate as much wastewater as the city of Philadelphia, but they're not required to have wastewater treatment plants in the same way the city of Philadelphia is required to have wastewater treatment plants. Okay, so I have this idea, and this idea is that if you concentrate animals on land, you can exceed the soil carrying capacity. So if you have all of these animals together and they're doing what animals do, like pooping and peeing, the ground can sustainably take up some amount of that reactive carbon, some amount of that reactive nitrogen, but you can exceed the carrying capacity of the soil. So for example, I live on a cul-de-sac and there's about 13 houses. And if each house had one dog, say, in the backyard, there would be no problem. But if all 12 dogs were in one backyard, it would probably be a problem. You'd be able to smell it from far away. And so I started to develop this idea that where animal numbers are concentrated, you exceed the carrying capacity of the soil, and that is what the NOAA and NASA satellites detect from outer space. And I just want to point out that there are these really tiny, sophisticated instruments floating around in outer space, and they can make these detailed measurements. Okay. So this poor little plant, it just doesn't stand a chance in this environment. Okay, so one of the first things that we did to test this hypothesis was we went to look at the USDA, U.S. Department of Agriculture census. And the interesting thing is that the United States counts animals more frequently than it counts people. So the human census is every 10 years, the animal census is every 5 years. And the first thing I noticed when I started looking at the USDA Census of Agriculture is that the animal counts from the largest concentrated animal feeding operations are often not included, and they're actually deleted from the census. So if you look in the census, there'll be all these counties with numbers, but then sometimes USDA reports a D for deleted. So I'm about to show you some maps, and I'm going to show you animal units. And the reason why is I'm trying to normalize by the weight of each animal. So a beef cattle weighs more than a chicken, for example. And then the other thing is that laying hens and hens that lay eggs tend to have longer lives than broilers. So I'm accounting for how much animals weigh, and I'm counting or trying to take account for how long that they are alive. And we've counted this way for a couple different censuses. We partnered with an NGO once and started counting by hand. And we're recently developed a generalized linear model for the most recent census. So in 2017, what I'm showing you on the left-hand side is animal unit density. We see this red arc across the United States. We see this hotspot in California. We see the hog triangle. So in North Carolina, there's a research triangle. There's also a barbecue triangle. And then on the right-hand side, I'm showing you the average summertime ammonia from satellites in outer space. And I hope that something you see is there's a hotspot in California, and there's also this arc across the Western United States. And so my students and I did this thing where we gave our animal numbers to a statistician. And we asked him, can you make us a map of where the highest animal concentrations are? So he drew this black line on a map. He didn't have any access to the ammonia data. And he outlined this as the 91st percentile in animal unit density, developed from the USDA Census of Agriculture that we added animal numbers for. And what this means, the 91st percentile, you could imagine that you're in, say, you're in your first meteorology class, and then the professor takes all 100 exams and listen from the highest score to the lowest score. So people who got in the 91st percentile and above, like they would be the top of the pile. So that's what this sort of weirdish kidney shape looks like. And then he gave us that map, and then we overlaid it on the satellite ammonia data for that same summer. And when I looked at this, I mean, it kind of looks like we're lying, right? Like they line up so perfectly well. And one of the things that I think is interesting from an atmospheric perspective is that you can see ammonia is bleeding out of the level set, and that's because, you know, prevailing winds are to the east. Something else is that agricultural emissions also affect climate. So here I'm looking at US emissions of methane by source. So this part of the pie, natural gas and petroleum, is 32%. Landfills are 17%. But actually, if you take enteric fermentation, so this is like cows burping, and manure management, they actually add up to be more than natural gas. So EPA reports that agriculture is the largest source of two greenhouse gases. The first one is nitrous oxide, and that has a global warming potential that is 300 times greater than carbon dioxide, and also the largest source of methane that has a global warming potential that is 80 times carbon dioxide. And one of the things that I find frustrating is that agricultural methane is not regulated. And when we enter into international agreements, such as the methane pledge with the UK. I'm very excited about that. I think that was really great. But agricultural methane is exempt from the methane pledge. Another thing I want to point out is that N2O also can destroy stratospheric ozone. So in the atmosphere, there's the troposphere. That's the closest level to Earth. That's like where all the action is. And then above that is the stratosphere. And that's where the protective ozone layer is. And so N2O can destroy stratospheric ozone, and it has the fastest rate of growth in the South Pole. And it's also not covered by international agreements like the Montreal Protocol or the Kigali Agreement that is pretty young. And for me, that's sort of a global environmental justice issue because most N2O emissions are associated with agriculture. They happen in the Northern Hemisphere, but then we see that their destruction of ozone happens mostly in the Southern Hemisphere. I made this plot a little bit quickly. And here what I'm showing, the x-axis is time, and then the y-axis is the fraction of total greenhouse gas emissions from agriculture, and everything is normalized to CO2 equivalents. And what I want you to take away from this is that data is still pretty noisy, but there is an upward trend. And the reason why there's an upward trend is twofold. One, emissions from the agriculture sector are increasing, in part due to that consolidation. And two, other sectors are being regulated. Okay, so because I have the attention of really smart, civic-minded people, I wanted to take a moment to walk you through some of the policy and regulations surrounding agriculture and how this can come to be. Why is it that agriculture can pollute in ways that other sectors cannot? So EPA actually regulates ammonia under CERCLA and EPGRA. So that would be Superfund and the right to know, except when it's on a farm. So I could have, say, a barrel of ammonia. It's regulated. I take that barrel, I put it on a farm. It's not regulated anymore. I take that barrel off a farm, it gets regulated again. Isn't that bananas? In 2006, and I will tell you that my students say that that was a very, very long time ago. When you teach general chemistry, none of your students are born yet in 2006. So in 2006, EPA entered into a final order that any CAFO or any industry that owned a CAFO that contributed money, I would call it a nominal penalty, to fund a 2-year study to establish emission estimating methods for agriculture is protected from any civil or criminal activity associated with air pollution. But the EEMs, that methodology is still not finalized. And because it's not finalized, the order remains in effect. So sometimes people live next to CAFOs, but then there's little they can do about it. EPA's own Inspector General has asked them to end this final order more than once publicly. In 2008, the Government Accountability Office urged that better data was needed. And as a scientist, I always agree with that sentiment. NEPA, that's the National Environmental Policy Act. It's sort of like the Magna Carta of all environmental rules in the United States. And it exempts agriculture and CAFOs from some regulations. In the last Farm Act was passed in 2018. There hasn't been a new Farm Act yet. They're supposed to come out every 5 years. But the last Farm Act exempts any farms from any reporting requirements for animal waste. And then any year that I've looked, there's been a rider in the Appropriations Act that prohibits the issuance of air pollutions or air permits or require greenhouse gas reporting from animal manure management. Okay, so I showed you a lot of plots with trends and data and satellite images, but something that really inspired me was a story in the Sacramento Bee during the pandemic. And there was a photograph like this. And so this is farm workers. It's during COVID, so they have on masks. There's also this epic wildfire going on in the background. And I was at home. I felt safe, and I probably had fruit and vegetables in my refrigerator that they picked. And so abstract conversations about numbers don't move people the way images like this can. And I wanted to try to speak for them because they're real people. So if you take away anything from my talk, I hope it's this. Independent, federally funded science safeguards human health and the environment. And when politics intrude in that, we all lose. I used data that was publicly available and free from the Department of Agriculture, from the Environmental Protection Agency, from the National Oceanic and Atmospheric Administration, from NASA. And then at all those organizations, there were program managers, there were field technicians, there were data analysts. And I also want to thank the organizers that did this. I've been showing pictures here of different people who have contributed to this work. This is my son, Reese. I grew one of my own collaborators. This is Ben, Sally, Coy, and Harriet. And this is an image. I like to do fun projects. And at Valentine's Day, Coy had made a plot at one of her favorite sampling locations of PM 2.5 concentrations. So thank you so much for your kind attention.
Wonderful talk. Thank you so much, Anne-Marie. I think we have time for maybe a quick question or two that we'll go through. We're going to start with going back to that methane pledge question. Kelsey had a question. What was the reasoning behind excluding agricultural methane from the methane pledge? Is it because agriculture is considered so essential it can't be limited in the same way as other sources?
Yeah, I mean, I think that that's exactly right. There was no specific reason given. It just was exempt and not included. And it's really interesting. The Netherlands tried to do agricultural air emission rules, and it created a lot of political problems for that. And it was really interesting because I remember reading an article in The Guardian at the time, and the story was much like what you're saying, like, oh, they're just trying to grow food to feed the Dutch people. But then the protagonist in that story, he was producing meat that was like 80% exports. And so I think that is the idea. That sentiment is what people will point to, but I don't buy it, maybe.
Great. Yeah, good answer. Final question we'll do here is from LEB. Do satellites measure things besides ammonia, or are these satellites heavily specialized?
That's a great question. I love that question so much. Yeah, so NASA satellites and NOAA satellites, they detect other pollutants like NO2. There's hard to pick what to put in here, but I could have shown you a movie of NO2 declines. They measure PM 2.5. They measure aerosols. They measure methane, formaldehyde, glyoxal, the list goes on and on. And then, I use satellites to interrogate troposphere constituents, but other people use it to trace plate tectonics. Or when I showed you that picture of Angel Stadium, there was a waterway there that was completely empty. It's not supposed to be empty. There's supposed to be water there, and other people use satellite tools to investigate topics like that.
Wonderful. Thank you. And with that, everyone, please thank Anne-Marie for joining us and giving us a really great talk. There are still some more questions in the chat. If you want to hop onto the YouTube live stream chat, you can answer some of those. That'd be great. But yeah, everyone in the chat, please thank Anne-Marie again.
Thank you so much. It was so much fun. Thank you for inspiring me.
Yes, thank you for inspiring us too. All right, and with that, I'm going to do one final reminder before we move on to our last keynote speaker and just talk about why we're all here in hour 30 of the live stream. And that is because U.S. scientists have been world leaders in weather and climate prediction, and that is currently, all that funding is currently in jeopardy under the current administration. And all of the amazing research that we do in the weather and climate fields is thanks to you, the public, because our taxpayer dollars is what supports U.S. federal funding, and it's absolutely essential for all of our research. Recently, there's a current proposal by the Office of Management and Budget, or the OMB, that would drastically change how federal research is funded. One such example is that when professors and researchers are writing proposals to apply for funding, each program now needs to align with the administration's political priorities rather than scientific need, which is a shift from what had previously been designed for this process after World War II. So we've already seen negative impacts that we've been talking about throughout this live stream. And as you can see in this banner down here, we encourage all of you to please visit the wclivestream.com/act to contact your representatives and senators to help protect weather and climate research. So now we're going to continue on to our final keynote speaker of the night, who is Jeff Vallis, who's a climate scientist at UC Berkeley studying the atmosphere and ocean. He's going to be talking about contribution of national labs to climate and society. And just as a reminder, all of our speakers' views are their own, and they're not representing their employers or any other institution. So Jeff, we're really excited to have you here, especially some of you may not know on the live stream, but Jeff has written one of the main textbooks that a lot of us younger atmospheric scientists have used that has laid the foundation for our understanding of dynamics in the atmosphere and ocean. So I want to personally thank you for that. It's really wonderful. So looking forward to your talk. Thank you.
Thank you for the introduction. Can you hear me okay?
Yes.
Great. Well, I'm very glad to be here, and I'm very grateful for those of you who are listening. I'm not going to talk about my own research in this talk. I'm going to talk about the research which has done and is being done at national labs and how that is of benefit to science and society. Mainly, I will be talking about GFDL and NCAR. The reasons for that is that I worked at GFDL for many years, and also NCAR is currently under direct threat, as many of you know. I'll give a little bit of history of the labs, of what they did in the early days, then how did they develop tools, which many of us still use today, general circulation models, Earth system models, and LiDAR, oddly enough, which is now used in driverless taxis. Talk about some of the predictions that they've made about global warming, hurricane modeling, and so on, and some of the consequences that might have. I want to emphasize that I'm not going to make any assumption at all that global warming is bad. I'm just going to sort of try to state what it is. It's the need to know that is paramount, whether it is good or bad. GFDL, Geophysical Fluid Dynamics Laboratory, was founded in about 1955 by Joe Smagorinsky as part of the US Weather Bureau, supported by Jules Charney and John von Neumann, who were major figures at that time. It actually only became named GFDL in 1963, then it moved to Princeton 1968, continues to be managed by NOAA, and in particular the OAR branch of NOAA. Smagorinsky was something of a visionary. He saw that numerical weather forecasts, which were coming online then, could actually be extended to climate. He hired Suki Minabe, who went on to win the Nobel Prize, Kurt Bryan, who founded ocean modeling, and many others. NCAR was founded in 1960 by Walter Orr Roberts in Boulder on the Mesa. It's a FFRDC, formerly a federally funded research and development center, primarily funded by NSF. It has a wider remit than GFDL, not just climate models, but also space weather, research aircraft, instrumentation, technology transfer, and so on. It's tasked with serving the community. It provides tools, and it has wide collaborations with universities. And I should say, if global warming were not occurring, there would still be a need for climate research and climate models. Lots of natural variability which affects our lives, El Nino, seasonal effects. And the labs were not created to study global warming. They were created to understand climate and weather. But as we know, global warming is occurring, and there's even more need, especially given all the press about global warming, that we shouldn't believe it, that global warmings are wrong. There have been various critical reviews of it by branches of the government, and so on and so forth. These just, I think, emphasize the need for objective scientific research. So what is happening? On the left-hand plot, you see the reconstructed temperature from various, both from direct measurements and from proxies like treeving data and so on. On the right-hand plot, that's blown up from 1850 to 2020. The sort of light brown line is the observed line, which shows what the models have predicted in comparison to the observations. The model variation is this light brown area. The actual observed temperature is this darker black line. And we see it's increased rapidly especially since 1950. If we didn't have anthropogenic carbon dioxide, if we weren't putting greenhouse gases into the atmosphere, we wouldn't have expected the temperature to have increased anywhere nearly as much as that. And I should emphasize that, of course, temperature has changed in the past. It's been much warmer than it is now. So it's not necessarily just the change which is of concern, it's the rate of change, the fact that it's increased so rapidly over the past 100 years, and that is unprecedented. There are many uncertainties in our models. So models which, I may emphasize, have been created by the national labs. They're not perfect. There are two main uncertainties. It's very hard to predict clouds, and it's also rather hard to predict what exactly is forcing the atmosphere, what exactly the greenhouse gases are, and in particular, aerosol forcing, which is in a sense pollution, which is put out by industries, which actually is a slight cooling effect. We really don't have an accurate idea of what the level of aerosols were. So we're making educated guesses at that, and depending on what we think were the levels of aerosols in the past, our global warming estimates will be different. But I should also emphasize it's not the absolute warming that is the most important thing. A degree or two of warming in itself doesn't seem so bad. The most important thing is how the atmosphere and the weather responds to that warming. And many aspects of that are consistent across models. Let me talk a little bit about the physics of the atmosphere and how and why it is warming. This slide is courtesy of Nadir Jeevanjee from GFDL. On the left-hand side, you see the solar radiation coming in. Most of the solar radiation, this yellow arrow, reaches the surface. The surface, in turn, emits infrared radiation, which is absorbed by the atmosphere and re-emitted both downwards and upwards. And it's because of this re-emission downwards, which we call the greenhouse effect, that keeps the planet warmer than it would be without the atmosphere. The other main aspects of what's going on in the atmosphere is convection. We see convection, we see cumulus clouds, we see storms, and so on. That actually also transports heat from the surface to the atmosphere. And the combination of radiation and convection produces the temperature profile in the atmosphere, which we see in this slide. Without convection, we would just have this dashed blue line, which is the radiative equilibrium line. When we add convection, the temperature changes according to this red line, and that's sort of an average temperature profile which we actually see in the atmosphere. And in fact, temperature increases slightly in the stratosphere, the upper atmosphere, because there's ozone in the stratosphere which absorbs radiation. Let's take away let's just look at what the radiative convective equilibrium temperature, as we call it, looks like. Of course, it varies from place to place, but on average, it looks like this. Some interesting things happen when we add carbon dioxide. In particular, let's go back and forth between these two slides. That's what it, as it were, is now. That if we add carbon dioxide, the greenhouse effect, the tropopause actually rises slightly and the stratosphere actually cools. And this was a prediction made by people at GFDL, some 50 or more years ago, that the stratosphere would actually cool. People didn't really take notice of it at the time, but here's a plot from a paper by Manabe and Weatherald, and as you go from here to here to here on the right-hand plot, you see the stratosphere cooling even as the lower atmosphere and the surface is warming. And gosh, we actually now see this in the atmosphere. If we look at the trends over the past few decades, we actually see that there's been warming in the lower atmosphere. This is the global warming we're talking about, but we see cooling in the stratosphere. Another effect, which is predicted by the models, is that tropopause height increases. The tropopause is the boundary between the lower atmosphere, the troposphere, and the stratosphere. Turns out that to a pretty good approximation, the temperature of the tropopause stays constant even with global warming. And I won't go into the technical reasons why that is the case, but that's fairly well understood. The temperature of the tropopause will actually stay constant. But if the temperature of the tropopause stays constant, temperature must go from this blue line here on the right to the red line here, and the height of the tropopause increases. Turns out it does that by about 300 meters per degree of warming. Airplanes like to fly above the tropopause because it's quieter. So another societal impact, if you will, is that we do expect planes to have to fly a little bit higher in future. And that is, again, let me not go into too many details, but recent observations, a paper by Latstatler, which appeared last year, you can see it on the right-hand side, have shown that the LRT, which stands for lapse rate tropopause, just the tropopause height, has actually increased, especially at high latitudes, by about 100 meters per decade, which is a noticeable increase. Again, this was a prediction at the national labs. Perhaps of more immediate concern is that as global warming continues, we expect the high latitudes to warm much more than the low latitudes. Partly that is because ice will melt and it will reflect back less solar radiation. But there are other reasons also, which were again predicted by the modelers many years ago without observational evidence at the time, but they are now being confirmed, and as a consequence, sea ice is melting. Modern models, you can see the darker red here at high latitudes, tells us that the warming at high latitudes is much warmer than the warming at cool latitudes, and we're already seeing that. High latitudes, the northern Canada, northern Scandinavia, northern Russia are already warming much more than other places on Earth. Here again are the observations. The change in temperature from 1981 to 2020. The dark red here indicates polar amplification. And that was being particularly analyzed by papers coming from NCAR and elsewhere. One very important consequence of polar amplification is sea ice loss. And there have been model predictions of that. And if you look at the right-hand side, you can see the sea ice extent from 1980 to 2010 up to the present day. And there was considerable sea ice loss from 1980 to 2010. But in fact, over the last 15 years or so, we haven't really seen much sea ice loss. This has perhaps suggested to some people that, oh, global warming is no longer happening. But in fact, in a paper coming from National Center for Atmospheric Research in 2011, it was predicted that, in fact, internal variability of the sea ice extent can actually be the dominant effect on timescales which are less than about 20 years. What that means that even as we have global warming, the natural variability in the climate system can actually lead to pauses in sea ice loss across decades, even as greenhouse gas emissions continue to rise. On multi-decadal timescales, i.e. 50 to 100 years, the anthropogenic warming which we see is likely to will become a dominant factor. But it's interesting that the prediction that we could have large-scale internal variability on a decadal timescale has indeed now been verified by observations. A recent paper by England in 2025 again shows that the sea ice extent is actually, or sea ice is no longer diminishing. But if I were to put money on it, I would almost certainly expect sea ice to start diminishing again. And we've seen that with global warming. There have been decadal periods when we haven't really had any global warming. These things, of course, sea ice loss has obvious societal relevance. It's of obvious relevance to North Europe, Canada, Greenland, Russia. And again, whether that high latitude warming is good or bad, it's not my job as a scientist to say. I'll pass that torch onto people, onto economists and people who study societies. Of course, it does potentially help trade routes across the Arctic Ocean because the so-called Northwest Passage opens. There are obvious security implications, as we've seen now in the news over the past year or so, with much greater impact in Greenland. And I think it's fair to say that even if we were to stop emitting carbon dioxide, which is the main greenhouse gas, CO2 levels would subside only very slowly. Temperature would not decrease for a very long time. Another topic which has entered the news a lot, you just need to open the New York Times, or the Guardian is particularly concerned about this, is the so-called Atlantic meridional overturning circulation. Let me just focus on the right-hand, the bottom right-hand plot here. But if you actually look at the ocean circulation, we now understand, both as a combination of observations and modeling effects at GFDL and NCAR and other places, that there's a very large overturning circulation in the ocean, which goes from pole to pole in the Atlantic, called the AMOC, the Atlantic Meridional Overturning Circulation. Interestingly enough, the AMOC transports heat northwards, and it warms high latitudes, especially in the northern hemisphere. And this is one of the uncertainties of our predictions of the future, that it's predicted to weaken over the coming decades, but the degree of weakening is known only rather poorly, and the observations so far are inconclusive. And the AMOC, the reason it might or is likely to weaken is because of this polar amplification effect that we're losing sea ice here. So it's not nearly as cold here, so it doesn't, the ocean doesn't, the waters don't descend here, and potentially the whole circulation collapses. And this is again, it's a combination of looking at the observations and using models. And I was rather surprised to see that some of the ocean, that only last week in the newspapers, it was reported that some of the observations of high latitudes of the oceans will actually be discontinued by the government. Needless to say, if the AMOC were to collapse, it could have a very large impact on our climate, and that's one of the uncertainties of global warming. I think I'll skip that slide. So why, coming back to a slightly more general point, why do we have labs? Why not, for example, have universities or smaller research groups? Why do we have labs for studying the environment? And the reason for that is that labs are experts in long-term problems that require significant resources, that require steady funding over many years. If you're in a university, you apply for funding. If you write a good proposal, you'll get funding for a few years, and you'll do a problem. You'll investigate basic science problems. But some of these very long-term problems, like developing the models, take a decade or more, and they really do require a steady stream of funding over many years. GCMs, I make the point here, require a decade or more of development, millions of lines of code. They require testing, verification, and importantly, comparison with observations. They're believable when they generally agree with each other, and the disagreements are understood. We call that robustness. And sound scientific principles can transparently be seen in their methodology and results. So they have to be based on basic science. The same models, essentially the same models, are used for both weather and climate. So these models are linked and are becoming more so. The NOAA National Weather Service model that it uses for predicting weather now uses the basic dynamical core, the dynamical sort of the heart of the model, which was actually developed at GFDL initially for climate purposes. It's now used for weather. Of course, then why, you might ask, why do we have universities why not put all our resources in the national labs? And it's because the labs are, in a sense, problem-oriented. Basic science, blue sky science, if you will, is often best done at universities, giving some more free range to the imagination. And also, we train the next generation. The benefits to society, I think, of labs are so obvious that we sometimes forget to mention them. So let me actually mention a few, even if I think this is rather obvious. Global warming and its causes are now unequivocally established. We understand the greenhouse effect. We understand why the planet is warming, why it has warmed over the past century or so, and the fact that it's warmed about over 1 degree Celsius, over 2 degrees Fahrenheit, is now well understood, and it's an anthropogenic or human-caused effect. Anybody who denies that should be called out, because they're either being disingenuous or ignorant or plain dishonest. The consequences of that global warming are less well understood, and this is really a job for the national labs, building on the science which is done in the universities. The adaptation costs of global warming can be measured in trillions of dollars. That goes back to a Stern report about almost 20 years ago. It's perhaps time for another such report. It will be expensive to adapt to it. And again, I'm not making a value judgment here. We may be adapting to a better climate, but we need to know. It's a matter of we need to know the effects. We need to know how much it costs. Some of the things which will affect us, we know that ice is going to melt. The Arctic Ocean is likely going to free up over the next few decades. If global warming continues, shipping routes will change. Rainfall patterns will change. Agricultural regions will, as a consequence, change. Temperature increases, that's one of the things that we do know with absolute certainty. Tourist industries will have to adapt. The sea level will rise maybe half a meter this century. Potentially flooding of cities. And the Hadley cell, which I didn't talk about in this talk, is likely to expand. This means that the locations of the deserts will also likely change. Populations will be displaced. All of these things, or many of these things, we don't know with absolute certainty. And it is the climate labs, NCAR, GFDL, but also the DOE labs and the NASA labs. And they are the best place to understand these effects and to predict these effects. In conjunction with the basic science which is done with the universities. And I might also, just for my very last point, mention something which I'm not an expert in at all, but I'm now living in San Francisco and I often take driverless taxis. Driverless taxis see using a LiDAR, which is similar to a radar, except it uses a different wavelength of light. LiDAR was greatly developed at NCAR for looking at clouds. The technology was further developed and then passed over to industry. And now we see it everywhere with Waymos and Zooxes and other such driverless vehicles. And without NCAR's early development, we might not be seeing those driverless taxis today. So I think that is my last slide. Yes, indeed. And so I'm going to stop there. And I hope I've convinced you that whether you think global warming is a good thing or not a good thing, we need to know about it. And the national labs, in conjunction with the universities, are the places where we can find out what is going to happen. So thank you all for listening.
Yes, thank you so much for a great talk. Agreed, national labs are absolutely amazing. It's my dream to work at one day. So it's so important that we're talking about this now, raising awareness about needing to keep funding these wonderful organizations. But now we have a few questions for you from the chat. Jay Lee asks, how confident or uncertain are we in the effects of AMOC slowdown on the atmospheric circulation? What might be promising approaches to reduce these uncertainties?
That's a great question, and it's one that I'm actually interested in myself and have done research on. There are two uncertainties. First one is, although we are expecting the AMOC to slow down, we really don't know how much it is slowing down or how much it will slow down. In fact, some of the direct observations that we can make of AMOC show very little slowdown. So that's one uncertainty. The second uncertainty is what will the effect be on the atmospheric circulation? If AMOC does slow down, there'll be less heat transport to high latitudes. So you might expect high latitudes to get cooler. In fact, the atmosphere tends to compensate for that by transporting more heat itself. It's called the Bjerknes compensation effect. But by in order to transport more heat, the atmosphere has to be more energetic. So even if there were no temperature change, because of this compensation, we might have a stormier atmosphere at high latitudes. That your questioner has highlighted one of the key uncertainties that we do not know. What are the promising approaches to reduce these uncertainties? We have to have believable models in conjunction with observations. So we do need observations of the ocean to tell us whether the AMOC is slowing down and by how much. And then we need good models, believable models of the atmosphere based on sound scientific principles to understand what those effects will be, those uncertainties will be. So it's a matter of observations from things like Argo floats and moored observing arrays in conjunction with models which are based on sound science. And I don't have a magic way, a particular thing to do there, except doing good research.
Absolutely. Going off of you were talking about observations there at the end of your answer to that question. We had an earlier question from Ellie B, if I can find it. But she was asking how buoyancy gain or loss can be measured.
Well, first of all, how buoyancy gain or loss measured. There are two. Talking about observations, we can actually measure the density of the ocean. That is one of the things we can measure, or by and large, we measure it by measuring the temperature of the ocean, and we measure the salt content of the ocean. And if we know the temperature and the salinity, we know how heavy the ocean is. So and the density of the ocean is a measure of the buoyancy. Now, in terms of the actual gain or loss, that's also to do with the fluxes between the atmosphere and the ocean. So if we know what the energy budget of the ocean surface is, and in particular, if we know what the things like precipitation are doing, then we can actually calculate what the buoyancy loss or gain would be over a particular region of ocean. For example, precipitation brings fresh water to the ocean. Fresh water is lighter than salt water, so precipitation has an effect of buoyancy gain, in fact, if you will. So that's how we do it. It's a combination of things, both looking at the surface fluxes and actually measuring the density of the ocean itself.
Wonderful. Thank you for answering that question. I think we'll do about two more. Tassie has a clarification question. Jeff, I thought the northern sinking arm of the AMOC was due to cold, stormy weather, for example, in the Labrador Sea area, rather than sea ice.
Yes, it is.
Okay.
Good. But what will happen is if the sea ice melts, then we're putting fresh water into the ocean. And so if we're putting fresh water into the ocean, fresh water is less dense than the salty water which is there. So if we were to melt all the sea ice, we would potentially be gaining buoyancy, going back to the previous question. And so we would not have such a strong sinking arm. So you're correct. But if, so it's not due to the sea ice, but if the sea ice were to go away, we'd have less sinking. Or that is what we believe.
Yes. Awesome. Thank you for explaining and going through that process. I think we have time for one more question, kind of a fun one. Tree asks, what advice do you have to anyone who wants to write a textbook someday?
Well, talk to somebody who might talk you out of it. but I think I wrote a textbook. It was actually quite a relaxing experience for me because I didn't have anybody bothering me when I wrote it. So I think don't try and write it too early. Make sure, get your career going first. So you're somewhat established because most textbooks don't actually succeed, and that won't do you any good. So wait a little bit. Make sure you have something to say, and also when I wrote mine, it was in conjunction with teaching. So the textbooks I wrote were actually derived from teaching classes, mainly at Princeton. So without getting the student feedback, you're kind of sunk.
Yeah, absolutely. Well, awesome. If everyone in the chat could thank Jeff again. Thank you so much for giving a great talk and supporting the live stream and taking the time out of your day to do that. We all really appreciate that.
Sure.
Well,
thank you for having me.
Yes, awesome. All right, so next we're gonna change over into the 31st hour of the live stream now. Woohoo, sound off 31s in the chat. We're also gonna switch hosts now. My 2-hour period's done. We're also done with the keynote section for this evening. So we're gonna go back to those 20-minute segments with some talks. So now I want to welcome Michael, who's gonna be our next host. If you wanna introduce yourself.
Hi, everybody. Thanks for great send-off, McKenzie. I'm looking forward to your talk in just a little bit, in fact.
Yes, I will be right back.
Thanks, everyone, for being here. I am Michael Zeppetello. I'm a research scientist. Are you, McKenzie, are you talking? I can't hear anyone else speaking.
Can you hear me right now?
No, I can't hear you.
Okay.
Everything just cut out when Jeff left.
Vamp,
and I'll leave and come back.
Perfect. Yes, we've been having this issue when some people leave and things like that. So welcome everyone to the 31st hour of the live stream. I'm just going to remind everyone why we are all here. Some of you have been here from the very beginning, or if you're just now joining, welcome. But I'm McKenzie. I'm a PhD candidate, and I have just been hosting, and I'm going to pass off to Michael. Michael, can you hear me now?
I can now.
Okay, perfect.
This is our first time streaming. We've never done this before. So
there has to be issues, technical issues. Otherwise, it wouldn't be a live stream.
Absolutely. Thank you so much for hosting. I'm again looking forward to your talk in just a little bit.
Perfect. I'll see you
hello,
shortly.
everyone. I am Michael Zeppetello. I'm a research scientist at Yale. I'm delighted to be hosting hours 31 and 32 of the Weather and Climate live stream of 2026. We have 19 and then 18 hours left. I'm so excited that all of you are here. I'm so excited to be hosting here at 10 p.m. on the East Coast. And we have an excellent slate of talks lined up after a phenomenal talk by Professor Vargas. Always great to listen to him. But we have some excellent talks lined up after this. However, we're here for a purpose. We're here for a reason. Over the last 80 years or so, the United States has led the way in helping all of us to understand the atmosphere that we live in by putting weather stations across our great nation, launching balloon satellites, sending actual people into hurricanes to take measurements. We've done a lot. We've advanced a lot. We've learned a lot. We've helped the economy. We've saved people's lives. All of that has been made possible thanks to you, all of you watching at home right now, the U.S. taxpayer. But we are here for a purpose, and we need your help. Right now, I want you to go down, look at the bottom of the screen, wclivestream.com/act. Go there right now if you can. There's lots of information and scripts on how to contact your congresspeople, both your senators and your representative, and tell them how important it is to fund weather and climate science and science more broadly. Over the last couple of years, we've seen attacks on science by slashing budgets. And what we need is not just a flat budget. We need increases in our science funding to keep up with the inflation that we've been seeing recently. And you can help do that. Tell your science person we need to push back against the massive cuts in proposals that we've seen for science across NSF, NOAA, NASA, and elsewhere, all across the scientific agencies of the US. By funding science, we help the economy. Fund science, it's a jobs program. It's an economic development program. It's a national security program. It behooves all of us to fund science, and with your help, we can do what we did last year and push back against these budget cuts. All right, enough with the serious stuff. Let's get back to the fun science now. We have an excellent slate of candidates. I'm so excited to listen to people. Our first speaker this evening is Shane Russett. He's a climate science PhD student, and I'm very intrigued by his title of Ocean and Atmospheres 11. I certainly hope there's screenshots from the movie in here, and I'm really excited to hear about a heist into the past. Thanks for being here, Shane. Take it away.
Thanks so much for that intro, Michael. That was amazing, and you will not be disappointed. All right. I hope everyone can hear me okay. I'm going to get right into it. My presentation is Ocean and Atmospheres 11, a heist into the past. All right, so before I begin, a little bit about me. I grew up in San Luis. Uh-oh. Can you hear me? Oh, just Michael can't hear me. Okay, great. Not great, but better than nobody. All right, well, I grew up in San Luis Obispo, California, and it's pictured here. It looks very green, but it often was not like that. Throughout most of my life, I lived in an area that was experiencing quite a bit of drought, which is something that I'll get into later. And like a lot of people that work in the earth sciences, I absolutely love being outside. It's one of the reasons why working in this field is so rewarding. I did my undergrad at UC Berkeley, where after a little bit of hemming and hawing, I decided to become an atmospheric science major. And here I am pictured in a hole that I dug, setting up some instruments for my senior thesis in soil biogeochemistry. And now I am getting my PhD in earth science at Columbia University, where I'm researching rain and drought in the past 1,000 years. So you may be saying, Shane, 1,000 years is a long time. How are we able to know about rain and drought 1,000 years ago? How are we able to know about other climate variables back into the past? So I'm going to illustrate this using CO2. So how do we know CO2 concentrations before we started instrumental measurements? On this plot here, we have year on the x-axis, so from 1760 to 2020. And we have CO2 concentration in parts per million on the y-axis. And the squiggly line on the far right are instrumental measurements that were taken at Mauna Loa Observatory. But humans weren't physically recording CO2 in the atmosphere before around 1958. So how do we know what CO2 was like before people were measuring it? The answer is from paleoclimate archives, such as ice cores. So what is a climate archive? I just mentioned ice cores on the previous slide. And a climate archive is essentially, it can be anything. You know, I want you to think more broadly than maybe you would think at first glance. Often they're things that sort of accumulate over time and that occur in the natural world and that we're able to use to understand what climate looked like in the past. So this is a picture of an ice core. It's a cylindrical core of ice that is taken from usually either Greenland or Antarctica. So researchers will drill down and take out a cylinder of this ice. And what's really cool about it is that over time, as snow falls, little pockets of gas get trapped in these ice cores. And because the ice, as you go from snow to ice, it sort of gets denser and denser as you go down, little pockets of the Earth's atmosphere get trapped as little gas pockets in this ice core. And so we're able to use it to understand what Earth's atmosphere looked like in the past. And also the actual, precipitate, the snow itself also records important information about past climate. Another climate archive that we often use are tree rings. So trees grow and they record annual rings, and the width of those rings, as well as the density of the cell walls that are within them, are dependent on things like temperature and moisture. So we can take a core of a tree and learn something about what climate was like in the past using tree rings. Another climate archive are corals. Again, corals are another naturally occurring thing that accumulate growth over time, and we're able to take a core of corals to understand what the ocean looked like as around them as the corals were growing. Okay, now we're going to get a little bit more creative. This is an artist's rendering of a titanoboa, which is the largest recorded snake, the largest snake fossil that we're aware of. And it lived around 60 million years ago. And the reason why this snake is a climate archive is because snake growth is indeterminate. Snake growth is not regulated by anything about their physiology. Snakes can actually get as big as the temperature will allow them to, because they're reptiles. So what some scientists did is compare the size of the titanoboa to the modern anaconda to try to understand what temperatures were like 60 million years ago when this animal was alive. Okay, this is one of my favorites. These little friends are called hyraxes, and they live in sub-Saharan Africa. And hyraxes live in groups, and they use communal bathrooms. And these communal bathrooms often exist for thousands of years. Hyraxes keep coming back to the same area to do their business. And because their excrement contains things like pollen, and it sort of builds up like a sedimentary rock, like records layers in these communal bathrooms, scientists are actually able to use this sort of fossilized material to understand what climate was like in the past where these hyraxes are living. And lastly, if you think about it, your clothes are kind of like a climate archive. Like if you were to let me go into your room, go into your laundry basket, and look through all of the clothes in there, you sort of build up a layer of clothes over time. And so I could sort of go back into the past, going deeper into your laundry basket. And if clothes, say, have a sweat stain on them, then I could infer something about the temperature on the day in which you wore that clothing item. Okay, so why is paleoclimate research important? First, it extends climate records past the instrumental era. I touched on this on my ice core slide. It allows us to understand the sensitivity of climate to changes in the Earth system. It helps us understand natural variability. The Earth has gone through things like ice ages. So understanding these things are, very important, and we can use paleoclimate to do that. And overall, the past is really essential context to understand both the present and the future. Okay, so now we're finally getting to the title of the talk. My research is kind of like a heist movie. I don't know if you all have seen Ocean's 11. They sort of assemble a team of people to go and take some money from a vault. And this is kind of like what I'm doing. So my team that I assemble are all of my climate archives that I work with. Here I just have pictured a few that we've talked about already. And the work that a lot of people are doing are using these climate archives to create climate field reconstructions, or gridded, sometimes global, sometimes regional reconstructions of what climate looked like in the past. So sometimes people will take just tree rings to create a gridded reconstruction. Sometimes people will take sort of every proxy they can get their hands on to create one of these gridded reconstructions. And sometimes they'll even combine proxies and a climate model to create a gridded reconstruction to look back into Earth's past, which is an incredibly useful tool. So a lot of my work is working with tools like this. Okay, so now we're going to talk about applying one of these climate field reconstructions. This is from a paper, Williams et al. 2022. And we're going to start with the figure on the left, panel A. So on the x-axis here, we have year from 800 to the present. And on the y-axis, we have soil moisture. And this line is showing a 22-year running mean of soil moisture. And what this paper found is that, and sorry, I forgot to mention that this is using a collection of over 1,500 tree ring records in the Southwest USA. So, you know, I showed my the picture of where I grew up earlier. So I grew up, you know, right in this region. This paper found that in the Southwest USA, 2000 to 2021 is the driest 22-year period since at least 800 CE. And I was actually born in the year 2000. So I experienced this 22-year period, the first 22 years of my life. You can see on panel A, that's the red line at the bottom there. And in panel B, what they did is they, you know, this is the gridded climate field reconstruction that they got from those tree rings. They're comparing observed drought to drought when they removed the trend of anthropogenic climate change. So they calculated this trend using models, a multi-model mean from the Climate Model Intercomparison Project. And they found that these anthropogenic climate change trends account for 42% of this 22-year drought anomaly. So these climate field reconstructions are really powerful. They can help us understand really important things that are happening in our lives and place them into the context of history. So I actually haven't showed any of my own research results, but I'm going to give you just a taste. A lot of what I do is applying these climate field reconstructions to areas where not a lot of proxy archives exist. So this is a plot from Pages 2K, which is a collection of archives that is often used as the basis for these climate field reconstructions. You can see trees here are these little green triangles. And so you can see exactly where all the tree ring proxy archives are. But there's some areas in the map where there aren't that many archives. And so I focus on one of these areas, which is this black box in Eastern Africa, and try to understand, you know, how we can understand what past climate looks like there, even with, you know, this sort of lack of traditional proxy records. Okay, I'm going to quickly conclude talking about funding cuts and my career. So often I get asked by people, doesn't your work depress you? And the answer is, I actually used to feel much more existential unease about climate change before I started my PhD than I do now. I actually feel better now than I did before. And obviously that's not to detract from the problem of anthropogenic climate change, which will require immense collaboration to overcome. But I do feel less nervous because I met so many of the amazing and talented people working in climate research, which is demonstrated by this incredible 50-hour live stream. And I realized that, you know, I'm not the only one worrying about this. There's so many amazing, smart people that have devoted their careers to solving these problems. However, the public funding that allows for this area of research to flourish is now being threatened, which is really bad. You know, it's threatening all of these careers and future careers for people that think about these issues all the time. So I would really urge you to reach out to your representatives. Go to wclivestream.com/act and call your representatives, write your representatives, tell them to fully fund NOAA, increase NOAA's funding, increase NASA's funding on Earth science research. And that's it. Thank you so much.
Thank you so much, Shane. That was excellent talk. I like your boldness in putting your photo over Clooney's in the poster. Well done. Very good. We have some fantastic questions lined up. And again, thanks to our director, Phoebe, for pitching these to me. It makes it look like I'm picking out great questions. It's her behind the scenes doing it, so thank you. We have quite a few, and I think we have time. Maybe we'll get through all of them. We'll see. But I think I'm just going to go down the list that I saw in order. So the first one is from Cosmo Conjurer. Shane, how did you get into this specific research, and were there any inspirations from people or events in your life? Maybe someone you looked up to?
Yeah, absolutely. I mean, there's so many inspirational people in my life. You know, I picked atmospheric science in undergrad after I applied as an undeclared physical science major, and then I did sort of a ranked choice of the majors that were available to me based on things like, you know, where do I think I would be the happiest? where do I think I would feel the most fulfilled? And atmospheric science was the major that won out. So that was that. I worked in Dr. Wendy Silver's lab in undergrad, who is amazing. I also minored in history in undergrad, and I feel like I have Dr. Carlos Narenia to thank for that, who is an amazing professor who I took his lecture as an elective. So climate and history sort of came together in paleoclimate. And now I have an amazing advisor, Dr. Jason Smurden, who's just been incredible in helping me along this wild ride.
Great, fantastic. It's great to have good mentors in your life. All right, next up we have a question from Kelsey Ward. Are there different kinds of paleoclimate sources used for different things? Like, are ice cores preferred for certain things or tree rings for others?
Yeah, absolutely. All of these different paleoclimate archives have different temporal resolutions. They go back, to different lengths of time. Ice cores go back. We have existing ice core records that go back 800,000 years, but they're in the process of harvesting more ice cores that go back even further than that. Tree rings, trees don't live for that long. They do not go back that far. So a lot of these proxy records have different time resolutions, but also they record different things depending on where they are. A tree that grows in the Arctic is going to be more temperature sensitive and will record temperature much better than a tree that lives in somewhere that's really dry, which will record rain and drought better.
Yeah, interesting. Yeah, so it really depends on where the source is, on what it might be best used for. Next, we have a question from Sydney Lindquist. Is biological data better than inorganic data, for example, from rock layers, when it comes to understanding paleoclimate? Question.
Yeah, like I said, I am thinking about the past 1,000 years. So, if I'm thinking about, I actually don't really think about paleoclimate using rocks very much. So, again, it all depends on how far back into the past you're thinking. If you're thinking millions of years ago, you're probably thinking a lot more about rocks than the way that I'm thinking. So I probably leaned more towards biology when I was listing different archives.
Cool. Next up, we have from Homendorf. Do we know what caused some of those wild swings in soil moisture historically?
Yeah, there's a lot of theories as to why these different swings happened. Obviously, El Niños and La Niña are sort of a chaotic system, the ENSO cycle in climate that will cause big swings in rain and drought across the world. I don't want to talk specifically about any one swing in soil moisture, but I think that is often something that we discuss when it comes to changes in rain and drought in the past.
We have a really fun question here now that I'd love to hear what you have to say about it. Charlotte Cockburn asks, how well do you think you would do in an actual heist situation?
That's a great question. And, something that I've thought a lot about. Again, it really comes down to my team. A heist team is only as strong as its weakest link. I think I can imagine myself playing a number of roles, getaway driver, man in the chair. It seems like they always sort of just like hack into something fairly easily. I don't know if I could do that actually. Write me down as the getaway driver. I think I would do great.
Oh, come on. You can do better than that. Let's see what else we have. We have a few minutes left actually. So let me scroll through here and spot a couple of others. We actually got through the list pretty quickly. Great answers, by the way. I saw a couple scroll by, other ones. Phoebe, if you see any others, throw them set them aside. There's one, I thought I saw one. Oh, we answered that one. Are there regions that are particularly sparse in data with creative ways to gain the data, or do you have some ideas on how to fill in gaps amongst in data sparse regions, for example?
Yeah, I think it comes down to just coming up with creative ways to reproduce past climate, like those Hyrax middens that I was talking about. Those are a source that exists in sub-Saharan Africa where there's not a lot of other paleoclimate records. And I don't want to cut myself off, but I think we might have to get the next person back in here.
Oh, that's right. Yeah, I was trying to give you the full 20 minutes, but we should really.
Yeah, all good. Thank you so much,
Yeah,
chat. Thank you, Michael. This was so much fun. I really appreciate it.
Of course. Thank you so much for being here. Thank you so much for sharing your science with us. All right. Moving on. Thank you, Phoebe, for keeping me on track. Next up, we have another terrific speaker lined up. Carolyn Zhuang, who's a postdoctoral research fellow and climate scientist. Hello, hello. And hello. I suspect we're going to hear about fire weather and how we measure them from satellites. And so I'm really excited to hear about that. Please take it away, Carolyn.
Awesome. Well, thank you so much for having me. I'm really glad to be on the Weather and Climate live stream. And special thanks to Michael for being the host. Special thanks to Phoebe behind the scenes. Welcome to, hour 31. And I'm really happy to present about climate, the ocean, the effects on wildfires, what satellites can do about it, because my research is much funded by NASA, which has the satellites, and funded by NSF, which supports my research, and thanks to the Ziegler Family Foundation for some funding as well. So I'd like to set the stage here. So I started out on this fire weather journey, fire climate science journey with in 2019 with the start of my PhD. And so in 2019, I want to just direct your attention to this time series from 1984 to about 2019. We can see that the fire season has been steadily increasing. The forest burned area has been increasing over time. And fire in the Western US has been breaking modern records. And I was actually at NASA Goddard Space Flight Center as an intern researching landslides when I learned about this record-breaking fire years of 2017 and 2018. And I was working as a project coordinator. I was making a landslide citizen science project. And actually this Thomas fire, not only did it cause a lot of destruction from the fire itself, but also there was a debris flow aftermath that led to more than 20 deaths. And so this really got me thinking about like these effects, these cascading hazards of fires, of debris flows, landslides, and climate, and how climate change is affecting all these different kinds of hazards that are affecting humans and human health. And you can see even another effect of human health is the smoke that you can actually see from space, which can affect air quality. So I thought that 2017, 2018 are extremely bad fire years, but then as I continued in my PhD, what I actually learned was fires got even worse. And so the years 2020 and 2021 ended up even more record-breaking. And this increasing in fire between 1984 and 2023 amounts to a 1,000% increase in annual forest area burned. And so not only did fires affect people living directly in California to Colorado, but fires began affecting everyone. And so I was doing my PhD at Columbia University. That's where I actually got to meet Shane in the last talk. So we got to work together for a little bit and cross paths. And together we, and with all the other PhD students in the program, we've been breathing in all this smoke pollution that turned the skies orange for a little bit. And these smoke came from both the Western US, but also from Canadian wildfires that happened in like 2021. So I've been feeling the effects of fires even though I'm studying the Western US. So that's been a really interesting experience, a very motivating experience. And then continuing on, what I've been learning through my research is that it's really these Western United States forests that are impacted the most by these record-breaking fires. And if you can follow my mouse here, what I see is that the darkest colors are the percent change in burned area, and the darkest colors are the ones that are about like 4,000% to 5,000% increases since 1984 in burned area. And that's happening a lot in the Sierra Nevada, that's happening in the Pacific Cascades, that's happening in the Rocky Mountains in Colorado. And it's these areas that I've been like focusing on to really understand like how is climate driving these huge increases in area burned, and what are the effects? And it's interesting because I talk about fire in this very negative context, but what I want to remind you is that in a lot of these habitats in the Western US, fire is good fire. So fire is needed, and fire is a natural part of the landscape. And some forests, especially in the southwestern US, rely on fires to propagate their seeds, for seed dispersal. They have developed properties such as being able to like resprout from the base of their trunks in order to really work together in a very like fire frequent environment. And one of these environments that I visited actually out in Big Basin Redwood State Park, and this is like kind of off of the Bay Area, nearish to San Francisco. This area tends to get pretty frequent fires, and these coastal redwoods, these extremely tall trees, are used to this kinds of fire. But when we get like huge fire years like 2020, we see a lot of destruction, and if the fire is too severe, rather than like happily working together with the environment, we might see entire forests being razed to the ground. And just to show you like the severity of this particular fire, along this trunk here is like the actual fire scar. So you can see that the burn scar got pretty high up on the tree, and you can compare it to me. I'm like 5'3", so if that puts in the context, these are extremely severe fires, and we might expect even more severe fires in the future. And so talking about fires and how fire scientists look at fires, there's a natural recipe for fire. And in order for a fire to start and for a fire to spread, we need ignitions, we need fuel, and we need climate. And these combine together, and without one or more of these drivers, fire can't occur. And in the last century, non-Indigenous populations have influenced all of these variables. And with ignitions, expansion into the wildland-urban interface has increased the number of ignitions and increased the seasonality of ignitions. So rather than just lightning being the cause, you have like fires being ignited from electricity poles, from different kinds of gender reveal parties, other human kinds of like campfires. And then we also have fire and forest management, where the way that we put out fires, how often we put out fires, affects how much fuel is built up into the environment. And then anthropogenic climate change is a main driver of like warming and drying that has made the possibility of a fire igniting and spreading even greater. So these are very important to consider when thinking about what's the future of fire. And then the Western US forest area burn varies with climate within a year. And we can see that precipitation is high in the winter months and goes down in the summer months here. And at the same time, temperature reaches a maximum in the summer months. And the way we can then look at the seasonality of fires, that if we look at the timing of this lowest precipitation and highest temperatures, what we find is that this is the same timing as when the most amount of area burned happens. And then continuing on, I want to introduce an important variable here, which is vapor pressure deficit, which measures that warming and drying. So considering temperature, considering precipitation, and vapor pressure deficit is then this measurement of aridity that's connected with burned area, because we're trying to develop a way to connect the atmosphere with fuels and fuel dryness. So if we think about the atmosphere like a sponge, then what we have is that as temperature increases, the amount of water that sponge can hold increases. And so saturation vapor pressure describes the amount of water that the sponge can hold. Meanwhile, actual vapor pressure is a measurement of the amount of water vapor the sponge is holding currently. And so therefore, this saturation vapor pressure minus actual vapor pressure becomes the amount of water that the sponge is lacking, or in a way, the amount of water that the atmosphere is lacking. And when as the atmosphere lacks more water, then more water is drawn from the surface, from soils, and through the vegetation, through transpiration. And so the warmer and drier the atmosphere is, the drier the fuel will be as water is drawn from the surface, and therefore this is related to how much fire we might possibly have. And then going forward with that, we can then take our time series of burned area and with our extreme burned area years in 2020 and 2021, and we can like relate this to vapor pressure deficits. So if we look at both time series, and if we color these points by pre-2000 and post-2000, and we scale them onto the same axis forest burned area on the y-axis, and if we take vapor pressure deficit, put that on the x-axis, so every point is a measurement of burned area and vapor pressure deficit, then what we find is that there's this extremely good and strong relationship between vapor pressure deficit on the x-axis and forest burned area on the y-axis, where and 2020 and 2021 fit right along this exponential relationship. So as we get warmer and drier in the western US, what we found is that burned area also increases exponentially. And so if we think about anthropogenic climate change, which is affecting warming and drying in the western US and increasing temperatures in the western US, then scientists have actually related western US burned area to scale with that. And so anthropogenic climate change has these direct and important impacts on burned area. And so that kind of has been motivating a lot of my research to really study all these different relationships between climate and burned area. And so I wanted to share two little papers since I don't have a super amount of time, but I'm really excited to be able to present just like what this NASA-funded research, NSF-funded research has been helping with. Is in 2022, what I found is that like even though we have this strong relationship, at the time in 2022, we didn't really know why this relationship, which is like an atmospheric variable related to a surface variable, why this relationship is working. And by using a database that my PhD advisor and I developed, the Western US Monitoring Trends in Burn Severity Interagency Database, which is a database of 21,000 fires, and it's continuing to grow. Using this huge database of individual fire events, we were able to find that fire size matters a lot more than number of fires. So it's not really about like the number of ignitions and number of fires. When we're thinking about this drying and warming relationship with fire size, it's actually more about how the fires grow themselves. And then what we show in this particular paper is that as fires get bigger, like a compounding bank account, those fires had a greater potential to grow even larger. And so what we ended up finding is that at the individual fire scale, these fires are growing exponentially larger across the landscape as long as fuel exists, which is abundant in forests. And so if you look at the annual scale of all those individual fires together, it's actually like the top largest fires in every year that are the ones overall like creating this huge picture of what is the annual area burned per year. And in terms of like in terms of warming and drying, if anthropogenic climate change is going to keep increasing warming and drying, then what we might find is that the largest fires are going to keep getting larger and larger. And so we really have to think about the dynamics of fires spreading at these huge scales, at these massive fire events, including the LA fires that just happened in 2025 in January. And another small point that I want to make here is that anthropogenic warming is actually working together with natural variability to influence climate across years. So anthropogenic climate change is from CO2 being pumped into the atmosphere, and we see this massive spike in CO2 in parts per million that has then led to these increases in temperature. Well, that is also working together with natural variability of ocean dynamics, for example, such as the El Nino Southern Oscillation, which is varying ocean temperatures every 3 to 7 years. And then there's also longer scale ocean temperatures that vary every like 40 years. And so scientists really have to be able to decompose these different signals from anthropogenic forcing and from natural variability from the ocean to really understand what will the future of temperatures look like, what will the future of precipitations look like, because there's all these different competing factors. And then so another paper I wanted to highlight really, really quickly in one slide is that there are these contributions of the tropical Pacific Ocean to affecting areas of the Southwest US on the coast and in the inland areas. And what my colleague, Dr. Jacobson, has found in this paper that I've also been able to contribute to is that there is this effect of vapor pressure deficit from anthropogenic warming, but also there's this small but important effect of vapor pressure of the tropical Pacific Ocean actually affecting that vapor pressure deficit. And so overall, there's this like trend upwards in vapor pressure deficit. So it's warming and drying is going up, but also tropical Pacific Ocean temperatures are also increasing that on top of anthropogenic climate changes, also increasing this warming and drying. And so therefore we could put all these signals back into our burned area trend in these regions to see that there are all these stacked effects of all these different natural variability and anthropogenic forcing that are causing burned area to go up. And if we think about future climate, then we want to make sure we have all these signals in our coupled atmosphere ocean models, like these huge models that Shane was talking about, that allow us to predict the past and also predict the future. And then finally, I just want to really end with thinking about like NASA's contribution to all this, because taxpayer funding has been able to add all these different satellites. This is just a subset of the different satellites going around the Earth that are measuring fire variables, but also measuring the ocean, measuring land. And NASA assets, both airborne and satellites, contribute to these pre-fire and active fire and post-fire stages. I'm running out of time. I see Michael's back. And so I want to then finally just end thinking about that NASA and these other organizations are looking at fires. They're funding wildfire research. I've been able to contribute to this wildfire research and also be able to benefit from the funding given. And I think that if everyone can call their Congress people, I think that we can continue looking at fires, dealing with these intense fire seasons, and understanding how to manage fires in the future and live with fires. So thank you.
Thank you so much for that really sort of combination inspiring and sort of a little scary talk. I will squeeze in one question for you from the chat, and I'll do host prerogative and pick one. Kelsey Ward asks, so 4,000 to 5,000% is a huge increase, right? How do you convey such enormous numbers to the public so they can visualize how large a difference that is? It's really hard to think about 4,000 to 5,000%. Oh my gosh.
Definitely. Yeah, I think that, these increases in area burned are huge. And one fun strategy that I've been able to really like convey this information is like trying to relate like these thousands of percents to maybe like the size of a state or like the size of a county or, size of Washington, D.C., these kind of things. Like thinking about these like largest fires that have happened individually. Some of these fires have been like 65 times the size of Manhattan, for example. And I think with the figure that I show, just coloring it, sometimes doesn't quite convey it all the time. And so that's why we need the work of both scientists, science communicators, and people in the public to really bring together different ways of being able to show sizes, show scales. So I really appreciate this question. Thank you, Kelsey.
Yeah, excellent answer. Yeah, it's really sort of hard to think about at those sorts of scales. Thank you so much for joining us this evening. I think we're ready to move on. Thank you so much once again. Really informative talk. Thanks for being here. It is time to move on to our next speaker. There is a reason we are here, though. I'd much rather be enjoying a bowl of ice cream myself right now, but we are here because we need your help out in the public to reach out to your Congress people. Go down to wclivestream.com/act and contact your Congress people. Let them know that the proposed cuts to science funding at NSF, at NOAA, at NASA cannot be allowed to stand. We need not just flat budgets, but we need increases in budgets to keep up with inflation. And we need to do all of this because of the economic impact that understanding the weather and climate has for the United States. It really provides a strong benefit to protect life and property, and we cannot risk sacrificing the amazing progress that we've made over almost a century now in learning and studying and understanding and being able to forecast and predict the weather for the United States. All right, I believe we are ready for our next speaker. We have McKenzie Larson, a Ph.D. candidate, just did a fantastic job hosting right before me. She's a Ph.D. candidate at UC Boulder, and I'm really looking forward to her talks about, looks like we're going to learn about windstorms on the Front Range of Colorado.
Yes.
Thank you so much for coming back yet again, and please take it away, McKenzie.
Yes, of course. Happy to give a talk, and thank you as well for hosting. and contributing to the live stream. So hello, everyone. My name's McKenzie Larson. If you haven't met me yet already, well, I've been hosting on the stream. And I'm in my last year of my PhD at the University of Colorado Boulder in the Department of Atmospheric and Oceanic Sciences. And today I'm going to be talking to you about our downslope windstorms. So to kind of orient you where I'm going to be talking about my science today, we're going to be looking at the Colorado Front Range. So here you can see a map of North America focused on the US. It's a terrain map. And Colorado Front Range, I have circled here with this black oval. If we do look at a larger zoomed in version of the whole state of Colorado, you can maybe see my cursor, maybe not, that's okay. But you can see Denver is over in like the northeast part of the map on here. And to the northwest of that is Boulder, which is where we live and my university is, and where the National Center for Atmospheric Research, or NCAR, is located too. And so all along this Front Range, which is part of the longer Rocky Mountain Range, we get some really severe downslope windstorms. And so a downslope windstorm is a really strong, gusty wind that blows down the lee slope of a mountain range. It would look something like this. And it often reaches its peak strength right near the foot of the mountains, or where the flat part where many of us live kind of reaches the part of the mountains that start to really rise in steepness quite quickly. And then the winds will weaken quite rapidly as you move further away. And we care about these windstorms because they endanger lives, they damage property, disrupt travel, and they also exacerbate fire weather. And so here in Boulder, Colorado, folks have been noting these windstorms for a long time. They've been even measured at NCAR going back to the mid-60s. So what you're seeing here is analog observational measurements shown in this little center plot here with all the squiggly lines that were taken at the NCAR Table Mesa Laboratory. So there's an observation site on top of the roof of those buildings. And so it's showing a downslope windstorm observations shown here. And there was a peak gust in one of the overnight wind bands of 137 miles per hour. So these are like hurricane force winds that we can get here along the Front Range. And the figure you're seeing on the right here are showing some damage and peak gust speeds from all of the windstorms in January of 1982. Along the whole Front Range, you can see the different terrain in the contours on here. And it also extends northward into Wyoming as well. So another damage to highlight from this windstorm was that there were 20 airplanes overturned at our local airport. There's a picture of that shown here. Lots of housing damage. There were power lines down by the NOAA building over here back in the 80s. So very, very impactful. More recently, one windstorm that you might have heard of, because it did make national news coverage, was associated with the Marshall Fire, which was on the 30th of December in 2021. So we had a really strong, persistent windstorm lasting for hours on this day. Fire was ignited during it, and it led to a pretty devastating fire in our region. These are some pictures shown here. There were over 1,100 homes destroyed in our local community. 2 deaths, and at NSF NCAR, like I showed you observations on the previous slide, there was a 112 mile per hour gust measured there. So very, very strong winds. And so the way the Marshall Fire kind of happened, to kind of break it down, is before December of that year, so over the summer, we had a really great wet and rainy season. Everything, we were getting nice thunderstorms, lots of rain. So all the vegetation and the plants could grow quite tall. They were really flourishing. And then once we got into the fall, there was this really big kind of regime shift. Things got really dry, really fast. We weren't getting a lot of precipitation, a lot of snow. So when you combine that with some really strong winds that are really persistent for hours, and you just add an ignition source for a fire, you can have what happened with the Marshall Fire. So here's some more photos of those homes, as well as some of the damage as well and the extent of that fire. It's also, this Marshall Fire was included in the US $2021 billion weather and climate disasters as part of the Western wildfires in 2021, which you can see here with the kind of orange circles on the left, combined with fires from California, Oregon, Washington, Colorado, and other states. So it was very impactful, the fires during this time. And one thing I want to point out about this awesome graphic that's really great for scientific communication is that this data set has been part of NOAA, but as of last year, and changes with evolving priorities and funding, this data set is now no longer supported. I believe it's now only goes till 2024, which is unfortunate. This is a really great data set. Really good graphics, helps you understand a lot about the impacts of weather, and it's really good to show others as well. So I just wanted to highlight that there. But now that I've hopefully convinced you that these windstorms can be quite impactful, quite strong, the focus of this talk today is just gonna I'm gonna show you some fun drawings that I've made. I'm not an artist, but I'm just gonna show you how downslope windstorms occur along the Colorado Front Range. So we have two flavors of windstorms here in Colorado. One is called a Chinook or a fen wind, and we're going to start with that one. And that is our warm downslope windstorm. So you can picture on this map here, I have a low pressure system that has a cold front shown in the blue line with the blue triangles on there. Sometimes these winds can occur before a cold front moves through, where we're having winds above the mountain that are coming from the west or coming from the northwest. And it gives us what we call cross barrier flow. So where you have that mountain ridge of the Rocky Mountains and you have some winds coming right at it, they're going to cross over each other. So schematically, what this looks like is you can have cold air trapped on the windward side of the mountain. That's what's shown here on the left. We call that cold air damming. That allows for this warm air above to essentially just skirt over the top and descend down towards the surface. And as it descends towards the surface, it speeds up and also continues to warm. This can also happen through something called orographic precipitation, or you might know more of as like the rain shadow effect. This is where you have air that is forced to rise over a mountain. It doesn't really want to. It needs to precipitate out all of its moisture. And then that leaves you with warm, dry air that descends on the leeward side of the mountain. And so when I was hosting in the early hours of this morning, we were doing some cloud brackets and things. And so when you get this orographic precipitation, you can get these fern wall clouds, which are really cool. It just looks like you see the mountains, and there's this big wall of clouds. It's really pretty when I drive into work, but I know it's going to be a windy day when I see that. So the other type of winds that we have are called bora winds. So now these, as opposed to the Chinooks, are our cold winds. So after that cold front has moved through Colorado, we're really getting predominantly flow or winds from the northwest, bringing down some more of that Arctic air. So instead of having that cold air trapped behind the mountain now, you have this cold layer that extends above the whole layer of the mountain range that you can see here. And it's capped by this warm layer aloft or above. And so what happens at the top of that mountain where you have all this air that's forced to go up there, it enters this little space, is something called Bernoulli's principle. So this cold air is forced up, it's in this little region, and it needs to speed up since it doesn't have as much room to kind of spread around. And then from there, it descends towards the surface as well. Some phenomena associated with these downslope windstorms, I'm going to show you here. The streamlines, like you've seen, are shown in these gray contours. Those are just like how the wind would be moving. During windstorms, you can have what we call mountain waves, and these are atmospheric gravity waves. So if you kind of forced like air to rise up, it would essentially just kind of bobble up and down. And we could actually see this during the Marshall Fire, since the fire was at the surface. It was trapped in that lower boundary, in the planetary boundary layer. And it was trapped within that first kind of mountain wave region. So you can actually see that shown here with the fire and all the smoke. Something else, going back to our cloud discussion that we had earlier this morning, when we have these mountain waves, we can have lenticular clouds, which are my favorite. They look like UFOs. They're like pretty freaky, but you just have these clouds that are trapped in these layers, and they form that fun little UFO shape. And as downslope windstorms progress, it looks a little scary, but it's okay. You can eventually up much higher, get these wave breaking regions where you have the circulation start to kind of flip back over itself. And at the surface, what's interesting is where you have this wind that descends really rapidly at the surface, and it's confined to this really shallow layer at the surface. Once it reaches a region where it can now freely move up higher, that's what's called a hydraulic jump. You might have seen something like that, like in a river, when you just see like a little bit of fast moving stream and then it suddenly starts to get really turbulent. And then that area downstream of that that's really turbulent is called a rotor. And so this is another graphic from the Marshall Fire. So you can see on the right side of this figure, you have these fast winds with the smoke in it that we can use to see as a tracer. They're really stuck down towards the surface. They're moving really fast, and then they get to a region of the atmosphere where now they can freely go up faster, and it causes this turbulent motion. So that is mostly what I wanted to talk about today, just kind of show how these windstorms formed, but also show you some of the cool clouds and phenomena associated with them. Some other work that I've been doing with collaborators at NCAR and the National Weather Service kind of goes back to that plot we saw in the 80s of that 137 mile per hour gust. A lot of people here that have been living in Boulder since the 80s have been talking. So here are people in Boulder. And everyone's kind of been like, why are the winds just not as strong as they used to be back in the 80s? And a lot of people have kind of come to this themselves as well. So that is something that we decided to actually take a look at. We started to look at downslope windstorms measured at NCAR from 1967 when they first placed the anemometer all the way to 2024. And I don't have time to go into it today, but there's this article that you should be able to access. It's a fun title, Earth, Wind, and Fire, Are Boulder's Extreme Downslope Winds Changing? Again, this wouldn't have been possible without collaborators at NCAR, as well as the National Weather Service, as well as other universities. But it reads kind of like an investigative novel type little short story. So even if you're not a scientist, I would definitely encourage you to read it. It's quite entertaining. And then just finally, I want to say that government funding has been absolutely essential for my growth as a scientist, and I would not be where I am today without it. This all started for me in 2020 when I participated in the Ernest F. Hollings undergraduate scholarship program, which helped give me some scholarship to finish my undergraduate studies and then continue with an internship at the National Weather Service in Boulder, which began my passion for downslope windstorms. Once I graduated, I did a summer internship at NCAR, and I'm still working with those collaborators today, still on downslope windstorms. I'm currently, as a graduate student, funded by the Department of Energy Computational Science Graduate Fellowship, which I'm extremely grateful for. I've spent a summer doing some ocean model development at Los Alamos National Lab in New Mexico. And just last summer, I was participating in the La Penta internship at NOAA to work on some of our high resolution model development. So I've absolutely found my passion and have met so many amazing, wonderful people through all of these programs, and I would not be where I am without them today. So with that, I'll leave you with some fun Colorado pictures up there on the top right. Bottom are Kelvin Helmholtz clouds that we saw right outside of our office. And then the right here is a picture of me and my friend Clary, who's in my research group, when we were at trying to advocate for NOAA. So I'm happy to take any questions if anyone has any.
Well, thank you so much, McKenzie. I really love the movies that you were able to put together with your explanations. It really kind of helps visualize what the structures of these winds are in the atmosphere. We have a couple of, I think, really engaging questions that I want to get to. So the first one from Stu Weiss: how are some of these particular wind types forecasted? How well are they forecasted?
Yes. So I think it depends on your model that you're using, your weather model. Currently, the biggest restriction right now is that, so in Boulder, we're hugged right along that Colorado Front Range, and it's this very complex mountain terrain, and my cat is trying to eat things. So we're kind of limited by how well we can represent this topography within the models. But currently a lot of the forecasters here do a great job, and they kind of know more anecdotally what to expect and how some models are biased. So I think they're definitely getting better, and I think like the research that many of us are doing will help with that.
Excellent. I'll try and get to two more, which is, are people thinking about harnessing these winds for electricity generation? This is fish failure sun.
Yes. So I've talked to quite a few people about this before. There's a lot of people, at the National Renewable Energy Lab who've also kind of worked on some of this. And sorry, this is Trixie. She wants to participate. The thing is, when we have some of these windstorms that are, over 100 mile per hour gusts, that's like too fast for the wind turbines to like safely safely turn. So it's also important for us to be able to forecast those to make sure that we don't mess up our electric energy grid as well. So it would be really cool if we could just spin it really fast and do that. But currently, to my knowledge, no.
A super important question has just popped up in the chat. People are demanding to know what the cat's name is.
The cat is Trixie, and she has now just left. Sorry, she was all after one of our directors, Brianna, is letting me use her little camera, and she really wanted the string. So if you heard any clanking around, that was her.
I'll ask one more science question that's really piqued my interest from Sydney Lindquist. Do severe fire seasons in Colorado have a link to tornado seasons in the Midwest?
I don't know how much I can really speak to this because I'm not a fire weather meteorologist per se, I suppose. But a lot of these windstorms are really synoptically, or that's what we call large scale weather system driven. And so when there's Trixie. So if a lot of these things are large scale driven, in the Midwest, that's further downstream. So whatever kind of how that storm evolves will then further impact the Midwest too. And so especially if you have fire season, so things are really dry, that could bring, drier air to the Midwest, which maybe won't be quite as advantageous to form some tornadoes going into some of those large scale systems. Yeah.
All right. Well, thank you so much.
Yes, of course. Sorry about the cat interruptions.
No. The star of the show, I think.
Well, I know.
Honestly.
Star of my life.
Absolutely. Thank you so much. Enjoy your evening. You've had a long day.
Yes. Time for some rest. But thank you again so much for hosting.
Have a good evening. Thank you so much. All right, we are about to move into hour 32 now. We have 18 hours left in the Weather and Climate live stream. Hello, I'm Michael Patello. I'm your host for the next hour still. We are here to help push back against the budget cuts that weather and climate science has been facing across the country. Think about what all you as the American taxpayer gain by having the excellent forecasts that have been developed over the last 80 years. Perhaps just a couple of weeks ago, you were going to go to your kid's baseball game and you saw that maybe it was going to rain and you brought an umbrella and you were the only dry parent there. Ranging to perhaps a couple of years ago, you got a warning that a hurricane was heading your way and you were able to batten down the hatches and cover up your windows. Perhaps you were at the other extreme in Colorado, for example, and there was a blizzard coming and you went out and you got your milk and bread in time, and so you weren't peckish during those few days you were trapped inside. You can thank the Weather and Climate enterprise that's brought to you by all of the research that's been done over the last 80 years in understanding how to forecast, where to get these data from, how to incorporate data into weather models and interpret these things. All the things that we've heard about in the last 32 hours have been made possible by the US taxpayer. But that's at risk right now. And we need you to step up just like you did last year. We need you to do it again. We need you to contact your congressperson right now, reach out to them, let them know that budget cuts for weather and climate science and science in all disciplines in the US cannot be allowed to happen. We need to push back once again. Do not cut science budgets. We need increases to keep up with inflation. Even if we are able to push back against these budget cuts, there's still a lot of chicanery going on in the background as well. There was a recent rule proposed by OMB that basically allows political appointees to ignore peer review and merit in making decisions on what sort of grants are funded. And if you go right now and type into Google OMB science rules, you can see some of the write-ups about how terrible these things might be. And you can go and comment on these OMB rules and push back against this in other ways as well. So it's not just the budgets where we're feeling pressure. And so we need the public, we need all of you watching right now to help us out once again. I'd like to remind everyone that we are in hour 32 of the Weather and Climate live stream. The people that you're listening to right now are just regular US citizens. They're just speaking their mind. They're providing their own opinions. They're not speaking for their employers. They're just concerned, like everyone, that we should be getting the best value of the science that we've already put out there. I believe our next speaker is lined up, and I'm really excited to welcome Maggie Powell, an early career scientist and PhD candidate at Columbia University. We're going to learn about using simple models to help understand sunlight and clouds. I'm really excited. I've seen in the chat that your slides are really good. I'm really looking forward to this. Please take it away.
Awesome. Thanks, Michael. Hi, everyone. My name is Maggie Powell, and I'm a PhD student.
Oh, looks like we're
okay. Yeah, so I'll be talking about science, asking questions, and thinking about clouds. Let's make sure things are advancing. All good. Okay, so I'm a PhD student at Columbia University, and I study Earth and Environmental Engineering. Specifically, my research is about clouds and sunlight. And as part of that research, I use computer models as tools for investigating fundamental questions about the Earth system. But that's the central point of my talk. In a nutshell, that's what scientists do. They ask and try to answer questions about the world. So I thought it would be fun if together we could ask and maybe answer some questions about sun and clouds. So I'm going to pause for a second and let you think about this. Why do you think clouds have a silver lining? I'm going to give you 30 seconds. I actually can't see the chat, but you can put your thoughts there. Okay, I'm going to give it 10 more seconds and then we'll dig into it. It's a fun expression, but it also is true, right? We can see it with our eyes, this kind of illuminated edge of the clouds. Okay, so long story short, for the poetry of it all, that's very good. Long story short, the thin edges of the cloud let the light through, but the thick center blocks the light. But there's actually some more physics there. And so we're going to touch on a few of my favorite concepts from atmospheric radiation or the movement of sunlight through the Earth system in trying to answer this question. So first, we'll think about optical thickness, and that's basically how much water mass is there. So there's less water at the edges of clouds, and those optically thin edges let the sunlight go through easily. You might also wonder, why are clouds white, and particularly those silver or white edges? Well, that's because cloud drops scatter visible wavelengths roughly equally in all directions, and so together those different wavelengths look white to our eyes. But the dense core of the cloud scatters light a lot. There's a lot of scattering going on, even some absorption. And so very little light reaches your eye, and that makes that center part of the cloud appear gray or dark. But there's more. So there's diffraction. So light, which we could think of as a wavelength, bends around the drops, especially if they're around the same size at the cloud's edge. And this could concentrate extra light along the rim of the clouds and intensify that bright outline. And then there's one more thing going on, particularly if the cloud is like directly backlit, which is this concept of forward scattering. So for cloud drops, we're very much in this third regime here, where when the sunlight is scattered by a cloud drop, it preferentially just goes right on forward. And so if the sun is behind the cloud, the sunlight from the thin edges goes right towards your eyes. Okay, that was fun. That's more physics than you might expect for a simple poetic question. Let's answer another one. Hold on, this is a fun graphic, so I'm gonna hopefully let it load. Let's see, give it another try. Okay, that's okay. So why do cloud shadows stretch as the sun sets? I'm glad this one's working. So while you think about this, I'll let you watch this animation, which comes from a simulation I use as part of my research. So why are these shadows stretching? Yeah, exactly. It's basically geometry and the angle. Ooh, nice. Yoga, the shadows stretching like yoga. That's true. The sunlight intensity does change as it gets lower in the sky, but the first answer that I saw popped up looked like probably closest to what's actually going on here. So it's kind of like a geometry problem. The angle of the sun is changing. So I'm going to kind of break this problem down, and I'm using an idealized setting, and I find this really useful when I'm using my research. So I want to answer a complicated question: what's going on with these wacky shapes? But I picture the simplest and the smallest problem I can. So let's picture a spherical cloud. When the sun is overhead, the shadow sits directly beneath the cloud, and its shadow is basically the same size of its silhouette area. But as the sun moves lower in the sky, well, for the spherical cloud, the simplest case I could think of, that silhouette area is not changed. But the 3D shadow area on the surface increases due to stretching. And that's basically just the projection of that onto the surface. And that changes based on the solar angle, how high or how far it is from directly overhead. Okay, so let's build on this conceptual model a little more. Clouds aren't just spheres, they could have some aspect ratio. So let's picture an ellipsoid, a slightly taller cloud. In this case, the shadow area could change from not just stretching, but also changes in silhouette area. So as the sun gets lower in the sky, the outline of that cloud gets bigger. We're seeing the tall sides, and that kind of boosts the increase in shadow area at the surface. It would work the other way for shorter clouds. Okay, and now you might be wondering why we care about predicting the shadow size. Well, in many models of atmospheric radiation or sun and clouds, the shadows don't actually stretch. And this is what we call a one-dimensional approximation, where the horizontal movement of light is neglected, we don't worry about it, and it just moves up and down in the vertical. And this is one of the compromises we always have to make when we do modeling. It's expensive, takes a lot of time on the computer, so we have to decide what's really important. And so this is often left out, but it might matter. And so that's why we were asking these questions. So in my research, we asked some questions about this. We asked, how does that bias, the 1D approximation, the average amount of sunlight that reaches the surface? And how does the bias change with the sun's location in the sky? And the plot on the right-hand side is part of the answer. So it's showing you the difference between 3D, a world where shadows can stretch, and 1D, where the sun is always overhead, although the intensity can change. And we can see that basically on the left side of the plot, when the sun's overhead, in the 3D in our world, it's a bit higher. And then when the sun's really low and the shadows are stretched and big, so we have a much darker surface, that changes sign. The 3D or the real ground truth is lower on average. And then we asked the question, can we predict this using some simple theory? And I walked you through some of the concepts that I used to build that theory. But if you're looking for more answers, you're welcome to read our manuscript by using this tiny URL. But then I just wanted to wrap up by saying that science is a lot of fun. Asking questions is one of my favorite things. And funding for science has allowed me to turn my curiosity into research skills. And that's something I'm incredibly grateful for. So from summer programs as an undergraduate, including a research undergraduate experience, to my current PhD funding from the Department of Energy, I just wouldn't be an atmospheric scientist in training if not for federal support. So I would encourage you to reach out to your representatives to tell them just how important funding is for developing young scientists like me. And with that, I'll say thank you, and I'm happy to answer any questions.
Thank you so much, Maggie. That was a really cool talk. The chat was not underselling how great the animations that you have are. I recognize you using ParaView for some of those 3D animations.
Yeah.
So thank you so much for showing those. That was really an illuminating talk. Let's see. Let's see. Do we have any questions for Maggie in chat specifically? I'll wait for a couple to pop up. While we're doing that, I'll take host's prerogative and ask. So, as you're modeling all of these clouds and the impacts on the shadows, do you see or think about the relationship of how, you know, a warming or thickening atmosphere might have to changing the structure of the clouds, and then therefore the shapes of the shadows on the atmosphere, on the surface?
It's a good question, no pun intended. It's not something I've thought about, but of course, if you had changing in aspect ratios, that silhouette area concept I introduced, so basically how tall your cloud sides are, that would affect the shadow size, particularly when the sun is low in the sky. And so that would impact things, but I haven't thought about that. That would be interesting to try.
I hope it turns into something. Let's see, we have a question. Why are clouds diminishing? This is from a ComQuest.
Oh, well, you've asked one of the hardest questions in climate science is like, how are clouds going to change with climate change? And to be honest with you, that's why we study them. It's why you've heard a lot of cloud talks probably over the live stream, is because we're not sure exactly. For instance, low clouds, there's some regions where we think they might become less prevalent, less thick or less frequent, and that would really change the energy balance. For thick clouds or deep clouds, that would, yeah, there's different feedbacks, but why and if is a huge question, and that's why we spend so much time on it.
Yeah, of course. And I mean, it goes without saying that we would have no hope of maybe answering some of these questions if all of our funding is cut. And that's why it's so important to go contact your representatives. And by the way, I've seen in chat scroll by where people have complained about, oh, well, I've already contacted them. They're probably getting tired of hearing from me. Who cares? Contact them again. They're your representative. They're there to listen to you. So you want to call them again? Call them again. Do it every single day. Call early, call often, is what I would say to all of that. Did Maggie freeze again? Did we lose her? Looks like we lost her again. Oh, that's too bad. Thanks again, Maggie. It was an excellent talk. Your animations were terrific. I'm sorry we lost you again. We're all having technological problems this evening. So I'll just continue on with the stream this evening. Once again, you are listening to the Weather and Climate live stream 2026. I am Michael Battaglio. I'm your host for the next 45 minutes or so, up until midnight. I'm glad to be here. I'm thankful all of you are here with me. We are here for an important reason, though. And that reason is we all need to band together, reach out to our Congress critters, and let them know that some of the proposed cuts that we're facing in climate science and the weather enterprise in particular, but also throughout all scientific endeavors and fields in the United States, it's at risk. But there is something that each and every one of us can do about it. And that is to reach out to your congressperson and let them know that you are not in favor of these cuts that have been proposed. You want budgets to be at least flat and or to increase to help keep up with inflation. And we're not doing this just to get lots of grant money. There's a purpose behind it as well, and it's a purpose that serves the US taxpayer. Over the last 80 years, we've built an impressive, amazing, phenomenal series of studies and data collection and models that have helped us interpret and understand and forecast the atmosphere. And in so doing, we help drive the US economy, we help protect lives and property, and we inspire the next generation. Every single dollar that we put in R&D, a recent study, I was just reading in Forbes the other day, every dollar we put in, we get $2 back into the US economy. So really, it's not just about the science on its own. Even if you didn't care about the science, we still stimulate the economy greatly by putting money into research and development. And this research and development can't necessarily be made up by the private sector because the US government is so important in funding research. It's what makes all of the science that we do in America really the envy of the entire world. And it's really what drives and pushes forward learning throughout the globe. So that being said, I'd like to, we'll move on early, I think, to the next speaker. I will say, just to remind everyone that everyone that's talking here is talking as a private citizen. They're not speaking on behalf of their employer. They're speaking just like any other US citizen would. But we all agree, and there's strong agreement amongst all of us, that we need to fund science in and across the United States. Are we ready for Casey? We're coming up at 11:20 now. Oh, here we go, popping it up. Hello. Up next, we have Casey Ivanovich, a postdoctoral fellow at a government lab. We're going to learn about extreme heat, one of the really scary topics, and that's very critical to help us understand and navigate the changing climate. So I'm thankful to have you here. We're grateful to have you here. We're excited to hear what you have to say, Casey. Take it away.
Yeah, thanks so much for having me. I'm excited to participate in this year's live stream. So yeah, my name's Casey Ivanovich. I'm a postdoctoral fellow at the NASA Goddard Institute for Space Studies. So as a NASA postdoctoral fellow, I'm fully funded by the federal government through a fellowship grant that I won 2 years ago. And the work that I'm doing that's supported by this grant, and in the longer term work that I've done throughout my PhD and even in my undergrad, was all supported by federal funding. But the work that I'm doing right now focuses on when, where, and why extreme heat events occur. So when we tend to think about climate hazards, I think we picture something very dramatic, very destructive. But when heat waves are written about in the news, we're fed these kinds of fun in the sun images. People eating ice cream in the shade, families spending the day at the beach, children playing in park fountains. But in reality, year after year, extreme heat is the deadliest weather extreme in the US and many other regions around the globe. We can see this in example data from the National Weather Service, which shows that weather-related fatalities in 2024, the past 10 years, and the last 3 decades have all been dominated by extreme heat events. But not all heat events are created equal, and the timing of extremes can really influence how dangerous they can be. This is especially true if extreme heat events take place outside of the traditional heat season. So for example, extremes that occur in the spring before the start of the traditional heat season can catch people off guard. This is before individuals may be acclimatized to higher temperatures and when they're sort of behaviorally unprepared to utilize heat cooling strategies. In contrast, if heat extremes occur during the fall, there may be a larger strain on people physiologically or on heat mitigation infrastructure after a long heat season where we have repeat exposure to extremes. So this makes seasonality a really important characteristic of extreme heat, particularly for its impacts. A recent example of heat that was really extreme in its seasonality comes from Phoenix, Arizona in 2024. So Phoenix is no stranger to extreme heat, but the summer of 2024 was really unusual. During the summer, Phoenix experienced over 110 days in a row above 100 degrees Fahrenheit. The temperatures dropped down for a couple of days and then shot right back up for an additional few weeks in the month of October. Now, 100 degrees Fahrenheit, not a super intense magnitude of temperature in a city like Phoenix, but what was record-breaking was the duration and the timing of this extreme heat, and especially the record-breaking extremes that happened further and further into the fall season. So this really provided motivation for exploring whether these kinds of out-of-season heat extremes are starting to pop up more and more around the world. So recent papers have really pointed out that warm seasons, or the summer season overall throughout the mid-latitudes, are lengthening, and that this expansion is expected to continue in the future with ongoing human-caused climate change. But we don't know if changes in the overall summer season will align with changes in the timing of individual extreme events. So in this project, we wanted to understand historical extreme heat seasonality around the world and also quantify how these extreme heat seasons have changed over the last 45 years. In order to do this, we just need a baseline definition for extreme heat seasons. And the simplest way we tend to do this as climate scientists is thinking about meteorological summer. So this is June through August in the Northern Hemisphere and December through February in the Southern Hemisphere. This definition just follows when it's hottest and coolest on average in each hemisphere, but it doesn't account for any regional differences in temperature seasonality, and it also can't measure any changes over time. So we address this by making our own method, thinking about when in the calendar year extreme temperature events have historically tended to occur. As an example, we'll pull out the data for Phoenix. And so we're going to split the year into weekly bins, so the 52 weeks of the year, and plot the number of extreme heat events that have occurred in each of those bins in the earliest 10 years of the temperature record, so during the 1980s from this data set. So to orient ourselves, on the x-axis here, we have the months of the year, and on the vertical axis, we have the number of extremes that are happening in those weeks. And we're seeing, in this example, the highest frequencies in June and July. Now we're going to define the extreme heat seasons as being the 3 months per year which exhibit the highest frequency of extreme events. So this is the same length as our typical meteorological summer. But we're also going to create a pre and post season as the 2 months before and after that extreme heat season. So in Phoenix, where we think of there as being 4 distinct seasons, we can think of these as functioning like spring and fall. So you can apply this definition globally and identify that center month of the 3-month heat season at each point around the world. So if we had just used our simple meteorological summer definition, this would be all July in the Northern Hemisphere and all January in the Southern Hemisphere. So we can already see that we're capturing a lot more spatial differences using this definition. We can also calculate the fraction of extreme temperature events in the 1980s, so in that baseline period, that occurred within those defined extreme heat seasons. And so we see in this figure on the right that this number is quite close to 1 throughout most of the globe. And this is true throughout even in the tropics, where we tend to think of seasonality as being much less defined. So overall, globally, historically, we've seen that extreme heat events just tend to occur in one season. So once we've established what heat seasonality looks like in the baseline, we can also use these methods to explore whether seasonality is changing. So coming back to Phoenix as our example, we're now going to also plot on top of that baseline period the occurrence of extreme events happening in the last 10 years of the temperature record when we started this project, so from 2015 to 2024. So maybe we can see that the distribution throughout the calendar year is changing a bit, but these patterns are quite complicated by the fact that our climate is changing. So as temperatures rise, we're experiencing a much greater number of extreme events overall. In Phoenix, for example, we saw 136 extreme temperature days in the period from within the 1980s, but in the last 10 years, this has increased to 281 events. So maybe a better comparison is to instead plot the fraction of extreme temperature days that occur in each week of the calendar year instead of the total number. So right now, we're just changing that vertical axis to be the share of extreme events rather than the absolute number. And so this helps us identify that we can see a clear decrease in the number of heat extremes that are happening in the heat season and primarily the early part of the heat season, while we see that the fraction of extremes that occur during the postseason or the fall are increasing. So for Phoenix, it appears that the extreme heat season is starting to expand, but it's doing so asymmetrically. So we're having more extreme heat events lengthening into the fall, but not into the spring. So we want to be a little bit more quantitative about these changes. So we're going to measure these shifts in seasonal distributions in a couple of different ways, but we're particularly curious about what's happening at the very edges of the heat season. So next, we're going to plot the difference and the change in the fraction of extremes that happen in the fall versus in the spring between these two time periods, so over the last 45 years or so. So globally, we again see that most changes in the frequency of extreme events happening in the spring and fall are expanding in an asymmetric way. So any locations that are shown in purple have experienced a larger expansion of the heat season into the fall, while locations in green have experienced a larger expansion into the spring. One example that I want to highlight is what's going on in the United States. So in this region, we're seeing a lot of purple, and this is indicating that we're having a larger expansion of the heat season into the fall. And this has important implications for things like compound extremes. So imagine we're someone living in the Western US, a heat season which creeps later and later into the year is going to increase the existing overlap with the existing wildfire season. But if we're on the eastern coast of the US or in the Gulf Coast, for example, the expansion into the fall could potentially increase the overlap with the Atlantic hurricane season. And so because the impacts of compound extremes, having these two, heat wildfire or heat hurricane events happening at the same time or in rapid succession, the impacts are going to be much greater than if these events happened in isolation. And so this kind of information is really essential for disaster preparedness and making sure that management is ready to tackle these challenges. So to summarize what we've seen in this work, we saw that in previous decades, extreme heat was pretty well constrained to a singular heat season. And this was even true in much of the tropics where we don't have much temperature seasonality overall. But we've seen that over the last 45 years, extreme heat seasons have expanded over most of the globe. And this expansion is taking place in a way that's asymmetric. So some places are having larger expansion into the fall, while others are having larger expansion into the spring. And so as we look forward, we really want to be able to understand if these patterns will continue into the future. And so this is where climate models come in. We first want to know if these kinds of historical patterns are being captured by global climate models, and then we can use those models to say, are these patterns going to continue into the future or are they going to change? And so these extensions are really essential to understand how extreme heat seasonality may change in the future, providing essential information about how we might need to adapt our adaptation planning and emergency management. So it's very important to keep funding these and other climate projects to really keep everyone safe. So I want to emphasize my support for everyone making calls or writing to their representatives to stress how important this funding is to continue. So thanks so much, and I'm happy to answer any questions.
Excellent slides. Thank you so much for that really concise, well-described, visually appealing talk. I really liked the explanation of your methods and how you developed the understanding of the expanding heat seasons. We have some great questions in the chat, and you're all asking great questions. We're not gonna have time for the ones that I have. Anyway, let's start from the top. We have some terrific questions. Failure Son here. Over and over again, you're asking great questions. I really love the questions you're asking. But they ask, could this fun in the sun type reporting of heat waves be a contributing factor to medical complications caused by heat waves, since people probably won't be preparing as they should be, given the kind of conflicting messages that might be sent around?
Yeah, this is a great point to stress. I think one of the aspects about working on extreme heat is that we can understand the physical hazard, we can predict it well, we can forecast it well, and there still is sort of this behavioral component that we are totally, as climate scientists, not in charge of, and is really hard to capture. And so there is inherent in everyone a bias to think, I know that heat waves are risky, I know that it's dangerous, but I'll be fine. And so I think a lot of these messaging campaigns can really not necessarily provide misinformation, but lead people to take these events less seriously, to assume that they'll be fine, to kind of reinforce this bias that it's not really something that I specifically need to worry about. And so that is something that I think climate scientists and social scientists can really work hand in hand to improve the communication of these kinds of risks and make sure that people keep themselves safe.
Yeah, absolutely. Totally agree. Next question from Cambrian. Could the asymmetrical hottest days have anything to do with longer days in October versus March, or sun angle in different months?
Yeah, this is a great question. Yeah, and so that could certainly have an influence over these different spatial patterns, given that different regions are going to experience different length of days in different months. There's been some really interesting work on the Pacific Northwest heat wave, particularly that happened in 2021, looking at how day length, the fact that this happened at a time when the day length is maximized in this region, how much that contributed to driving the intensity of the extreme heat. So it certainly is a factor. Other things that we would think about are how the hydroclimate is changing. So if there's changes in precipitation, that can kind of remove a cooling source if we're drying out the surface. If There's changes in local land use. So if we're irrigating more, maybe that cools down the surface. Or if we are urbanizing more in some regions, that is going to heat up the surface. So there's a lot of different mechanisms at play that I think we'll need to, as another future extension of this work, really look at sort of regional analyses to understand what's going on at each location on the globe.
Yeah, excellent. Interesting answer. Next up, we have What is My Life? Who's asking a question that I also have, which is, do you have explanations, ideas for why some places have the expansion pre-season in your little leaf in the spring, which I really liked, or in the fall season with like the maple leaf, which I also really liked? So what's controlling perhaps the differences in which side the directions are happening in space?
Yeah, so each of those kind of mechanisms that I listed off are going to contribute differently in different directions. And so I'll take Phoenix as the example because I talked the most about that, and it was kind of the case study for this project. So we know in 2024, when we had this totally insane summer season where the heat just dragged on and on and on, and we particularly had record-breaking extremes in October, that this was a really dry summer. And so having really dry surface and removing all of the moisture source is going to remove evaporation as a key cooling process at the surface. And so that allows higher and higher temperatures to build throughout the duration. And so we think that in Phoenix or in the Southwest US more broadly, it's got something to do with these drying processes. But if we look at recent papers that have identified sort of changes in soil moisture and precipitation in the spring versus fall, we actually might expect the opposite pattern to emerge, where we would tend to see more expansion into the spring season. So clearly these are very complicated processes that we need to dive into really explicitly to understand the trade-offs between sort of these surface processes and more sort of circulation-driven changes. So it's a great question, and I would love to dig in more in the future.
Yeah. Great, and you need funding to do so, which is why you should contact your congressperson right now and tell them that Casey needs funding. Go do it right now. Next up on the docket for questions, we have from Stu Weiss, how does the March 2026 event change your seasonality, or are you not counting it as an extreme heat event specifically?
Great question. So this does not rank as an extreme heat event in this specific definition. So this was a particular, there might be a couple of days, let me preface, I haven't explicitly looked at it, but there might be a couple of days that, rank in our distribution graphs as being extreme days. But what was particularly crazy about March was that it was so unusual for March. But how we're defining extreme temperature days here is saying, what is a really hot day? So it's gonna, an extreme temperature day in our definition is a 95th percentile temperature day. So this means that it is in the hottest 5% of days in history in each given location on Earth. And so it's gonna be really hard, even if it's a very unusual March, for it to pass that threshold for the entire year. So it would have to feel like one of the hottest, August days, for example, in March, which some of the days may have crossed that threshold. I'm not going to hold myself to that, exclusion. But in general, these are two different ways about thinking about unseasonable heat, and they have really different implications for impact. So for this project, we're thinking about, what are the hottest days that are happening at a given location in terms of the magnitude of the temperatures. And this has really important implications for things like human health. So high temperatures can act on the human body on very short time scales. So one day of a heat event can be detrimental, as well as if you have prolonged, day after day exposure, or if you're having, it happening in different times of year. But if we think about what is really unusual for March, especially when we have, a full month being so warm in comparison to the historical values in March, this has really important implications for things like growing seasons and plant health. And so how we define extremes and how we define seasonality really depends on what we're trying to answer a question for, what we're thinking about is at risk, and what kind of information we want to uncover.
Yeah, very, very interesting answer. Next up, we have a very good question from Sydney Lindquist here. Is unusual spring heat becoming an accurate indicator of extreme summer heat? We've been hearing a lot about seasonal and sub-seasonal predictability. So does one follow the other? Are they not exactly linked?
Yes, in some situations, yes. So particularly when we have these, like in Phoenix, we saw this kind of multi-month mega heat wave. And so the drying conditions that are setting up this really long, persistent, and duration heat are going to facilitate more extremes happening later in the season. And so that is definitely a possibility. It's also possible that different time scale mechanisms are going to kick in, and that we might have heat popping up in March that then does not follow in the following seasons. So it depends on the location, but there are certainly circumstances in which we have these very extreme persistent events which build and build and build and build and can extend the duration into summer.
Yeah. Time for one last question from Cambrian here. Does ground cover matter? Really pulling on some threads from earlier today. One of our talks said green space in cities holds heat. Are those scales too small to matter? Do you see them here?
Yeah, so the data sets that we're using for this analysis don't take any kind of like urban scale information into account, but it certainly takes other kinds of land cover is reflected in this data set. So when we're thinking about irrigation is can be really large scale. That kind of influence on the surface is going to make a big difference, as well as agricultural expansion in general. Planting more sort of green materials at the surface is going to change the surface energy balance and move energy from one space to the other. And so, yes, definitely surface cover, the albedo, so how reflective the surface is, as well as the vegetation that's at the surface, which is evaporating, doing this process of evapotranspiration, so converting heat via the process of evaporation mostly, to cool down the surface are all going to be really important aspects of this of these patterns.
Well, thank you so much. This has been a fantastic Q&A. Thanks for your answers. Thanks for joining us, Dr. Ivanovich, and thanks to the chat for some of these fantastic questions. This has been really a really great discussion we've had over the last little bit, but we need to move on to our next speaker. Thank you so much for joining us. You were here last year. Thanks for coming back and do it again, Dr. Ivanovich. Glad to have you. As a reminder, I am here talking to you on the 2026 Weather and Climate live stream. We're here today and over the next 18 more hours. We're already in hour 32, 18 left, and we're talking about and hoping to inspire all of you that are watching to go out there and contact your congressperson and let them know that the proposed cuts that we're seeing towards science and climate, the attacks on the National Center for Atmospheric Research, cuts in the National Weather Service, those can't be allowed to stand. And the reason for that is we know over the last 80 years that fundamental research into understanding our weather and our climate benefits life, it benefits saving property, it helps us understand the atmosphere, it helps boost the economy. Every dollar we put into R&D, we get roughly $2 back based on some studies. Some have it even more than that. But we get money back when we put it into the economy, when we do scientific research. And if you hear discussions or comments about from various politicians of certain types that, well, it's all a hoax, we don't need to study this. Take a moment and think about, well, where are they getting their campaign contributions and donations from? I can assure you none of us research scientists are getting rich off of doing this. We're doing this because we care about it. We are doing this because we know it helps the American taxpayer, and we're motivated to understand the weather and climate that we live in. And we need you, viewers out there right now, to do what you did last year, to step up again and reach out to your congressperson and let them know that we can't have these cuts, and flat budgets are okay, but even better, we need to increase our scientific R&D budgets to keep up with inflation. And not only that, we need to push back against some of the illegal impoundment efforts that we're seeing, where Congress appropriates the money and then the federal agencies don't spend it, and that's illegal. And we have to make sure that Congress grows a backbone and actually takes some of its power back and asserts its authority the way it should. Well, we have one last talk left before we get to the end of the day here on the East Coast, and I'm very thankful and grateful to have our last speaker. We have Charlie Coven, a research scientist at the government lab. We're going to be talking about, is climate change reversible? Very interesting question. I'm excited to hear what this talk has to say.
Great, thanks so much. Yeah, so the talk I'm going to give today is called "Is Climate Change Reversible?" This is a photo I took above where I live in Northern California a couple of years ago during one of the big wildfire days when the whole Bay Area was covered in smoke. And this is just an example of one of the many types of impacts on climate change that we're all feeling right now. And so the way I want to frame this is, if you look at what we would need to be doing in order to achieve the Paris Agreement goals of limiting global warming to either 1.5 or 2 degrees C, we're basically not doing it. So, in this figure here, the green emissions trajectories are what we would need to be doing to reach 1.5 C. The blue is what we need to be doing to stay below 2 degrees C. What we're doing is this upper line. And if you factor in all the various scenarios that the countries of laws that have been put into place to reduce emissions, that gets us down to those red and orange lines. But we're not doing what we need to do to limit global warming to the Paris Agreement levels. And so the question I just want to ask here is okay, so even when we fail to keep global warming below a given level, what would it take to bring the global mean temperature back down to that level afterwards? Because we're simply not on track to meet our goals. And so if we fail, then what? Is there any chance that, is it even physically possible to get back to these global warming levels afterwards? Okay, so that's the question I want to ask. In order to answer that question, I want to talk through this sort of chain of causality between CO2 and climate. I'm going to start with CO2 emissions. So that's what society is doing. What the thing that we could plausibly build policies around. And so we're emitting, CO2 into the atmosphere, about 10 petagrams or 40 gigatons of CO2 every year. It's been rising, although it's been roughly, much slower rate of growth over the past decade than previous decades. So that's the first link in the chain. Second link is the CO2 concentrations. We know we can measure CO2 rising in the atmosphere. Sure, you maybe seen this figure before of the measure of CO2 in Mauna Loa, Hawaii. It's inexorably going up with this seasonal cycle on top of that. And next is climate change, and we can see global warming levels are going up. We're closing in very fast on 1.5 degrees C of climate change. So that's that's sort of the third link is emissions to concentrations to climate change, and then impacts. And again, I'm showing this picture of smoke near where I live, and that's one of the most salient climate impacts that we feel. To the extent that we have global policy around, like say, the 2015 Paris Agreement, it's linked around this chain kind of in reverse. So the Paris Agreement says that we want to hold global warming below 2 degrees C, or ideally 1.5 degrees C, in order to reduce these impacts. And then working back from that goal, it says we need to get to net zero in order to stabilize the climate. And so I want to walk through each of these links in this chain in tandem in order to understand this question of whether or not climate change is reversible. So between the first two links, between CO2 emissions and CO2 concentrations, a lot of mechanisms happen. Only about half of the CO2 that we emit stays in the atmosphere. So this figure here shows, emissions over the past decades, or century and a half, and then where that CO2 has ended up. So of what we emit, about half of it stays in the atmosphere, and the other half goes into the land and ocean. And this is what's been happening historically, but that could change. And in order to answer the question of, well, how might that change, we build Earth system models, which take climate models and couple those to carbon cycle models, And then look at how all these things interact so that we, with lots of processes, we've got, dissolving CO2 in the ocean, changing the ocean chemistry. On land, we've got, permafrost thawing, we've got soil respiration, plants growing and dying, all these things interacting with each other, which are all climate sensitive processes. And we build these super complicated models to try and understand these things. And when we take these models and ask, well, do these kind of proportionality of CO2 and the climate change, between these two first links of CO2 emissions and CO2 concentrations, the answer is yes. We actually expect that the more we emit, the more of what we emit will stay in the atmosphere. So this figure comes from the most recent IPCC report showing that under scenarios with high amounts of CO2 emissions, more of that CO2 stays in the atmosphere. Okay, so that's the first two links. Now I want to go to the second two links between CO2 concentrations and climate change. And what I want to argue here is that if we just look at this relationship between global mean temperature change and CO2 concentrations, that can actually lead us to asking some of the wrong questions. And the way I want to sort of argue that is that if you can imagine two curves in this space of temperature as a function of CO2 concentrations, and there's basically a short-term climate response, which is less extreme than the long-term climate response. Basically, the short-term climate response is the atmosphere and the upper, just the uppermost parts of the ocean warming. And then after a long period of time, the whole ocean warms. And so you can get more warming in the planet system. And so we quantify these two metrics using these two climate sensitivity metrics called the transient climate response, which is the short-term response, and then the equilibrium climate sensitivity, which is this long-term response. But these are just 2 points on these curves that relate the global mean temperature change as a function of CO2 concentration. And if you imagine, where we are right now, we're sort of somewhere on one of these curves, right? Where basically humanity's, pumping out CO2 into the atmosphere, basically, as fast as we can. And as a result of that, CO2 concentrations are going up and global temperature changes are also going up. But if you imagine, if we successfully mitigate climate change, we'll get to some point where CO2 concentrations stop going up. So we'll stop moving from left to right in this space. And then the question is, well, okay, so what happens then? And historically, the answer was, well, we have to move from this dashed line to the solid line. We know that's what sort of how the system works. Over time, the planet's always going to tend to move from this dashed line to the solid line. And so that if we hold concentrations constant, then the planet's still going to keep warming for some long period of time afterwards because of the tendency for the oceans to heat up and the planet to heat up as a result of that. And we can call that the constant concentration commitment. Basically, is there committed warming in the pipeline from holding CO2 concentrations constant? But what that ignores is that there are actual natural carbon sinks that tend to want to pull CO2 out of the atmosphere. Just as half of our CO2 emissions currently go into land and ocean, we expect those to continue even if we stop emitting CO2. And so that's going to tend to pull things to the left here. It's going to tend to reduce CO2 concentrations. And so these two things interact and give us this other metric that we call the zero emissions commitment, which is basically this trade-off between the two tendencies. On the one hand, we know that our system wants to move from this dashed short-term line to this solid long-term line, which is going to tend to warm the planet. But at the same time, sinks going to tend to pull from right to left and tend to reduce CO2 concentration. So we expect that around zero emissions, that you might get a little bit of warming and a little bit of cooling, but mostly you'll get climate stabilization. Okay. So what about the relationship? What if we actually look at the first two links, or we skip that second link and look just between the CO2 emissions and climate change? Now we've taken all the physical climate, all the carbon cycle, put all these things together, and you might expect that we've added really complex system to another really complex system, and so we're going to get just crazy complexity in this relationship between global mean temperature change now as a function of cumulative CO2 emissions instead of concentrations. But what actually happens is weirdly the opposite. Instead of getting a much more complicated story, we actually get a much simpler story, which is basically that this relationship between cumulative CO2 and temperature has two key features. One is that it's basically just a straight line. It's linear proportional. Global mean temperature change is proportional to cumulative CO2 emissions. And the second is that it's emissions pathway independent. Basically, all of these different scenarios that we use for things like IPCC reports, they all fall on top of each other in this space. So this much more complicated system that I showed in the prior slide boils down to this basically a straight line where the more we emit, the more temperature rises. And this gives rise to the idea that every ton of CO2 matters. Every ton of CO2 leads to additional warming. And so we can quantify this slope of proportionality as the transient climate response to emissions. It's like an annoying acronym, but it basically allows us to, it's just the slope in this line. How much warming do we get per ton of CO2 that we emit into the atmosphere? And then there's this zero emissions agreement that I talked about before, this tendency of sinks to kind of balance out from the gradual warming that happens for a given CO2 concentration, is basically in this space is what would happen if you stop moving from left to right. So, if we currently we're moving from left to right, we're emitting a lot of CO2. If we abruptly stop emitting CO2, the path dependency argument would say, well, if we stop moving horizontally, then we should also stop moving vertically. And roughly that's true, but it's not exact. There's still maybe a little bit of extra warming that might happen after we stop emitting CO2. Okay, so the question I motivated this for is, okay, so if we fail to achieve our Paris Agreement, is there any going back? In the most recent IPCC report, what we said there was, at the time, that there was limited evidence supporting this quantitative application of TCRE, i.e., if you're moving from right to left in this space, you might follow the same slope, but it might be a slightly less slope or slightly greater slope. And we didn't really know at the time when we wrote the sixth assessment report. And so since then, this has been one of the questions that's been motivating me in my research. And so I'm going to talk about some experiments we've done to try and test this. And the first is this: we basically designed this like very idealized experiment to test this. It's symmetric and continuous emissions reversal experiment to infer this reversibility. And so if you imagine this, like I try to think like what's the simplest possible experiment? You imagine basically you first start emitting positive amounts of CO2, then you get to some amount of peak emissions rate. And then you reduce emissions until you get to net zero. So on the left is, the annual emissions cost zero, which means the cumulative emissions stop increasing. And then imagine some imaginary currently, because the technologies do not exist for this yet. But, we might, people might come up with great technologies to pull CO2 out of the atmosphere in, several decades from now. So let's just imagine some hypothetical negative emissions technology that would then pull out as much CO2 from the atmosphere as we previously put into it, until you get down to cumulative zero emissions. And just ask, what does the coupled carbon climate system do under this kind of scenario? Okay, and so then we take, what I did here is took the Communicators system model, which comes out of the National Center for Atmospheric Research with lots of collaborators around the world who work on this. And it's a model I've worked on for a bunch. And so we would take this Communicators system model too and run it through this very simplified experiment. So it's basically an atmospheric model, land carbon cycle, ocean physics, everything interacting with each other. Okay, so what are the results? So basically, here's this cumulative emissions curve that I showed from the last slide. It peaks, 150 years into the experiment, and then it goes back down to zero. And so first, let's look at the atmospheric CO2. So because this is an emissions-driven experiment, the model is predicting the atmospheric CO2 as a function of our emissions plus the sinks in the land and ocean. Interestingly, the atmospheric CO2 concentrations peak before the cumulative emissions peak, i.e. before net zero. So the atmospheric CO2 actually leads our emissions, peaks before cumulative emissions peak, and starts to decline before we get to net zero, because of the fact that at the point when you are at net zero, the sinks have already kicked in, are still happening. So CO2 has to be declining at that point of net zero, and that forces the warming to lead the emissions. The climate here, just the global mean surface temperature change, then lags the atmospheric CO2 and it basically lines up with emissions. And it actually, in this particular model, it actually also slightly leads the emissions. So you get a slightly faster decline in temperature than cumulative emissions. But this is just one model. But basically, the point is that these two leads and lags kind of offset each other. And so the climate is actually weirdly just in line with cumulative emissions, even under this reverse, this sort of crazy reversal scenario of reimagining a world where we pull as much CO2 out of the atmosphere as we previously put into it. Okay, again, that was just one model. So then we said, okay, well, what we really need is to get a bunch of the Earth system models around the world to actually do this, so we can understand the response to this. And so, what can we learn from an even simpler set of experiments, testing the coordinated response of the climate system to positive, zero, and negative emissions? So the first part of that is, let's imagine just emitting 10 petagrams of carbon per year. So it's roughly the amount of CO2 that we're emitting right now. So that's the annual emissions, just a flat line, 10 petagrams per year for hundreds of years. What that means is that the cumulative emissions is just a straight line going up. And because the proportionality of global temperature change to cumulative emissions is also a straight line going up with some uncertainty because we don't know exactly the slope of this TCRE. And then second part is if we abruptly stop emitting CO2 at year 100 in this experiment, so that the cumulative emissions sort of flatlines after that, and then we expect the temperature change to also flatline. And from this one, we can measure this zero emissions commitment. It's basically the warming 100 years after we stop emitting CO2. And then it's for this reversal experiment, it's basically this similar design to what I just showed, but now fully linear. And so it's basically just reverses from positive emissions through net zero down to negative emissions. And the question is, does the temperature change reverse also? Okay, and so basically what happens across 10 of our system models, we see roughly the proportionality we expect, that the temperature increases or flatlines or reverses. And here's the key point, is that if you're in this space of the global warming as a function of cumulative CO2 emissions, we basically see no irreversibility across all these Earth system models. That this single number, this TCRE, which is like this shockingly simple relationship between global climate and cumulative CO2 emissions, it holds roughly, even under this crazy scenario of pulling all the CO2 out of the atmosphere that we put into it. But there's a lot of extra spread, right? So the red line is during the positive emissions phase, and we've sort of normalized it. So everything goes through this point of one and 1,000 petagrams of carbon. But then we see this spread really widen up afterwards. So there's additional uncertainty. We don't expect there's nothing fundamentally irreversible, but the uncertainty is quite wide. And if you look across all the different models, they see some of them do have a positive irreversibility, some of them have a negative irreversibility. In general, it's related to the zero emissions commitment. You see a similar thing happen under negative emissions as under zero emissions. But you have this wide range of things. So basically, the take-home points here are, one, that the proportionality of global warming to cumulative CO2 emissions, this TCRE metric, it's just a single number that relates to the global warming. The global mean surface temperature change is a function of cumulative CO2 emissions, and it holds across an incredibly wide range of scenarios, from large amounts of positive CO2 emissions to large amounts of net negative emissions. There may be some degree of irreversibility in this temperature to cumulative CO2 emissions relationship, and it's well captured by this other metric, the zero emissions commitment, which is also how much temperature would continue to change if we were to abruptly stop emitting CO2 emissions. But all of what I just said only applies to global mean surface temperatures, right? It does not mean the climate impacts can be reversed or even stabilized if we can stabilize temperature. But it's an important step. Stabilizing temperature is kind of the goal of climate policy. And after that, maybe the goal of climate policy might be to actually get back to the temperature we have right now, which by the time we get to net zero will seem probably quite cool compared to where the planet is at when we get there. So that's it. I'll stop.
Thank you so much, Dr. Colvin. I mean, that was a great talk, and it's kind of a little bit relieving, I suppose, that if we might be able to turn things around if we develop the technology to help with removal. Unfortunately, we do need to move on because we need to do a stream change right now. So
okay, sorry about that.
Yeah, no problem. We are at midnight. We're at the top of the hour. Welcome to June 3rd, everybody. We're about to start hour 33 of the Weather and Climate live stream, and I see the directors in the background working to prepare for the live stream. What you need to do right now is go to wclivestream.com/watch. The link will change just because we don't want the YouTube files to get enormous and we can't deal with them, and it makes it a pain to deal with. So we're going to reset the YouTube stream. So we need you to go to wclivestream.com/watch. Click on that link, go there right now, and it'll send you straight to the next YouTube stream that has already been set up and I hope is already running. As we're doing that, we are getting ready for hour number 33. We only have 17 hours left. Thank you so much for joining us. You're watching the 2026 Weather and Climate live stream. I will be handing it off as host in just a moment. I believe we have Dr. Singer ready in the background. I saw them up on chat, and I believe she'll be taking over for me for the next 2 hours. As we're waiting right now for all of you to head over to the next stream, again, weatherandclimatelivestream.com/watch. If the stream has already been cut out, please go to the website right now and move over to the next YouTube live stream. We're going on right now. We're glad to have you. Hope you're all catching and moving over. This is the 2026 version of the Weather and Climate live stream. We're so glad to have all of you watching and joining with us. And we're all here for